Welcome to React Katas, a steady way to work in a world where most of the code around you was generated. These lessons exist so you understand this technology from the inside. That is what lets you work effectively with code and AI wrote rather than only trusting it. Kata is a practice loop borrowed from martial arts. Read it, code it, review what you wrote. 47 of them are stacked up behind the sentence, and each one is a reference you come back to after you have tried the thing yourself, not before. So here is how to use this video. The chapter list in the description has every lesson in it. Pick one, watch it, then open the playground, close the video and write the code without looking. When it does not work, come back and find the part you are wrong about. That loop is where the learning happens, and it is the part a video genuinely cannot do for you. One lesson a day for 7 weeks will teach you more than one afternoon of all of them. The cards between lessons are there for that reason. 2 questions each, about your own code rather than about mine. If you cannot answer them, that is the signal to go back rather than forward. The course is 8 sections, and they are meant to be taken in order. It starts with what a component actually is and how state and events really work underneath. Then hooks and why most of the effects people write should not exist. Then performance, which is really one idea. Renders are cheap and DOM updates are not. Then the patterns a component library is built from, how state is shared at scale, and what accessibility asks of you. It ends with 5 interview problems and 3 questions that have no code in them at all, because at some point the limit on a code base stops being what you know and starts being what your team defends. And the goal is narrower than it looks, not to memorize an API. A model will write most of this code for you faster than you can, and it will be right most of the time. What it cannot do is tell you when it is wrong. That judgment comes from having built the thing yourself at least once, and it is the only part of this that stays yours. Everything is free, the link is in the description, and the first lesson starts in a moment. Read it, code it, review it. Something has changed about learning React. You can generate a working component in seconds now. What you cannot generate is the judgment to tell whether it is any good. That is what this course is for. 46 lessons from JSX through hooks, performance, patterns, state management, accessibility, machine coding, and architecture. Every one of them runs in your browser. No setup, no install, no account. Each lesson is short and has a live playground. You read the idea, then you change the code and watch what breaks. Reading React carefully is a different skill from typing it from memory, and it is the skill that decides whether generated code ships or bites you later. When a model writes an effect that fires twice, a memo that never helps, or a key that quietly reorders your list, you need to recognize it on site. That recognition is what we practice here lesson by lesson on code you can run. So the goal here is narrow and practical. Learn enough React to work effectively with any large language model. Enough to read what it generated and know whether it is right. Enough to maintain that code once it is in your code base and the model has moved on. It is free and open source, new lessons weekly, and the link is in the description. A kata is something you practice, not something you watch. Read the lesson, write the code yourself, then review what you wrote. This video is the reference you come back to afterwards. A model can produce this code in seconds, and the reason to write it by hand is to keep the judgment that tells you whether the code is any good. This lesson covers JSX syntax, how to embed expressions in it, how to render conditionally, and how fragments let you group elements without adding extra nodes to the page. JSX stands for JavaScript XML. It may look like HTML, but it is actually JavaScript in disguise. React transforms this JSX into regular JavaScript function calls behind the scenes. This transformation is what makes JSX so powerful in React development. By allowing us to write HTML-like syntax within JavaScript, JSX simplifies the process of creating dynamic user interfaces. This is because you can use JavaScript logic directly within your markup. Imagine building a complex UI with pure JavaScript. It would involve lots of document manipulation, making it hard to read and maintain. JSX abstracts that complexity away. It does so while still giving you full access to the power of JavaScript. That's why JSX is the foundation of React development. In JSX, you can embed any JavaScript expression by wrapping it in curly braces. This means you can easily integrate dynamic content within your UI. Say you want to display the result of a simple math operation on your page. You can write 2 + 2 inside curly braces and JSX will evaluate it for you. Similarly, you can embed variables. Consider a variable holding the current year. Wrapping it in curly braces allows JSX to display the year directly in the markup. Another powerful feature of JSX is its support for conditional expressions. For instance, you can use a ternary operator within curly braces. This lets you render different content based on a condition. Whether you're displaying a simple variable, performing an operation, or using logical expressions, JSX handles it seamlessly. This flexibility makes JSX extremely useful for building dynamic and interactive user interfaces. Look at how JSX handles different types of expressions. First, consider variables. You can directly use them inside JSX by enclosing them in curly braces. This is useful for displaying dynamic data such as user inputs or API responses. Next, think about function calls. You can call a JavaScript function within JSX, again using curly braces. This is particularly helpful when you need to execute something dynamically based on user actions. Conditional expressions in JSX allow for if-else logic. You can use a ternary operator to choose between two different outputs. This is very handy for rendering different components or messages based on application state. Each of these examples demonstrates the power and versatility of JSX in embedding JavaScript logic within your UI. It allows you to build responsive and dynamic interfaces with ease. When using JSX, there are some important rules to follow. First, JSX must return a single root element. If you have multiple elements, wrap them in a parent tag or use a React fragment. This is because JSX needs to convert to a single JavaScript function call. Second, always close your tags. Even self-closing tags like images need to be properly closed. This is different from regular HTML where some tags can remain open. Third, use camel case for HTML attributes. Instead of writing HTML attributes like you normally would, convert them to camel case. For example, use onClick instead of onClick. Lastly, be careful with reserved words in JavaScript. In JSX, you cannot use class because it is a reserved word. Instead, use class name to apply CSS classes. Following these rules ensures that your JSX compiles correctly and functions as expected. React fragments allow you to return multiple elements from a component without adding extra nodes to the DOM. This is useful when you want to group a list of children without wrapping them in an unnecessary element. For instance, if you have two paragraphs that you want to render side by side, you can use a fragment. This will keep the DOM clean and avoid additional divs or spans that could complicate your layout. To use fragments, you simply enclose the elements you want to group in an empty tag. React will handle the rest, ensuring that no extra nodes appear in the DOM. This is an efficient way to manage the structure of your components without interfering with their styling or layout. It's a simple yet powerful feature for maintaining clean and organized code. JSX is a syntax extension for JavaScript that makes React code more readable and intuitive. It allows you to write HTML-like markup directly within JavaScript files. React transforms this JSX into JavaScript function calls which power your application. Use curly braces to embed JavaScript expressions in your JSX. This lets you integrate dynamic content seamlessly. Follow important JSX rules. This includes returning a single root element, closing all tags, and using camel case for attributes. React fragments let you group multiple elements without adding extra nodes to the DOM. This keeps your code clean and your application efficient. Understanding these concepts is crucial for building effective React applications. We have a file named app.tsx on the screen. Go through what it sets up and how it works. At the top, you see an import statement bringing in the useState hook from React. This is important for managing state within a functional component. Next, we have a function called greeting. This function takes a prop called name and returns a paragraph element. The paragraph says hello followed by the name in bold. This is a simple example of using props in a React component. Let's look at the main app component. We've set up a state variable called text using the useState hook. This variable will hold the text input value. There's also a variable called current year, which stores the current year using JavaScript's date object. We then have a Boolean variable isLearning set to true. Inside the return statement, you see a div with some inline styles. This div contains multiple sections. The first section demonstrates embedding expressions in JSX. It displays a list with math operations, the current year, and a ternary expression. The second section is about conditional rendering. You see an input field where users can type their name. If the text state is not empty, the greeting component displays. Otherwise, a message prompts the user to enter their name. The last section shows React fragments in action. 2 paragraphs are wrapped in a fragment to prevent adding extra DOM nodes. To experiment, you can try changing the initial value of the text state or modifying the isLearning variable. Notice how these changes are immediately reflected in the rendered output. This interactive environment is great for understanding how JSX and React work together. The key concept to remember from this lesson is that JSX makes your React code more readable and intuitive. By understanding how it works and following its rules, you can build dynamic and efficient user interfaces with ease. The kata is the part that matters. Open the lesson, write the code yourself, then read back what you wrote and judge it. The link is in the description, and that practice is what keeps the skill yours. A kata is something you practice, not something you watch. Read the lesson, write the code yourself, then review what you wrote. This video is the reference you come back to afterwards. A model can produce this code in seconds, and the reason to write it by hand is to keep the judgment that tells you whether the code is any good. This lesson is about the difference between a component and an element. A component is a function you write. An element is the object that function call produces. They are easy to blur together because JSX makes them look the same on the page. Getting them apart explains why calling a component directly breaks its hooks, and why React can sometimes skip re-rendering part of your tree. A React element is a plain JavaScript object. It describes what you want on the screen and nothing more. It has a type, some props, and a key. That is the whole shape of it. An element is immutable, so once it exists, you do not change its props or its children. Creating one is cheap because you are only allocating a small object. React holds on to these objects and compares the new ones against the old ones to work out what actually has to change in the DOM. A component is a function that takes props and returns elements. It is the definition, not the result. The component says how to build a piece of UI, and the element is one particular piece built from it. React is the one that calls your function. You hand React the element, React decides when to invoke the component behind it, and React keeps track of the state and effects that belong to each call. You can see the difference at runtime without any tooling. Ask for the type of the component itself and you get back a function. Ask for the type of the element the component produces and you get back an object. That is the whole distinction in one line of output. React treats the two differently for exactly that reason. A function is something to call later. An object is a description to compare against the last one. JSX is a syntax extension, not a language feature. A JSX tag compiles down to a create element call, and create element returns the element object we have been describing. So writing an angle bracket greeting tag and writing create element of greeting produce exactly the same object. Neither one calls the greeting function. This is worth holding on to because it is the step where most of the confusion starts. Writing the tag builds a description. Something else has to decide when to run it. Element identity is what React checks during reconciliation. When React walks the tree, it compares the new element in a position against the element that was there before. If it is the exact same object, by reference, React knows nothing in that subtree can have changed, so it skips it. That is a real bailout, not an optimization you have to ask for. It is also the mechanism behind passing elements through as children. A parent that re-renders does not rebuild the children it was handed, so those children keep their identity and get skipped. The lesson has a demo that puts the two side by side. One element is created once and kept in state. The other is written inline, so a fresh object is built on every render. Both render the same component and both look identical on screen. Then you re-render the parent and only the inline one counts up. The stored element is the same object it was before, so React leaves that subtree alone. The inline element is a new object every time, so React has to go and check it. A few things are worth stating plainly because they trip people up. Writing a JSX tag does not call the component function. It builds an element and React calls the function later. An element is not a component. The component is the function and the element is the object it describes. Creating elements is not the expensive part. Rendering is, because rendering is where your function actually runs. And calling a component directly as a plain function is not the same as rendering it. React never sees a separate component there, so the hooks inside it get attributed to whoever called it. A component is a function that returns elements. An element is a plain object describing what to render. JSX compiles to create element, which builds that object without invoking your function. React calls your component during rendering on its own schedule. And when the same element object comes back in the same position, React can skip that part of the tree. The practical rule that falls out of all of it is to let React call your components by rendering elements rather than calling them yourself. The playground ships this lesson in 3 implementations, and the first one is the mistake start at the top. It imports useState from React, and that is the only import it needs. Below that is greeting, a component taking a name prop. It holds its own state, a wave count starting at 0, and it returns a div with the name, the count, and a button that increments the count. On its own, that component is completely ordinary. Now look at app underneath it. App holds its own piece of state, a boolean called show, and renders a heading and a button that toggles it. The last line inside the div is the one that matters. Greeting is called as a plain function with an object argument rather than rendered as a tag. It works in the sense that something appears on screen, but React never learns that greeting exists. There is no separate component here, only app calling a function that happens to run a hook. So the wave count is app's state, not greetings, and the comment above that line says exactly that. Watch what the toggle does. Hiding greeting changes how many hooks app runs, and the hook order React depends on stops being stable. Try clicking wave a few times and then toggling. This is the same file with one line change. The imports are the same, and greeting above is unchanged, still holding its own wave count and rendering the same markup. App is unchanged too, right down to the toggle button and the show state. The difference is the last line. Greeting is written as a JSX tag now, with name passed as an attribute rather than as an object argument. That single change means the expression builds an element instead of calling the function. App hands that element to React. React sees a greeting component and it gives that component its own place to keep state. Now the wave count belongs to greeting where it was always meant to be. Toggling it off unmounts the component and its state goes with it, which is the behavior you would expect. The background color changed from red to green, so the two versions are easy to tell apart when you flip between them. Nothing else about the file moved. The third implementation is the evidence for everything in the lesson. The imports are wider here. useState, create element, and useRef. Greeting at the top is trimmed down to a heading because it is only being used as something to point at. Then render counter, which is the measuring instrument. It takes a label and it keeps a count in a ref rather than in state. A ref is the right tool because incrementing it does not cause a render, so it can count renders without changing the thing it is counting. Below that, describe element is a helper that takes an element and prints its type, its props, and its key as readable text. That is how the page shows you the inside of an element object. Now up. It holds a count in state for forcing re-renders. It builds an element from a JSX tag and a second element from a create element call with the same component and the same props. And it builds a third element inside a useState initializer so that one is created once and kept. The initializer is a function on purpose. That is what makes it run only on the first render. The markup below is 3 numbered sections that each show one of those. Section 1 prints the type of greeting and the type of the element, function against object with the element's contents underneath. Section 2 prints the create element version, and you can compare the 2 blocks and see the same object. Section 3 is the identity demo, a button that bumps the parent's count, then the stored element, then an inline render counter. Press the button and watch the 2 counters diverge. Change the label strings and rerun, then try moving the stored element into the markup as a plain tag and see the difference disappear. The short version is that a component is the function and an element is the object. JSX builds objects, React calls the functions. Everything else in this lesson follows from that, including why the hooks broke in the first implementation and why one counter stopped counting in the third. The kata is the part that matters. Open the lesson, write the code yourself, then read back what you wrote and judge it. The link is in the description, and that practice is what keeps the skill yours. A kata is something you practice, not something you watch. Read the lesson, write the code yourself, then review what you wrote. This video is the reference you come back to afterwards. A model can produce this code in seconds, and the reason to write it by hand is to keep the judgment that tells you whether the code is any good. A component is a function that returns a piece of user interface. Props are the arguments you pass it. Those two ideas are most of what you need to split an interface into parts you can build and change independently. The lesson covers how props flow from a parent into a child, why the children prop is treated differently from the rest, and what composition buys you once the pieces are small. In React 19, function components are the standard. A component is simply a JavaScript function that returns JSX, which is a syntax extension that looks similar to HTML. By using components, you can create custom elements that encapsulate both structure and behavior. For instance, a button component might include both its appearance and logic to handle clicks. This encapsulation helps keep your code organized, allowing you to focus on individual parts of the UI without getting overwhelmed by the entire application. Props, short for properties, are how you pass data from parent components to child components in React. They work much like function arguments, allowing you to customize a component's behavior or appearance based on the data passed in. For example, you might have a greeting component that takes a name as a prop and displays a personalized message. Props enable dynamic and flexible components, providing a way to control how components render based on external data. Always remember, props are read-only, meaning you cannot modify them within the child component. They maintain a one-way data flow, ensuring predictability in your application. Destructuring props in the function parameters is a common pattern in modern React. It simplifies your code by extracting values directly within the parameter list. Instead of accessing each property with the dot notation, you can directly use the property names. This makes the code cleaner and more readable. For example, if your component receives a name and age, destructuring allows you to write them directly in the function signature. This approach reduces boilerplate code and helps focus on the component's logic. The children prop is unique in React, allowing you to pass elements between the opening and closing tags of a component. It is fundamental to composition, enabling you to nest components and pass multiple elements as children. This makes it easier to build flexible layouts. For instance, a card component can wrap around any content, making it reusable for different purposes. The children prop acts as a placeholder for whatever content you want to display within the component. This flexibility is a key feature of React, allowing you to compose complex UIs from simpler building blocks. The welcome card on screen is rendered by a component that knows nothing about what is inside it. 2 paragraphs and a button were written between its opening and closing tags, and all 3 arrive together as the children prop. The card supplies the border, the padding, and the title, then renders whatever it was handed. Nothing about that button is written into the card, which is why the same card can hold a form on the next page. Children is one prop, whether you pass one element or several. Composition means building a larger component out of smaller ones rather than writing one long function. The user profile below is the example. It renders an avatar, a block of user information, and a list of skills, and its own body is 4 lines long because each of those is a component of its own. The code underneath it shows the whole thing. Every piece can be read, tested, and changed on its own, and the profile is where they are arranged. How far to take this is a matter of judgment. Splitting a component that only ever appears in one place buys you very little, and you can end up chasing a prop through 4 files to find where it is used. Components are pieces of user interface defined as functions that return JSX. Props carry data from a parent to a child in one direction only. Destructuring them in the parameter list puts the component's inputs in its signature, where they are easy to read. The children prop is what makes a wrapper component possible because it lets the parent decide the contents. Props are read only, So a component never writes to the ones it was given. If a child needs to change something, the parent owns that value and passes down a function to change it. This variant demonstrates a common mistake when using components. Notice the function named greeting with a lowercase g. In React, lowercase names are treated as standard HTML elements. Here, the greeting function is intended to be a React component. But because it is lowercase, React attempts to render it as a native HTML element. This results in the function not being called at all. In the app component, the greeting tag is used, but React renders it as is without invoking the function. Check the console to see a warning about an unknown element. This is a reminder to always capitalize component names to ensure React treats them as custom components. In this variant, the greeting function is correctly capitalized as greeting. With this change, React recognizes it as a custom component. The app component now successfully renders the greeting component with the name prop. You can see the rendered output displaying personalized greetings for Ada and Grace. This example shows the importance of naming conventions in React. By capitalizing component names, you ensure that React treats them as intended, allowing your components to function correctly. This variant showcases different patterns for using props in React components. At the top, you see imports for useState and React Node, which are used for state management and typing the children prop respectively. The greeting component now takes both name and age props, providing a more detailed greeting. Below, the card component uses the children prop to display any nested content between its tags. The badge component demonstrates styling with props, as each badge's label is passed as a prop. In the app component, state is managed with useState to dynamically update the name. By entering a name in the input field, you can see real-time updates in the greeting component within the dynamic card. This example highlights how props and state work together to create interactive components and how composition can encapsulate different elements to build a cohesive user interface. The one idea worth keeping is that a component is a function of its props. Give it the same props and it renders the same thing, which is what makes a component you can reason about on its own. Capitalize the name, so React calls it, keep the props read-only and let children carry whatever the parent wants inside. The kata is the part that matters. Open the lesson, write the code yourself, then read back what you wrote and judge it. The link is in the description, and that practice is what keeps the skill yours. A kata is something you practice, not something you watch. Read the lesson, write the code yourself, then review what you wrote. This video is the reference you come back to afterwards. A model can produce this code in seconds, and the reason to write it by hand is to keep the judgment that tells you whether the code is any good. A component that cannot remember anything can only ever show you the same thing. State is the memory and useState is how you ask React for it. This lesson covers why a plain variable will not do the job, how several pieces of state live side by side in one component, and what React does with your updates before it re-renders anything. There is a working counter, a form, and a batching example on the page. At the end, there is a playground with the broken version and the fixed one 2 lines apart. State is the data a component is allowed to remember between renders. Here is the part that makes the rest of it make sense. Your component is a function, and React calls that function again every time it needs new output. Every variable declared inside it is created from scratch on that call. So a plain variable cannot survive a render, no matter what you assign to it. React keeps state somewhere else, attached to this component's position in the tree, and hands it back to you each time the function runs. That is why setting state and setting a variable are not the same operation. Setting state also tells React that this component's output is now out of date and schedules the function to run again. The counter on screen is the smallest thing that needs memory. The number is state, and the 3 buttons are the only things that change it. Look at the shape of the call underneath it. useState is given the starting value and it hands back a pair. The current value and a function that sets the next one. Both names are yours to choose. Calling that setter is the whole mechanism. It stores the new value and marks the component as needing another render. Notice that increment passes a function to the setter rather than a number. That function receives the value React has queued so far, which is the reliable way to base a new value on the old one. A component is not limited to one piece of state. call useState again and you get another value with its own setter, independent of the first. React tells the two apart by the order the calls happen in. That is why hooks are always called at the top level of a component, never inside a condition or a loop. Keep unrelated values in separate pieces of state. Bundling them into one object means every update has to copy the rest of it forward, and you get nothing back for that work. The form here holds one piece of state, the text in the box. Every keystroke fires a change handler that sets the state to whatever the input now contains, and the box displays what state holds. That round trip is what makes it a controlled input. It is also why the line underneath can greet you on the same keystroke. Two things on screen are reading one value, so they cannot disagree with each other. The two columns on screen are worth reading side by side. State belongs to the component, and the component is the only thing that can change it. Props arrive from the parent, and the component only reads them. The useful question is not which one is better, it is who owns the value. If two components need the same value, it stops being state in either of them. It moves up to their nearest shared parent and comes back down to both as props. That move has a name, lifting state up, and you will do it constantly. The button here toggles a single true or false value, and the message below it appears or disappears. Nothing is hiding that message with a style rule. When the value is false, the component simply does not return that element, so it is not in the output at all. That distinction matters more than it looks. A hidden element is still mounted and still holding whatever it was holding. An absent one has been thrown away, and when it comes back new. Setting state does not re-render on the spot. React queues the update and carries on with the rest of your handler. The example on screen queues 3 updates in a row, and the component renders once afterwards with all 3 applied. Read a value straight after calling its setter, and you will still see the old one because the variables belonging to the current render never change. From React 18 onwards, this batching applies everywhere, not only inside event handlers. Updates from a timeout, a promise callback, or a native event are batched the same way. The lesson you're watching runs React 19.2. The reason for any of it is plain enough. 3 renders where one will do is 3 times the work for the same picture. useState adds one piece of memory to a function component and returns the current value with a setter. Calling that setter is what schedules the re-render. Assigning to the variable does nothing at all. One component can hold as many pieces of state as it needs as long as the hooks are called in the same order on every render. State is private to the component that owns it, and props come from the parent and are read only. One correction to the wording on screen. State is not mutable. You never edit a piece of state in place. You hand React a new value and it replaces the old one on the next render. This first version is the mistake that is worth making once deliberately. The component keeps its count in a plain variable declared inside the function, starting at 0. The increment function adds 1 to it and logs the result. Click the plus button and the console really does count up, so the code runs and the arithmetic is right. The heading never moves. 2 things are going wrong at the same time. Nothing has told React that anything changed, so it never calls the component again. And if something did call it, the function would run from the top and create that variable at 0 all over again. The note in the middle of the screen says exactly that. The variable updates, the interface does not. The reset button at the bottom has the same problem in a shorter form. It assigns 0 to a variable that nobody will ever read again. The working version opens with the import because useState comes from React. Then 2 calls, one for the count and one for the name, each returning its value and its setter. The counter markup is unchanged from the first version. Same heading, same buttons. It updates now purely because those buttons call a setter instead of assigning to a variable. Plus and minus both pass a function, so each one works from the value React has already queued. Reset passes a plain 0, which is fine when the new value does not depend on the old one. Below the counter is the second piece of state. The input is controlled. Its value comes from state, and its change handler writes every keystroke back. The last line renders the greeting only when the name is not empty, which is the conditional rendering from earlier in a single line. 2 independent pieces of state in one component, and neither one knows the other exists. The model to keep is short. A component is a function that React can call again whenever it likes. Anything that has to survive that call must be held by React, not by the function. useState is how you ask for that, and the setter is how you tell React the value has changed and the output is stale. Everything else in this lesson follows from those 2 sentences. The next time you assign to a variable inside a component and wonder why the screen will not update, that is the question to ask. Who is holding this value? The kata is the part that matters. Open the lesson, write the code yourself, then read back what you wrote and judge it. The link is in the description, and that practice is what keeps the skill yours. A kata is something you practice, not something you watch. Read the lesson, write the code yourself, then review what you wrote. This video is the reference you come back to afterwards. A model can produce this code in seconds, and the reason to write it by hand is to keep the judgment that tells you whether the code is any good. Writing a click handler in React takes about 10 seconds, and almost nothing about it is what it appears to be. The handler you passed is not attached to that button. The event object you receive is not the browser's event. This lesson covers the handlers you will actually write: clicks, mouse moves, form submits, and keystrokes, and then goes under them to what React is really doing with the browser's event system. There is one mistake near the start that everybody makes exactly once, and it is worth making on purpose. The click handler is the one you will write most often, and the shape of it is worth getting exactly right. You hand the onClick property a function. You do not call it. That distinction is the single most common error in React, and it does not fail the way you expect. Calling the function there runs it while the component is rendering and hands React whatever it returned. So the thing happens immediately once and then never again when you actually click. The playground at the end of this lesson has that mistake in it running, so you can watch it happen. The counter on screen is the working version. Every click adds 1, and the number above the button is state, so React re-renders and the count you see keeps up. The handler is an arrow function, which is what you reach for whenever the thing you want to run needs arguments. React calls that arrow function on the click, and the arrow function calls what you actually wanted. Clicks are one member of a family. React gives you mouse move, mouse enter, mouse leave, mouse down, and mouse up, and the names all follow the same rule: on, then the event name in camel case. Enter and leave are the two worth knowing properly. Unlike the older mouse over and mouse out, they do not fire again as the pointer crosses into a child element, which is the bug behind most hover effects that flicker. Move your pointer over the box on screen and the two numbers under it follow. The handler reads two properties of the event, client X and client Y, and puts them into state. Those coordinates are relative to the visible part of the window, not to the box and not to the page, so scrolling changes them without the pointer moving at all. Every mouse move fires this handler, which is dozens of events a second, and each one sets state. That is fine for two numbers on screen, and it is the first thing to look at if a mouse handler ever makes a page feel heavy. Forms need two handlers. On change fires as the user types, and on submit fires when the form is submitted. There is a detail hiding in the first one. Reacts on change is not the browser's change event. The browser fires change only when the field loses focus, which is far too late to be useful. React wires on change to the native input event instead, so it fires on every keystroke, which is what everybody assumes it does. It is one of the few places React quietly renames something to match what people expect. The form on screen has two fields and a submit button, and pressing submit puts the values in the panel underneath rather than reloading the page. Prevent default is what buys that. A form submit is a navigation as far as the browser is concerned, and unless you say otherwise, the page goes away and takes your application state with it. Notice also that one change handler serves both inputs. It reads the field's name of the event target and uses it to update that key in the state object, which is how a form with 12 fields still has one handler. Keyboard input comes through key down, key up, and key press. Reach for key down. Key press has been deprecated for years and never fired for keys that do not produce a character, so arrow keys and escape went straight past it. The event carries the key itself as a string in the key property. That is the character for a printable key, and a name like enter, escape, or arrow down for the rest. The box on screen reports the last key it saw. Type into it and the line underneath names the key, one word exactly as the event reported it. Try the keys that are not characters. Shift and the arrows come through with names rather than symbols, and that is the property you compare against when you want enter to submit something or escape to close it. Every handler is passed one argument, and the list on screen is the part of it worth memorizing. Target is the element the event started on. Current target is the element whose handler is running, which is the same thing until the event has bubbled up from a child and then it is not. Prevent default cancels what the browser would otherwise do. Stop propagation stops the event traveling further up. And the event-specific properties key for the keyboard, client X and client Y for the mouse carry the actual payload. One thing you may read elsewhere that is no longer true, these objects used to be pooled and reused, and you had to call persist to keep one. React 17 removed that. This lesson runs React 19.2, so the event object is an ordinary object that you can keep. 4 patterns on screen, and the first one is the error. Calling the function runs it now. Passing the function's name hands, react something to call later, which is what you want when the handler needs no arguments. The inline arrow function is what you want when it does, because the arrow closes over the argument and defers the call. And the fourth takes the event as a parameter, which you need whenever you're about to call prevent default or read a value of it. Almost every handler you write is one of those last 3. Here is the part that changes how you read all of it. React does not attach your click handler to that button. It attaches one listener per event type to the root container, the element you handed to create root when the application started, and nothing else in your tree has a listener at all. So when you click a button, the browser's own event bubbles all the way up to the root. React catches it there, works out from its own tree which component that element belongs to, wraps the native event in a synthetic one, and calls your handler. Then it walks up its own component tree, calling any parent handlers, which is React reproducing bubbling rather than the browser doing it. 2 consequences fall straight out of that. Thousands of rows cost you one listener, not thousands. And if some non-React code between the button and the root calls stop propagation on the native event, the event never arrives at the root, and your React handler simply never runs. That one is worth remembering the first time a handler goes silent for no visible reason. Pass functions to handlers, do not call them. Use an arrow function when you need to pass arguments. Call prevent default in any submit handler or the page reloads. The event you receive is React's synthetic event, consistent across browsers, and since React 17, no longer pooled. And underneath the whole thing, there is one listener at the root of your application, not one per element, which is the fact that explains the rest. This first version has the mistake running, so you can see what it actually looks like. 2 pieces of state and 2 buttons. Look at the first buttons on click. Alert is being called right there in the middle of rendering. The alert fires the moment this component renders before anyone has clicked anything, and what gets handed to onClick is alert's return value, which is undefined. So the button does nothing at all when you click it. The second button is the interesting part of the demonstration. It only forces a re-render, and every time you press it, the alert comes back, because rendering is what triggers it. A handler that fires when you are not clicking and ignores you when you are is the signature of this bug. The fix is small enough to miss. The alert is now inside an arrow function, so what onClick receives is a function to call later rather than the result of calling it now. Nothing fires on render. The click fires the alert and only the click. The second button is unchanged and still increments the counter, and the count above it now goes up on click rather than announcing itself on every render. If you take one line from this lesson, it is this one. The last variant puts all 3 families in one component so you can see them side by side. It opens with 4 pieces of state, a click count, the last key, an object holding the form fields, and the submitted result, which starts as null and is the thing that decides whether the result panel renders at all. Then 2 handlers defined above the markup. Handle submit calls prevent default first, stores what was submitted, and clears the fields. Handle change is the one worth studying. It reads both name and value of the event target and writes back a new object with that one key replaced, so the same 3 lines serve every input in the form. Below that, the markup in 3 sections. The click section increments and resets a counter. The keyboard section reads the key property on key down and shows it. The form section wires each input's name and change handler and hangs the result panel off whether submitted has anything in it. 3 event families, 4 pieces of state, and the shape of nearly every form you will write. The model worth keeping is short. Your handler is not on the element. There is one listener at the root of the application. The browser's event bubbles up to it, and React works out from its own tree whose handler to call, then does the bubbling itself. Everything else follows from that. Why the event object is React's and not the browser's, why one listener serves 10,000 rows, and why stopping the native event somewhere in between makes your handler go quiet. Write the handlers first, then go back and read that paragraph again.
The kata is the part that matters.
Open the lesson, write the code yourself, then read back what you wrote and judge it. The link is in the description, and that practice is what keeps the skill yours. A kata is something you practice, not something you watch. Read the lesson, write the code yourself, then review what you wrote. This video is the reference you come back to afterwards. A model can produce this code in seconds, and the reason to write it by hand is to keep the judgment that tells you whether the code is any good. There is no conditional syntax in JSX. There is no if tag and there is no show when attribute, and none of the 5 patterns in this lesson are React features. They are all ordinary JavaScript expressions that happen to evaluate to something React can render. Once you see it that way, the patterns stop being things to memorize and become a single question. What does this expression evaluate to, and what does React do with that value? One of them evaluates to something you did not intend and puts a 0 on the screen in front of your users. That one is at the end. The first pattern is the one people skip, and it is often the right answer. Work out what to render before the return statement, put it in a variable, and then render the variable. Plain if and else, no cleverness. This is what you want the moment the decision needs more than one line or an early exit or a comment explaining why. JSX has no if because it does not need one. Everything above the return is normal JavaScript and you can use all of it. The demo here toggles between 2 states and swaps the message with it. The code underneath is the shape to copy a variable declared before the return, assigned in a branch, and then dropped into the markup in braces. The important part is what that variable holds. It is JSX sitting in an ordinary JavaScript variable being passed around like any other value. That is the idea that makes the rest of this lesson obvious. The ternary operator is the one you will use most, and it is the right tool for exactly one job, 2 alternatives, one of which always renders condition, then the value when true, then the value when false. Because it is an expression rather than a statement, it can sit directly inside the markup, which is what if cannot do. The trap is nesting. A ternary inside a ternary inside a ternary is technically fine and unreadable by the next person, including you. When you reach the second level, that is the signal to go back to pattern 1 or to pull the branch out into its own component. 3 buttons on screen pick a role, and the panel underneath changes with it. The condition is a strict equality check against the string admin, and the 2 branches are the 2 panels. Notice that both branches are real markup, several elements each, wrapped in parentheses. That is what the parentheses are for here. They are not part of the ternary. They are how you give the operator a multi-line expression without JavaScript deciding the statement ended at the line break. Use and when there is nothing to show in the false case. Condition on the left, markup on the right, and if the condition is true, you get the markup. It reads like a sentence, and it is the shortest pattern here, which is why it is also the one that bites. The reason is what? And actually does. It is not a Boolean operator that returns true or false. It returns the left-hand value when that value is falsy and the right-hand value otherwise. So the thing React ends up rendering is whatever the left side was. Hold on to that sentence for the end of the lesson. The demo adds notifications to a list, and the block appears once there is at least one. The condition is a length compared against 0, not the length on its own, and that is deliberate. Compare it with the badge in the playground at the end of this lesson, which does exactly the same job with the comparison left out, and watch what appears on screen when the list is empty. Once there are 3 or more outcomes, both the ternary and the chain of AND stop being readable. A switch statement above the return handles it, returning the markup for each case with a default for the one you did not think of. The alternative on screen is an object whose keys are the states and whose values are the markup, and then you index into it. That version is compact and it removes the branching entirely, which is worth having when the set of states is fixed and known. Both are better than 4 nested ternaries. Loading, error, and success. 3 states, and every data fetching component you write will have these 3 plus an idle one before the request starts. Look at how each state gets its own complete piece of markup rather than one block with pieces switched on and off inside it. That separation is what makes the error state easy to design properly instead of being a red line bolted onto the success layout. A component can return null and React renders nothing at all for it. No wrapper, no empty element, nothing in the DOM. This is how a modal, a tooltip, or a banner is written. The parent always renders the component and the component itself decides whether it is on screen. That is worth preferring over wrapping it in a condition at the call side, because the rule about when it shows lives inside the thing it applies to rather than being repeated at every place that uses it. The modal on screen is that pattern. Its first line checks whether it is open and returns null if it is not, so everything below that line can assume it is visible. One thing to be clear about, returning null unmounts it. This is not hiding with a style rule. The component state goes, and when it comes back fresh. Most of the time that is what you want from a modal, and when it is not, that is the moment to lift the state up to the parent instead. The list on screen is the short version of everything above. And for show and hide, ternary for two alternatives. Switch or a lookup object for more than two. Never nest ternaries deeply. Pull a complicated condition out into its own component. And the one in the middle, which is the reason this lesson has a bug demo attached, do not use and with a number on the left. None of these are React syntax. They are JavaScript expressions in braces, and React renders whatever they evaluate to. It ignores true, false, null, and undefined, and it renders everything else it can, which includes 0. Useif statements above the return when the logic is complex, the ternary for two outcomes, and for one, a switch or a lookup for many, and null when a component should not be there at all. This is the bug running. A notification badge with a count that starts at 0, a button to add one, and a button to clear. The last line uses and with the count on the left, which reads as if there is a count, show the message. Add a notification and it works exactly as intended. Now clear it and a 0 appears on the screen. Not the message, not nothing, the digit 0 rendered as text in your interface. Here is why, and it follows from what, and actually does. When the left side is falsy and returns the left side, 0 is falsy, so the expression evaluates to 0 and React is handed the number 0 to render. React skips true, false, null, and undefined, and 0 is none of those. It is a perfectly good thing to put on a page, so React puts it on the page. The operator did the right thing, JavaScript did the right thing, React did the right thing, and your users can see a stray 0. The fix is to put a real boolean on the left. Count greater than 0 evaluates to true or false and nothing else, so the expression is either the markup or false, and React ignores false. This version also adds the empty case as a second line with an explicit check for count equal to 0, which is the honest way to write it. Two conditions, two outcomes, both visible. The same care applies to any value that can be 0 or an empty string. The habit worth building is that the left-hand side of and is always a comparison, never a bare value. The last variant is all of it in one component, so you can read the patterns against each other. It opens with the state that drives the demos and a status value that moves between loading, error, and success. Then the sections. The ternary section switches between two panels on a boolean. The end section shows a block only when a list has something in it, with the comparison written out. The switch section maps a status string to a different piece of markup for each case, with a default at the end. Read down the file and notice that all three do the same job, and the only thing that changes is how many outcomes there are. That is the whole decision. Count the outcomes, then pick the pattern. The model to keep is one sentence. Braces in JSX hold an expression, and React renders whatever it evaluates to, skipping only true, false, null, and undefined. Every pattern in this lesson follows from that, and so does the bug. 0 is not on the skip list. Next time you write and in your markup, look at the left-hand side and ask whether it is a boolean. If it is not, make it one.
The kata is the part that matters.
Open the lesson, write the code yourself, then read back what you wrote and judge it. The link is in the description, and that practice is what keeps the skill yours. A kata is something you practice, not something you watch. Read the lesson, write the code yourself, then review what you wrote. This video is the reference you come back to afterwards. A model can produce this code in seconds, and the reason to write it by hand is to keep the judgment that tells you whether the code is any good. UseEffect is the hook people reach for first and understand last. Most of that is because it gets taught as a lifecycle method with a strange signature, and it is not one. It has a single job: keep something outside React in step with something inside it. The document title, a timer, a subscription, a listener on the window. Once that is the definition, the most useful thing this lesson can tell you is that a large share of the effects in real code bases should not exist at all, and the playground at the end has one of those next to its replacement. A side effect is any work that reaches outside the component. Fetching from an API, starting a timer, subscribing to something, touching the DOM directly, adding a listener. What all of those have in common is that they are not part of producing the output. Rendering is meant to be a calculation. Given this state and these props, return this markup and change nothing else on the way. Effects are where the changing something else goes, and keeping the two apart is what lets React call your component whenever it likes. One detail on screen worth sharpening. Effects do not just run after React updates the DOM, they run after the browser has painted it. So the user sees the new frame first and your effect runs after. That is deliberate, and it is why an effect is the wrong place to measure or adjust layout. Two arguments: a function holding the work and an array. The array is where the confusion lives because it looks like a list of triggers, and it is not. It is a list of values to compare. After every single render, React compares each item against what it was last time, and if they are all the same, it skips the effect. So no array at all means nothing to compare, so it runs every render. An empty array means nothing ever changes, so it runs once. And a populated array means it runs whenever one of those values differs. Same mechanism in all three cases, which is easier to hold on to than three separate rules. The first example writes the count into the browser tab title. This is the shape of a proper effect: a value inside React, a thing outside it, and a line keeping the second in step with the first. The count is in the dependency array, so it runs when the count changes and not otherwise. Watch the tab as you press the button. Nothing about this could be done during render because writing to the document title is exactly the kind of outside world change that render is not allowed to make. An empty dependency array means the comparison never finds a difference, so the effect runs after the first render and never again. This is where setup goes: opening a connection, reading something once, starting a subscription. There is a detail here that catches everybody in development. React's strict mode deliberately mounts your component, unmounts it and mounts it again, so this effect runs twice and your console logs twice. Nothing is broken. It is a test, and what it is testing is whether your cleanup actually undoes your setup. If running the effect twice breaks something, it would also break in production the moment that component remounted. Fix the cleanup rather than fighting the double run. An effect can return a function, and React calls it before running the effect again and once more when the component goes away. That is the cleanup. The timer here is the clearest case. Set an interval on the way in, clear it on the way out. Leave that out, and every remount starts another interval while the old ones keep firing, which is a leak that shows up as a counter that speeds up for no reason. The rule is worth stating as a pair. Anything you start in an effect, stop in its cleanup. Anything you subscribe to, unsubscribe from. Same pattern against the browser window. Add the listener on mount, remove it in the cleanup, and the width on screen tracks the window as you resize it. Two things to notice: the function you pass to add event listener and the one you pass to remove event listener have to be the same reference, or the removal silently does nothing. And the dependency array is empty here, which is only correct because the handler does not close over anything that changes. The moment it reads a piece of state, that state belongs in the array, and then the listener is removed and re-added when it changes. Fetching on mount is the example everybody starts with, and it is the one with the most sharp edges. The effect function itself cannot be isync because React reserves its return value for the cleanup, and an isync function returns a promise. So the isync work goes in an inner function that you call. Beyond that, a fetch needs to handle the response arriving after the component has gone, and two fetches resolving out of order. The next lesson is about cleanup properly, and that is where those get handled. It is also worth saying plainly that for real applications, this is a solved problem. A data library handles caching, retries, and race conditions, and writing it by hand is for understanding, not for production. 4 on screen, and they have one root. Missing dependencies means the effect closes over a value from an old render and quietly uses a stale one. An infinite loop means the effect sets a piece of state that is in its own dependency array, so it runs, changes the thing it watches, and runs again. Forgetting cleanup leaks the timer or the listener, and the effect function cannot be async for the reason we just covered. Turn on the exhaustive dependencies lint rule and let it fill the array in for you. When it demands something you were not expecting, that is usually the rule finding a bug rather than being annoying. An effect synchronizes React with something outside it, and it runs after the browser paints. The dependency array is a comparison, not a trigger list. Cleanup runs before the next effect and on unmount, and anything you start belongs in it. The effect function is never async. And the question to ask before writing one at all is whether the work reaches outside the component, because if it does not, there is a good chance it should not be an effect. This is the effect that should not exist, and it is extremely common. 3 pieces of state, a first name, a last name, and a full name. An effect watches the first two and sets the third to the two joined together. It works. It is also wrong in 3 separate ways. There is a piece of state holding something that was already derivable from other state, so now there are 2 sources for one fact. Every keystroke costs an extra render because React renders with the new first name, then runs the effect, then the setter schedules another render. And in between those 2 renders, the full name on screen is the previous one, so the value is briefly stale. Read the note in the middle of the preview. It says exactly that, and you can watch it happen. The fix removes code. The third piece of state is gone, the effect is gone, and the full name is a plain constant computed in the body of the component. 1 render per keystroke, no stale window, 1 source of truth. The reason this is safe is the thing worth taking away. Rendering is a function call, and recomputing a value during render is what render is for. If a value can be calculated from state and props you already have, calculate it. Reach for an effect only when the calculation is genuinely expensive, and even then the answer is a memo rather than a piece of state. The last variant is the other half of the argument because none of this means effects are bad. 3 pieces of state and 2 effects, and both of them earn their place. The first writes the count into the document title, which is an external system that React knows nothing about. The second runs an interval while the timer is running, and returns a cleanup that clears it, so nothing is left behind when it stops or when the component goes away. Read the 2 together and the test becomes concrete. Is this effect keeping something outside React in step with something inside it? These 2 are. The one in the first variant was not. The model to keep is a single question. Does this reach outside the component? A timer, a subscription, the document title, a listener on the window, those are outside and they need an effect and a cleanup that undoes it. A value computed from state you already hold is not outside, and it needs a line of arithmetic during render. Most of the useEffect confusion people carry around comes from using it for the second thing, and the fix there is not a better effect, it is no effect.
The kata is the part that matters.
Open the lesson, write the code yourself, then read back what you wrote and judge it. The link is in the description, and that practice is what keeps the skill yours. Kata is something you practice, not something you watch. Read the lesson, write the code yourself, then review what you wrote. This video is the reference you come back to afterwards. A model can produce this code in seconds, and the reason to write it by hand is to keep the judgment that tells you whether the code is any good. The function and effect returns is the most underused line in React, and the name people give it is part of why. Calling it the unmount handler makes it sound like a last write, something that runs once when the component disappears. It runs far more often than that. It runs before every single rerun of the effect, and then once more at the end. Once you see it as the undo half of a pair, rather than a teardown step, the patterns in this lesson stop being 5 separate recipes, and a debounce turns into 3 lines with no library. 4 failures on screen, and they are all the same failure wearing different clothes. Something was started and never stopped. A timer keeps firing after the component has gone. A listener holds a reference to a closure that holds a reference to state, so nothing can be collected. A slow response arrives after a fast one and overwrites newer data with older data. And each of those compounds, because the component that leaked one timer will leak another every time it mounts. The rule underneath is one sentence. If an effect starts something, its cleanup stops it. That is not a style preference. It is what makes the effect safe to run twice, which React will do. Timers are the clearest case because you can hear them. Set an interval in the effect, clear it in the cleanup using the handle the setter returned. Miss the cleanup and the interval outlives the component that created it, still holding whatever it closed over, still firing into a callback whose component no longer exists. The playground at the end of this lesson has exactly that running, and it shows the part that makes it worse than a single leak. Mount the component again, and there are 2 intervals, then 3, all ticking together. Listeners on the window or the document are the ones that outlive components most often because the object they are attached to never goes away. Add in the effect, remove in the cleanup. The one detail that silently defeats this is the reference. Remove event listener finds the handler by identity, so it has to be handed the same function object that was added. Define the handler inside the effect, use it in both calls, and that is guaranteed. Define it inline in both places, and you have added a listener and removed a different one, and the code looks correct. A socket connection, a store subscription, a database listener, all the same shaping. Open it on the way in, and the cleanup closes it or calls the unsubscribe function that was handed back when you subscribed. That returned function is worth noticing as a convention. A well-designed subscribe API gives you its own undo, and your cleanup is then a single line calling it. When an API does not do that, that is a small signal about how carefully it will handle the rest. This one prevents a bug that is genuinely hard to reproduce and easy to ship. Search as the user types, and a request goes out per keystroke. Requests do not come back in the order they were sent, so a slow response for an early query can land after a fast response for a later one, and the user sees results for something they finished typing 3 letters ago. Cleanup is what fixes it. Because the cleanup for the previous effect runs before the next one starts, you can have it mark that request as no longer wanted, and the handler checks that flag before touching state. An abort controller does the stronger version, cancelling the request itself, so it never comes back at all. Either way, the ordering guarantee is what you are relying on, and that is the whole reason cleanup runs before the rerun rather than after. This is the pattern that shows the mechanism most clearly, and it is my favorite thing in this lesson. Put a timeout in the effect that does the work after a delay and clear that timeout in the cleanup. Now type. Every keystroke changes the dependency, so React runs the cleanup first, which cancels the pending timeout and then sets a fresh one. The work only ever happens once the user stops long enough for a timeout to survive. That is a debounce, and there is no library, no ref, and no timer bookkeeping in it. It falls straight out of cleanup running before the next effect. The 2 blocks on screen are the same effect with 1 line of difference, and it is the difference between a timer that stops and a timer that runs until the page is closed. Worth adding 2 more that the page does not list. Returning the result of a call rather than the function itself, which runs your tear down immediately and cleans up nothing later. And a cleanup that reads a value from state, which sees the value from the render it was created in, not the current one. That second is not a bug in itself. It is often exactly what you want, but it surprises people the first time. Cleanup runs before the next effect and on unmount, which means it usually runs many times, not once. Anything started gets stopped. Timers, listeners, subscriptions, requests. Use the same function reference for adding and removing a listener. Use a flag or an abort controller to stop an out-of-date response from writing to state. And the same ordering that makes cleanup useful for teardown makes debouncing almost free. Here is the leak running, and the console is where you watch it. A small timer component starts an interval in an effect and returns nothing at all. Press the button and the component unmounts. The log keeps going. The component is gone from the tree, React is no longer rendering it, and its interval is still firing every second, holding on to the closure it was created with. Now press the button again to mount a fresh one. That is 2 intervals. again, and it is 3, all ticking in the same console. Nothing errors, nothing turns red, and the tab quietly does more work every time. This is what a leak looks like in practice, not a crash, just a page that gets heavier the longer someone uses it. The same component with one line added. The effect keeps the handle that the interval setter returned, and the function it returns clears it. Now unmount and the log stops immediately. Mount again and there is exactly one timer, however many times you cycle it. Watch what the console prints on the first mount in development though. The setup runs, the cleanup runs, and the setup runs again. That is strict mode checking this very thing. The first variant fails that check by leaving a timer behind, and the fact that this one passes it is the same fact that makes it safe. The last variant is the listener version, and it is short enough to read in one go. The handler is defined inside the effect, added to the window, and removed by the cleanup using that same name. The dependency array is empty because the handler closes over nothing that changes. That last point is the one to carry into your own code. The moment the handler reads a piece of state, the empty array is wrong, that state joins the array, and the listener is then removed and re-added whenever it changes, which is correct and is exactly what the cleanup makes possible. The model to keep is a pair, not a life cycle. Every effect that sets something up returns the line that tears it down, and React runs that line before every rerun and once at the end. Read your effects looking for the pair. If you can find the setup and not the undo, you have found either a leak or a race, and usually the console will show it to you inside a minute. The kata is the part that matters. Open the lesson, write the code yourself, then read back what you wrote and judge it. The link is in the description, and that practice is what keeps the skill yours. Kata is something you practice, not something you watch. Read the lesson, write the code yourself, then review what you wrote. This video is the reference you come back to afterwards. A model can produce this code in seconds, and the reason to write it by hand is to keep the judgment that tells you whether the code is any good. useRef gets introduced as the hook for grabbing DOM elements, which is one of its jobs and not the interesting one. What it actually gives you is a box that survives re-renders and that React does not watch. Everything else follows from those two properties. It is where you put the things a component needs to remember, but the screen does not need to know about. And it is the answer to a question this course has been building towards since State Basics. What do you do with a value that has to persist but must not cause a render? Call useRef with an initial value and you get back an object with a single property called current. Two things about that object matter, and both are easy to say and easy to forget. It is the same object on every render, not an equal object, the same one, so anything holding a reference to it sees your changes and React does not watch it. Assigning to current is a plain property assignment on a plain object, so nothing is scheduled, nothing re-renders, and the screen carries on showing whatever it was showing. That is not a limitation to work around, it is the entire point of the hook. The common case first, create a ref, pass it to an element's ref attribute, and React sets current to the real DOM node once that element is on the page. Then you can focus it, measure it, or scroll it. Note the ordering because it is the thing that catches people. React assigns the node after it has committed the DOM, which is after your render function has finished. So during the first render, current is still null, and any code in the body of the component that reaches into the node will fail. Read a DOM ref in an effect or in an event handler, never during render. The second use has nothing to do with the DOM, and it is where the hook earns its keep. Anything the component needs to carry between renders that the user never sees, whether this is the first render, a socket instance, an ID from a previous request, a counter you are keeping for yourself. Put it in a ref and mutate it freely. The test is one question. If this value changed and the screen did not update, would that be a bug? If yes, it is state. If no, it is a ref. Tracking the previous value of something is the neatest small demonstration of the hook. Keep a ref, and in an effect after the render has happened, assign the current value into it. Because effects run after paint, that assignment lands after everything on screen has already read the ref. So on the next render, the ref still holds the previous value, and by the time you write to it again, the render that needed it is done. It is a two-line trick that depends entirely on the ordering, and it will not work if you assign during render instead. Timer handles are the textbook case, and it is worth being clear why a plain variable fails here. A variable declared in the component body is created fresh on every render. So the start function and the stop function are looking at different variables, and the stop cannot see what the start created. Ref is the same object across all of those renders. So the handle written by one function is visible to the other. This is also why the stopwatch in the last playground can have separate start, stop, and reset buttons that all agree with each other. Scrolling is DOM access again with a different method on the end. Hold a ref on the target element and call scroll into view when you want to go there. Worth saying out loud that this is a legitimate use of reaching into the DOM. React's model is that you describe what the UI should look like and it makes that true, but scroll, position, focus, and text selection are not things you describe, they are things you command. Those are exactly the cases where a ref is the right tool rather than an escape hatch. The table on screen is the decision, and it comes down to a single line. Does the screen need to change when this value changes? useState says yes and pays for that with a re-render and an update that you observe on the next render rather than immediately. useRef says no and gives you a value that changes the instant you assign it. That immediacy is worth noticing. Set state and read it on the very next line and you get the old value because the current render's variables never change. Assign to a ref and read it on the next line and you get the new one. Two different tools, and the difference is not convenience, it is whether React is involved at all. The list on screen is the honest summary of when to reach for it. DOM access for focus, scroll and measurement, timer and interval handles, previous values, and anything mutable that the UI does not depend on. There is one entry worth pushing back on gently, which is using refs to avoid re-renders. That is occasionally the right answer, and it is more often a sign that a value which does affect the UI has been hidden somewhere. React cannot see, so the screen goes stale and nobody can work out why. Reach for it deliberately, not as a performance habit. useRef gives you the same object on every render with one mutable property. Changing it schedules nothing. The ref attribute fills it with the DOM node after the commit, so it is null during the first render. Use it for DOM access, timer handles, previous values, and anything the screen does not depend on. And use state for everything the screen does depend on, because a value React cannot see is a value that cannot keep the UI honest. This variant is trying to count how many times the component has rendered using state, and it is an infinite loop. Read the effect. It has no dependency array, so it runs after every render, and what it does is set a piece of state. Setting state causes a render. That render runs the effect again, which sets state again. Nothing here is subtly wrong. It is the loop written out in 4 lines, and it is the shape of a genuine bug that people hit while trying to debug renders. The deeper mistake is the choice underneath. A render count is not something the UI depends on, it is something you want to watch. Putting it in state means every observation changes the thing being observed. The same counter in a ref. It increments, it persists, the number goes up as you type, and there is no loop because assigning to current tells React nothing. One caveat that this variant is a good excuse to state since the code does it. Writing to a ref during render is something React's own documentation tells you to avoid, and rendering is supposed to be a pure calculation. For a counter that exists to be looked at, it is a well-known and harmless exception, and you will see it in a lot of code. 2 things to be aware of if you use it. In development, strict mode renders twice, so the number will be double what you expect. And if you ever need that value to be correct rather than indicative, do the increment in an effect instead. The last variant puts both halves together. The top part holds a ref on an input and focuses it from a button, which is the DOM case. React committed the element set current to the node, and the handler calls focus on it. The bottom part is a stopwatch, and it is the mutable value case done properly. The elapsed time is state because the screen shows it and has to update. The interval handle is a ref because the screen does not show it and nothing should re-render when it changes. Start writes the handle into the ref, stop reads it back out and clears it. Reset does both and zeros the state. Read those three functions together and the division becomes obvious. What is displayed is state, what is bookkeeping is a ref. The model to keep is a box that React is not watching. It is the same object on every render, so it remembers. Changing it schedules nothing, so it is silent. That makes it right for DOM nodes, timer handles, previous values, and private bookkeeping, and wrong for anything the screen depends on. When you are unsure which one you need, ask whether a change to this value should be visible. If it should, React has to know, and that means state. The kata is the part that matters. Open the lesson, write the code yourself, then read back what you wrote and judge it. The link is in the description, and that practice is what keeps the skill yours. Kata is something you practice, not something you watch. Read the lesson, write the code yourself, then review what you wrote. This video is the reference you come back to afterwards. A model can produce this code in seconds, and the reason to write it by hand is to keep the judgment that tells you whether the code is any good. A custom hook is a function. That is the entire mechanism, and it is worth saying first because people expect there to be more. There is no registration step, no special export, nothing React has to be told about. If a function's name begins with use and it calls other hooks, it is a custom hook, and the only thing that makes the name matter is a lint rule. What you get for that is the ability to move stateful logic out of a component and into something you can name, test, and reuse, and this lesson builds 5 of them. The rules are short. The name starts with use because the linter uses that prefix to decide where the rules of hooks apply. It can call other hooks, which ordinary functions cannot. And it runs as part of the component that called it, which is the part we're dwelling on. A custom hook is not a shared object and it does not create anything global. Every component that calls it gets its own state, its own effects, its own everything. 2 components using the same hook are as independent as 2 components using useState directly, because that is literally what is happening one level down. The first one wraps a piece of state that also persists. It reads the stored value once for the initial state and writes back whenever the value changes. Look at what it returns, a value and a setter, the same shape as useState. That is the convention worth copying. A hook that returns the same shape as the built-in it wraps can be dropped into a component with almost no thought. One detail hiding in this example, reading from storage in the initializer rather than in an effect means the first render already has the stored value, so nothing flashes the default before correcting itself. This one subscribes to something outside React and hands back the current value. Set state to the size on mount, add a resize listener, remove it in the cleanup. Every component calling it gets the size and re-renders when the window changes. The interesting question is what happens with 10 components calling it, and the answer is 10 listeners because each call runs its own effect. That is fine at this scale, and it is exactly the kind of thing worth knowing before you use a hook like this in a list. The fix when you need it is one subscription in a context, which is a later lesson. Debounce is the one that shows why hooks compose. Take a value, return a copy of it that only catches up once the input has stopped changing for a while. Inside, it is the pattern from the cleanup lesson, an effect with a timeout, and a cleanup that clears it, so every change cancels the pending update and starts a new one. The whole hook is about 6 lines. Then a search box uses it by calling it on the input value and putting the result in the dependency array of the fetch, and the debouncing disappears from the component entirely. The smallest hook here, and a good example of when to stop, it holds a boolean and returns it with a function that flips it. That is all. It earns its place because the alternative appears in every component that has a modal or a panel, and because the flip function is stable and named rather than an inline arrow that inverts the value. Do not overextend this one. The moment a toggle needs 3 states, it is not a toggle anymore, and forcing it through a hook called useToggle is worse than the 2 lines it replaced. The previous value trick from the useRef lesson wrapped up ref, an effect that writes the current value into it after the render, and a return of what the ref held, which is to say the hook returns the value from the previous render because the write happens after everyone has read it. It is 4 lines, and it is genuinely hard to get right from memory, which is the best possible argument for extracting something into a hook, not because it is long but because it is subtle and you want to reason about it once. The list on screen is sound, and there are 2 entries worth waiting. Start the name with use always, because that is what tells the linter to check the rules of hooks inside it, and a hook that skips the prefix loses that checking silently. And extract logic used in more than one place. That second one is a limit as much as a permission. A hook pulled out of a single component used once tends to move the code away from where it is read without making it reusable, and now the state lives in one file and the markup that depends on it lives in another. Custom hooks are ordinary functions that call hooks. The prefix is what makes lint work. Each call gets its own independent state, so sharing a hook shares the logic, never the data. Return the same shape as the built-in you are wrapping when you can, and extract when the logic is repeated or when it is subtle enough to be worth reasoning about once and never again. 2 components, and both of them do the same 3 things. Read a value from local storage for their initial state, keep it in state, and write it back whenever it changes. The logic is not complicated, but it is duplicated exactly, including the JSON parse and the try around it. This is the state a codebase reaches naturally, and the cost is not the extra lines. It is that a bug in the parsing is now a bug in 2 places, and the third component that needs this will be written by copying one of these 2. The same 2 components with the shared part lifted into one hook. Each component is now one line of hook call plus its own markup, and the storage logic exists once. The thing to look at is the independence. Both components call the same hook with different keys, and neither can see the other's value. Nothing is shared except the code. That is the property that makes custom hooks safe to use everywhere, and it is the one people are least sure about when they start. The last variant is a small library of them in one file, so you can read them against each other. A toggle, a previous value, a window size, a debounce. Read them in order and notice how little there is to each one and how different their internals are. One holds state, one holds a ref, one subscribes to the window, one runs a timer with a cleanup. What they share is not their implementation, it is their shape. A function whose name begins with use that calls hooks and that returns something useful. Once that shape is familiar, the question stops being how to write a custom hook and becomes which piece of your component deserves to be one. The model to keep is that there is no such thing as a custom hook, only functions that are allowed to call hooks. That is why each call gets its own state, why they compose without any special machinery, and why the whole feature has almost no API surface to learn. When a piece of logic is repeated or subtle or has an obvious name, give it one and move it out. When it is none of those, leave it where it is. The kata is the part that matters. Open the lesson, write the code yourself, then read back what you wrote and judge it. The link is in the description, and that practice is what keeps the skill yours. Kata is something you practice, not something you watch. Read the lesson, write the code yourself, then review what you wrote. This video is the reference you come back to afterwards. A model can produce this code in seconds, and the reason to write it by hand is to keep the judgment that tells you whether the code is any good. useReducer is usually introduced as the hook for complex state, which is true and not very useful because nobody knows where complex begins. Here is a sharper version. Reach for it when the interesting thing about your state is not the values but the transitions. When what matters is that submitting moves you from editing to sending, and that failing moves you from sending back to editing with an error attached. Use state scatters those transitions across every handler that performs one. A reducer puts all of them in a single function you can read top to bottom. 2 arguments in, 2 values out. You pass a reducer function and an initial state, and you get back the current state and a dispatch function. The reducer takes the current state and an action and returns the next state. That is the whole contract, and the important word in it is returns. A reducer does not modify anything and it does not perform any work. Given the same state and the same action, it produces the same result every time, which means you can call it in a test with no React anywhere in sight. Dispatch is the other half. You do not tell React what the new state is, you tell it what happened and the reducer decides what that means. A counter is too small to need a reducer, and that is exactly why it is a good first example. Nothing is hidden. 3 actions, increment, decrement, and reset, and a switch statement that handles each one. Compare that with the useState version. The rule for incrementing lives in the reducer here next to the rules for the other 2 instead of inside the button that happens to do it. That relocation is the whole trade, and at this size it costs more than it earns. Look at the shape, not the value. A form is where it starts to pay. Several fields, a submitting flag, an error, and rules connecting them. Submitting clears the error. A successful submit resets the fields. A failure keeps them. With separate pieces of state, those rules end up spread over 3 or 4 handlers, and any handler that forgets one leaves the form in a state that should not exist, like submitting and showing a stale error at once. The reducer version makes each transition a single case, and the states that should not exist become states you simply never return. The to-do list shows the other reason to reach for this, arrays. Add, remove, and toggle are 3 operations on a collection, and each of them is a small piece of immutable update code, spreading and filtering and mapping. Inside a reducer, those sit together and read like a list of the things this data supports. Notice that every case returns a new array rather than pushing into the existing one. That is not ceremony. React compares the value it was given against the previous one to decide whether to re-render, so mutating the array in place produces the same reference and the screen does not update. The comparison on screen is fair, and I would reduce it to 2 questions. Do updates to this state depend on other parts of the same state? And are there transitions worth naming? If both answers are no, use state is simpler and you should use it. Independent values that change on their own do not become clearer by being routed through a switch statement. The moment 2 pieces of state have to change together to stay correct, they were 1 piece of state all along, and a reducer is how you say so. Type the actions if you are using TypeScript, because a union of action types turns a typo into a compile error and gives you exhaustive checking on the switch. Keep the reducer pure, no fetching, no timers, no random numbers, no reading the clock. Those belong in the handler that dispatches or in an effect. And give actions names that describe what happened rather than what to set. Submit failed is a better action than set error, because the first one lets the reducer decide everything that failing implies. And the second has already made that decision at the call site, which is precisely the scattering you move to a reducer to avoid. A reducer is a pure function from state and action to the next state. Dispatch report what happened, the reducer decides what it means. It suits state whose parts move together and collections with several operations. It is testable without React, and it is not an upgrade from useState. It is a different tool, and using it for 2 independent booleans makes code worse rather than better. 4 separate pieces of state in one component, and every handler updates 2 or 3 of them. Read the submit handler and count the things it has to remember, set submitting, clear the error, and on the way back either reset the fields or set the error and leave them alone. That knowledge is not written down anywhere, it is spread across the handlers that happen to implement it. Add a fifth field or a second way to submit, and the same sequence has to be repeated correctly somewhere else. Nothing here is wrong yet. This is what the code looks like just before it becomes wrong. The same component with one reducer. The state is one object now, and every transition is a case with a name. Read the reducer on its own and it tells you what this form can do and what each event implies without any markup in the way. The component underneath got shorter, and more importantly, its handlers stopped making decisions. They dispatch what happened and stop there. One thing to notice is that the reducer never touches the network. Submitting is still done by the handler, which dispatches before and after. Keeping the function pure is what lets you read it as a description of the rules rather than a sequence of events. The last variant is the collection case at full size. Add, toggle, remove, clear, completed, each as its own case, each returning a new array. Read them together and you have the complete list of things that can happen to this data, which is a genuinely useful thing to be able to hand someone. Look also at what is not in the reducer: no identifiers generated from the clock, no sorting that depends on anything outside its arguments. Everything it needs arrives in the action. That is what makes it a function you can test with a table of inputs and expected outputs, and it is the practical benefit that survives long after the readability argument stops being interesting. The model to keep is that dispatch describes an event and the reducer owns the consequences. Once those are separate, the rules of your state live in one pure function that you can read, test, and change without touching a single component. Use it when the parts of your state move together or when the transitions have names worth writing down. And when they do not, use state is still the right answer, which is worth saying because this is a hook people adopt everywhere the moment they understand it. The kata is the part that matters. Open the lesson, write the code yourself, then read back what you wrote and judge it. The link is in the description, and that practice is what keeps the skill yours. Kata is something you practice, not something you watch. Read the lesson, write the code yourself, then review what you wrote. This video is the reference you come back to afterwards. A model can produce this code in seconds, and the reason to write it by hand is to keep the judgment that tells you whether the code is any good. Memoization is the most over-applied idea in React, and the advice around it has genuinely changed, so this lesson has two jobs. The first is to explain what the three tools actually do, because they are simpler than their reputation. The second is to be precise about what the React compiler changes, because the short version people repeat is not quite right, and believing it will leave you with slow code and no idea why. Let me correct the framing on screen before we go further, because this matters. The React compiler is not something React 19 turns on for you. It is a separate build time tool, a Babel plugin you install and enable yourself, and it rewrites your components during the build to insert the memoization you would otherwise write by hand. Upgrading to React 19 gets you none of that on its own. Two consequences follow. If your project has not opted in, every rule about manual memoization still applies exactly as it did before. And this lesson's own playground has not opted in, which I checked. So what you are watching is ordinary unmemoized React, and that is the honest baseline to reason from. useMemo caches the result of a calculation between renders. You give it a function and a dependency array, and on each render, it compares the dependencies, returning the previous result if nothing changed and running the function again if something did. Same comparison mechanism as useEffect, different purpose. What it is for is a calculation that is genuinely expensive, sorting or filtering something large, or a derived structure that costs real time to build. What it is not for is adding two numbers, and the reason is that useMemo is not free. It stores the value, stores the dependencies, and compares them on every render. For cheap work, the bookkeeping costs more than the calculation. Used callback is the same idea applied to a function rather than a value. Every render creates fresh function objects. So a callback defined in a component is a different object each time, even though the code is identical. Usually nobody cares. It matters when that function is passed to a child wrapped in React.memo because the child compares its props, and a new function every render means the comparison always fails and the child re-renders anyway. Use callback keeps the same function object across renders so the comparison can succeed. Notice the shape of that. Use callback on its own does nothing useful. It only pays off in combination with something downstream that is comparing. React.memo wraps a component and skips re-rendering it when its props are unchanged. The comparison is shallow, which is the detail that decides whether it works. Each prop is compared by identity, so a string or a number compares fine, and a freshly built object or array or function never does. That is why memo and use callback are usually discussed together, and why wrapping a component in memo while passing it an inline object achieves precisely nothing at a small cost. Worth adding what memo does not do. It does not stop a re-render caused by the component's own state or by a context it reads. It only stops the one caused by its parent rendering. The list on screen is good and the principle behind it is better. Every memoization has a cost that is paid on every render and a benefit that is only collected when the thing it protects would have been expensive. Cheap calculations, components that render rarely, values that change every time anyway. In all of those, the cost is the only part you get. There is a second cost that is harder to see and worse in practice. Memoized code has dependency arrays and dependency arrays go stale. A bug where a callback closes over an old value is much harder to find than a component that renders more often than it strictly needed to. The advice on screen is right, and it is worth being clear that it is the same advice as before the compiler existed, only stated more confidently. Start with none of it. Write the straightforward version and use it. If something feels slow, measure it with the profiler and find out which component is re-rendering and how long it takes. Then memoize the specific thing the measurement pointed at and check that the number moved. If your project does enable the compiler that changes the default rather than the method, the compiler handles the routine cases at build time, and you are left doing this deliberately for the ones it cannot see, which is a smaller list but not an empty one. Use memo caches a value, use callback caches a function, React memo skips a re-render when props compare equal, and all three use a shallow comparison you should be able to picture. None of them is free. The compiler is an opt-in build tool, not a React 19 feature, so check whether your project actually has it before assuming anything. And the order of operations never changes. Write it simply, measure, then memoize what the measurement identified. The playground here is a single file, so read it as one worked example rather than a before and after. It builds an expensive calculation, wraps it in use memo, and passes a callback down to a child that is wrapped in memo. Follow the three pieces and how they connect. The memo on the child is what creates the need for the use callback, because without the memo, nothing is comparing props and a fresh function. Every render costs nothing. The use memo protects the calculation, and its dependency array is the list of things that make the previous answer invalid. Try the experiment the file invites, take the use callback off, and watch the memoized child start re-rendering again because its function prop is a new object every time. That is the clearest demonstration there is that these tools work as a set, and that any one of them alone is often just overhead. The model to keep has two parts. Memoization is caching, so it trades memory and a comparison for work you would otherwise repeat, and it only wins when that work is real. And the tools compose memo does the comparing, use callback and use memo make the comparison capable of succeeding. Before reaching for any of it, measure. After reaching for it, measure again, because the most common outcome of memoizing by instinct is code that is harder to read and exactly as fast. The kata is the part that matters. Open the lesson, write the code yourself, then read back what you wrote and judge it. The link is in the description, and that practice is what keeps the skill yours. Kata is something you practice, not something you watch. Read the lesson, write the code yourself, then review what you wrote. This video is the reference you come back to afterwards. A model can produce this code in seconds, and the reason to write it by hand is to keep the judgment that tells you whether the code is any good. Every application ends up with the same handful of browser behaviors. Close this when someone clicks outside it. Do something different on a narrow screen. Open the search box on a keyboard shortcut. Written inline, each of those is a ref, a listener, an effect, and a cleanup tangled into a component that was supposed to be about something else. This lesson is about pulling that class of thing out into hooks and about the specific details that make each one correct, because all three of the examples here have a detail that is easy to get wrong and hard to notice. The term is not a React concept, it is a useful label. A behavioral hook is a custom hook whose job is an interaction with the browser rather than a piece of your application's data. The list on screen is the usual set: clicking outside media queries, keyboard shortcuts, trapping focus, observing intersection. What they have in common is a shape. Each one attaches something to a global object, watches it, keeps a small piece of state, and tears the whole thing down on the way out. Once you have written two of them, the third is mostly filling in the middle. Take a ref and a callback, and call the callback when a click lands anywhere that is not inside that element. The implementation is a pointer down listener on the document and a check on each event asking whether the ref's node contains the event target. Two things about that check are worth stating. Contains is a DOM method, and it returns true for the element itself as well as its descendants, which is what you want. And the ref might be null on the first render or after unmount, so the check has to survive that. The drop-down on screen is the case everybody needs, and the notes underneath it are the detail that makes it work. Listen for pointer down rather than click. A click event only fires after the button is released, and by that point focus has already moved, so a drop-down that closes on click can flicker or lose a selection that was made on the way down. Pointer down fires first and behaves predictably. It is also the one event that covers a mouse, a finger, and a stylus, which is why it is the modern choice over mouse down. The other note matters just as much. The handler you pass in should be stable. Pass a fresh arrow function on every render, and the effects dependencies change every render, so the listener is removed and re-added constantly. Wrap it in use callback or accept that the hook is doing far more work than it looks like. This one subscribes to a media query and returns whether it currently matches. Match media gives you an object with a matches property and its own change event, so the hook reads the value once, then listens for changes and updates state. It is a small hook, and the interesting part is the cleanup, which removes the listener, and the initial read, which has to happen before the first paint or the component renders the wrong branch and then corrects itself visibly. The panel on screen is worth more than the hook because it answers a question people get wrong constantly. Use CSS media queries for showing and hiding, for layout, for spacing, for font sizes. Use this hook when the decision changes what React renders. A different component tree, different behavior, a different data request. The difference is not stylistic. CSS costs nothing and applies before your JavaScript has run. A hook costs a subscription, a piece of state, and a re-render on every change. Reaching for it to hide a sidebar is paying for a mechanism you did not need. Listen for a key combination and run something when it fires. The implementation checks the modifier flags on the event alongside the key itself, and the important line is the one that prevents the default. Take Control K or Command K, which is what most applications use for search. The browser has its own meaning for several of those combinations, and without preventing the default, you get both yours and the browser's. Worth noting the platform detail too. Control on Windows and Linux is Command on a Mac, so the check has to look at both, and users on either platform will assume theirs is the one that works. Press the combination and the panel opens. What is worth looking at is how little the component knows. It calls the hook with a combination and a function, and the entire business of attaching a listener, comparing modifiers, cancelling the browser's default, and cleaning up afterwards has gone somewhere else. That is the return you get for extracting a behavior rather than a value. The component stops containing any browser code at all. The section on screen makes a claim that is worth understanding rather than accepting. These compose without conflicting. The reason is that each hook owns its own effect and its own cleanup, and effects are independent of one another. A component can use all three at once, and each will attach and detach on its own schedule. That is not a special property of behavioral hooks. It is the property of hooks in general, and this is simply where it becomes obviously useful. The practical version, one hook per behavior, and a component that needs three behaviors calls three hooks. The list on screen is good, and two entries deserve emphasis. Accept a ref as a parameter rather than creating one inside the hook, because the component usually needs that ref for its own markup, and a hook that hides it forces an awkward dance to get it back. And stabilize the callbacks you pass in for the reason we covered with the dropdown. An unstable callback resubscribes on every render, which is invisible until you look at what the effect is actually doing. The server-side note is real too. Match media and document do not exist during server rendering, so a hook that touches them without checking will throw the moment the page is rendered on a server. A behavioral hook wraps a browser interaction, not a piece of data. They all have the same shape: subscribe, keep a little state, cleanup, pointer down beats click for outside click detection, and covers touch and pen as well. Prefer CSS to a media query hook unless the decision changes what renders. Prevent the default when you claim a keyboard combination, and check both control and command. Stabilize the callbacks and keep each hook to one behavior, because that is what lets them compose. A drop-down with the behavior written in line, a ref, an effect, a listener on the document, a check against the ref, a cleanup, and somewhere in the middle of all that, the actual drop-down. Read it and try to find the part that is about this feature rather than about the browser. It is a handful of lines surrounded by plumbing. Now imagine the second component that needs the same thing, and the third, each with its own copy of the listener and its own opportunity to forget the cleanup or use click instead of pointer down. The same component with the behavior extracted. The hook takes the ref and a callback. The component keeps the ref because it needs it for the markup anyway and calls the hook with it. What is left in the component is the dropdown and nothing else. Look at the hook itself as well, because it is where the correctness now lives in one place: the pointer down listener, the contains check, the null guard on the ref, and the cleanup. Fix a bug there and every dropdown in the application is fixed with it, which is the argument for extraction stated in its most practical form. The last variant runs all three hooks in one component, which is the composition claim made concrete. The dropdown closes on an outside click, the layout responds to a media query, and a keyboard combination toggles the search panel. Read the top of the component and count the hook calls: 3 lines, 3 behaviors, and no browser code anywhere in the body. Then look at what each hook is doing underneath and notice that all 3 end with a cleanup. 3 subscriptions to 3 different global things, each undone by the hook that made it. That is the shape worth taking away more than any of the individual implementations. The model to keep is a division of labor. Browser interactions have a common shape: subscribe, hold a little state, tear it down, and that shape belongs in a hook where it can be got right once. Your component keeps the part that is about your application. When you next find yourself writing a listener inside a component, ask whether it is really about this component or about the browser, and if it is the browser, give it a name beginning with use and move it out. The kata is the part that matters. Open the lesson, write the code yourself, then read back what you wrote and judge it. The link is in the description, and that practice is what keeps the skill yours. Kata is something you practice, not something you watch. Read the lesson, write the code yourself, then review what you wrote. This video is the reference you come back to afterwards. A model can produce this code in seconds, and the reason to write it by hand is to keep the judgment that tells you whether the code is any good. This is the lesson that makes the rest of the performance section make sense, and it answers a question most people carry a wrong answer to for years. When does React actually re-render, and what does it do when it does? The short version is that rendering and updating the DOM are two different steps, and almost every confusing React behavior lives in the gap between them. By the end of this, you should be able to predict which components run, which DOM nodes change, and why a list sometimes puts the wrong text in the wrong box. 3 triggers, and it is worth learning them as a closed list because the list is short and the wrong mental models are all longer. A component re-renders when its own state changes, when its parent re-renders, or when a context it reads changes. That is all. Notice what is not on the list. Props changing is not a trigger. It cannot be, because the only way a component receives new props is for its parent to render, and the parent rendering is already the second item. This sounds like a technicality, and it is the difference between understanding the model and guessing at it. Calling a state setter marks that component as needing to render, and React then renders it and everything below it. That second half surprises people. Changing state in one component does not surgically update one node. It reruns that component's function and the functions of all its descendants unless something stops the descent. Rendering a component is calling a function that returns a description, so this is cheaper than it sounds, and it is also why an unnecessary render high in the tree costs more than one at a leaf. When a parent renders, its children render, whether or not anything they receive has changed. This is the trigger behind most of the surprise re-renders people go hunting for. The default is that a subtree re-renders together, and stopping it takes something deliberate, which is what React.memo is for, and why the memoization lesson said memo is the tool that does the comparing. Until you place a memo somewhere, the whole subtree runs every time. Here is the part that matters most. Rendering does not touch the DOM. What it produces is a tree of plain objects describing what the UI should be. React then compares that tree with the previous one and works out the smallest set of real DOM operations to make the page match. That comparison is reconciliation. The reason this matters is that a component re-rendering is not the same as anything changing on screen. A component can render 10 times and produce an identical description 10 times, and the DOM is touched 0 times. So too many renders is a claim about your JavaScript, not about the page, and that is why measuring beats guessing. The comparison has one rule that explains a whole class of bugs. When React compares an element with the one that was in the same position before, it looks at the type first. Same type, see, it keeps the existing DOM node and the component state and just updates whatever props differ. Different type, it throws away the entire subtree, unmounts everything in it, and builds the new one from scratch. Watch the demo swap one element for another and see the state disappear. Nothing is preserved across a type change because as far as React is concerned, that is not the same thing in a new form, it is a different thing. Position works for comparing a single element against its predecessor, but it falls apart for lists because the item at index 2 this time may not be the item that was at index 2 last time. The key is how you tell React which element corresponds to which. Give it a stable identity from your data, an ID, and React can match them up correctly no matter how the list is reordered. The key is not a label and it is not for you. It is React's only way to answer the question, is this the same item I had before? Using the array index as a key means telling React that identity is position, which is exactly the thing that changes when a list changes. Insert an item at the front, and every item after it gets a new key. So React believes every one of them became a different item, when in fact they all just moved. The result is not usually a crash. Here it is state attached to the wrong row, a checkbox that follows the position instead of the item, or text in an input that jumps to a different entry. That is why the bug is so hard to spot. The list looks right and only the state is wrong. Index is safe in exactly one case, which is a list that never reorders, never inserts except at the end, and never removes. Since a changed key makes React discard the old component and mount a new one, you can use that on purpose. Put the user's ID as the key on a profile form, and switching users gives you a genuinely fresh form rather than one holding the previous user's half-type values. This is the cleanest way to reset a component state that exists, and it is worth preferring to an effect that watches a prop and clears the state, which is the version people usually write and which has a window where the old state is still on screen. The counter here uses a ref to count renders, which is the technique from the useRef lesson, and it is the honest way to find out what is happening rather than reasoning about it. Two things to keep in mind while reading the numbers. In development, strict mode renders twice deliberately, so expect doubles. And render counter tells you a component ran, not that the DOM changed, which is the distinction this whole lesson turns on. For real work, the profiler in the React developer tools gives you the same information with timings attached. 3 triggers own state, parent render, context change. Props are not 1 because props only change when the parent renders. Rendering builds a description. Reconciliation compares it to the last one and touches the DOM as little as it can. Same type keeps the node and its state, different type throws the subtree away. Keys give list items identity, index as a key gives them position instead, and a deliberate key change is the best state reset there is. The playground is one file with several demos, so read it as a set of experiments rather than a program. There is a parent with a counter that re-renders children which receive nothing at all, which is the second trigger in isolation. There is a type swap that destroys state. There is a list you can reorder, once keyed by index and once by ID, and it is worth actually doing the reorder and watching where the input text ends up, because reading about that bug and seeing it are different experiences. And there are render counters throughout. Change something and predict the numbers before you look at them. The places where your prediction is wrong are the parts of the model worth revisiting. The model to keep is 2 steps, not 1. React runs your component functions to build a description of the UI, then compares that description with the previous one and makes the smallest possible change to the page. Renders are cheap and frequent, DOM updates are neither, and React works hard to keep them minimal. Everything else follows. Type changes throw subtrees away because a different type is a different thing. Keys exist because position is not identity. And before you optimize a render, you can see in a counter, check whether it is costing anything at all. The kata is the part that matters. Open the lesson, write the code yourself, then read back what you wrote and judge it. The link is in the description, and that practice is what keeps the skill yours. Kata is something you practice, not something you watch. Read the lesson, write the code yourself, then review what you wrote. This video is the reference you come back to afterwards. A model can produce this code in seconds, and the reason to write it by hand is to keep the judgment that tells you whether the code is any good. The previous lesson established that when a parent renders, its children render with it. This one is about the way out of that, and it is not memoization. It is where you put things. By moving one piece of state down or by passing content in as a prop instead of writing it inline, you can stop re-render from reaching a subtree at all with no comparison function and nothing to remember. The reason it works is a single fact about element identity, and once you have it, the 4 patterns here stop being tricks and become obvious. Here is the situation, and it is extremely common. A component holds a piece of state that only a small part of it cares about, an input value, a toggle, a hover flag. Below it sits something expensive, a long list, a chart, a table. The state changes on every keystroke, the component re-renders, and the expensive thing re-renders too, because it is a child and that is what children do. Nothing is wrong with the code. The structure is wrong, and no amount of tuning the expensive component fixes a structure that reruns it for a reason unrelated to it. This is the important one, so let me give you the mechanism rather than the recipe. Move the state into a small wrapper component and pass the expensive part into it as children. Now when the wrapper state changes and the wrapper re-renders, look at where the children element actually came from. It was created by the component above during that component's render, and that component did not re-render. So the wrapper receives the exact same element object it had before. React compares them, sees the identical reference, and skips the whole subtree. The children did not render because there was nothing new to render. That is not React being clever about children, it is ordinary reconciliation acting on an element that was never rebuilt. The children prop is one slot. When you need several, pass them as separate props, a header, a sidebar, a footer, each receiving an element. The mechanism is identical because children was never special. It is just the prop that JSX fills in from what sits between the tags. Any prop holding an element gets the same treatment. This also tends to produce a better component because the slots are named in the signature and you can see at a glance what this layout is composed of. The cheapest version of all of this is not to lift the state in the first place. Keep each piece of state in the smallest component that needs it. A search box that owns its own input value re-renders only itself. The habit that causes the problem is lifting state up by default out of a vague sense that higher is more flexible. Lift it when two components genuinely need to share it, which is the rule from the state lesson, and leave it where it is otherwise. Most performance problems of this shape were created by a decision, not by React. The inverse move for when the state genuinely belongs where it is. Take the part that changes and pull it into its own component so the state moves down with it. Now the frequent re-render happens inside a small component and the rest of the tree is untouched. Between collocation and extraction, you can usually get any subtree to stop re-rendering purely by changing which component owns what. The comparison on screen is right, and it is worth saying why in mechanical terms. Memoization adds a comparison on every render and only pays when that comparison succeeds, and it succeeds only if every prop is stable, which usually means more memoization upstream. Composition removes the render instead of comparing it, costs nothing at runtime, and cannot go stale. One correction to the framing, the same one as the memoization lesson. The React compiler is a separate opt-in build tool, not something React 19 switches on, and this project does not have it installed. That does not weaken the argument here. It strengthens it because composition works identically with or without a compiler, and it is the one optimization you never have to ask that question about. When a parent renders, its children render, unless the element was created somewhere that did not re-render. Passing content in as children or as a slot prop is what makes that true. Keep state in the smallest component that needs it and extract the part that changes when it must live where it is. Reach for composition before memo because it removes the work rather than measuring whether the work is needed. The parent holds an input state and renders an expensive list inline in its own markup. Type in the box and watch the list's render counter climb with every keystroke. The list receives nothing that changes and does not care about the input at all, and it re-renders anyway because its element is being rebuilt by the parent's render every single time. This is the shape of the problem, and it is worth noticing how reasonable the code looks. There is no mistake in it, only a structure that ties two unrelated things together. The same two things rearranged. The state moves into a small wrapper, and the expensive list is passed into it as children from the component above. Type now and the counter does not move. The wrapper re-renders on every keystroke exactly as before, and the list does not because its element object was created one level up in a component that did not render. Same components, same state, same number of keystrokes, and the expensive work has simply stopped happening. No memo, no use callback, no dependency array to keep correct. The last variant is the collocation and extraction argument at slightly larger scale. Several pieces of state, several regions, and the demo lets you see which parts re-render as each piece changes. Read it looking for ownership rather than for syntax, which component holds each piece of state and how far the consequences of changing it travel. Then try the thought experiment that makes the lesson stick. Move one piece of state up a level in your head and work out which additional components would start re-rendering. That is the whole cost model, and once you can run it in your head, you will place state correctly the first time far more often than not. The model to keep is that a re-render travels down the tree, and an element passed in as a prop was not built by that render, so the travel stops there. Everything in this lesson follows from that one sentence. Put state where it is used, pass expensive things in rather than building them inline, and reach for memoization only when the structure genuinely cannot be changed. Structure is free and it does not go stale. The kata is the part that matters. Open the lesson, write the code yourself, then read back what you wrote and judge it. The link is in the description, and that practice is what keeps the skill yours. Kata is something you practice, not something you watch. Read the lesson, write the code yourself, then review what you wrote. This video is the reference you come back to afterwards. A model can produce this code in seconds, and the reason to write it by hand is to keep the judgment that tells you whether the code is any good. React.memo is one line of code, and almost all of the difficulty with it is in a single word: shallow. It wraps a component and skips the re-render when the props are unchanged, and whether they count as unchanged is decided by a comparison you can write out in about 4 lines. Learn that comparison properly, and everything about memo becomes predictable, including the large category of cases where adding it changes nothing at all and you cannot see why. Wrap a component in memo and you get a new component that remembers the props it was last rendered with. When its parent renders, memo compares the new props with the old ones, and if they match, it reuses the previous result and does not call your function. That is the only thing it does, and it is worth being precise about the boundary. Memo intercepts the second of the 3 re-render triggers from the reconciliation lesson, the parent one. It does nothing about the component's own state changing and nothing about a context it reads changing. Those still re-render it, memo or not. The demo puts the same component on screen twice, memoized and not, with a render counter on each. Press the button that changes something unrelated, and one counter climbs while the other does not. It is a small thing to watch, and it is the clearest way to see that memo is doing exactly one job. Worth noticing that the memoized version still renders the first time, and still renders whenever the props it actually receives do change. It is not frozen, it is compared. Memo takes a second argument, a function that receives the previous props and the next ones, and returns whether they should be treated as equal. 2 things to know before using it. The return value is the opposite of what most people expect. Returning true means equal, so skip the render, which is the reverse of the comparator you would write for a sort. And a custom comparison is usually a sign that something upstream should be fixed instead, because the reason the default failed is nearly always an object or a function being rebuilt every render. Use it when the props genuinely need a deep comparison you understand and control, and treat it as a last resort rather than an op. The 2 lists on screen are the whole practical content of this lesson. Memo breaks the moment any prop is a value that is rebuilt every render, an object literal, an array literal, an inline arrow function, or a child element created inline. All of those are new objects on every render, so the shallow comparison fails and the component re-renders exactly as it would have without memo, plus the cost of comparing. Memo works when the props are primitives or values that keep their identity: strings, numbers, booleans, a callback wrapped in useCallback, an object held in a ref or produced by useMemo. That is why the memoization lesson said these tools work as a set. Here is the comparison itself, and it is short enough to hold in your head. React takes the two props objects, checks that they have the same set of keys, and then compares each value with object ES. Object.ts is strict equality with two small corrections around not a number and -0. So for a string or a number, it compares the value, and for anything that is an object, an array or a function, it compares the reference. Nothing goes one level deeper. An object with identical contents but a different identity is a changed prop, and that single fact explains every case where memo appeared to do nothing. Memo skips a re-render caused by the parent, and only that. The comparison is shallow, key by key, with object keys. Any prop rebuild during render defeats it, which is most objects, arrays, inline functions, and inline elements. The custom comparator returns true for equal and is usually assigned to fix something upstream. And measure before and after, because a memo that never succeeds is pure cost, and there is nothing on screen to tell you which kind you have. A parent with a counter and a child that receives props unrelated to it. Press the button and both render counters go up. Nothing here is broken. This is just the default, and the child re-renders because its parent did. Look at what the child is being passed, because that is the thing to keep in mind for the next variant. If any of those props is built fresh during the parent's render, then wrapping the child in memo will not help. And this is exactly the situation in which people conclude that memo does not work. The same pair with the child wrapped. Press the button and the child's counter stops moving because its props compare equal and memo reuses the previous result. Then try the experiment that teaches the real lesson. Pass the child an inline object or an inline arrow function as an extra prop, and watch the counter start climbing again while the memo is still there. Nothing was removed. The comparison simply stopped succeeding. Once you have seen that once, you will read a memoized component by looking at its call site rather than at its definition, which is where the answer always is. The model to keep is 4 lines of comparison. Same keys, then each value compared by identity, nothing deeper. Memo is worth reaching for when a component is genuinely expensive and its props are genuinely stable, and it is worth nothing at all when one of those is untrue. And because there is no visible difference between a memo that works and a memo that never succeeds, this is one of the few places in React where you really do have to measure rather than reason. The kata is the part that matters. Open the lesson, write the code yourself, then read back what you wrote and judge it. The link is in the description, and that practice is what keeps the skill yours. Kata is something you practice, not something you watch. Read the lesson, write the code yourself, then review what you wrote. This video is the reference you come back to afterwards. A model can produce this code in seconds, and the reason to write it by hand is to keep the judgment that tells you whether the code is any good. Everything in this section so far has been about work your application does while it is running. Code splitting is about the work that happens before any of that, the download. By default, a bundler packs your entire application into one file, and a visitor who lands on your login page waits for the settings screen, the admin panel, and the chart library they may never open. Splitting is how you stop doing that, and React gives you 2 pieces to do it with, one of which is doing considerably more than it looks like. The cost is paid at the worst possible moment. Before a first-time visitor sees anything useful, the browser has to fetch the bundle, parse it and execute it, And on a phone, on a slow connection, the parse and execute are not free either. Every root and every rarely opened dialog you ship in that first file is time spent before the page becomes interactive. Splitting moves that code into separate chunks that are fetched when they are actually needed, so the first load carries only what the first screen requires. React Lazy takes a function that returns a dynamic import and gives you back a component. That is the whole API, and the interesting part is not React's half of it. The dynamic import is a JavaScript language feature, and it is a signal to your bundler. Everything reachable from that module goes into a separate chunk rather than the main bundle. So the splitting is done at build time by the bundler, and React's contribution is knowing how to render a component that does not exist yet. When the component is first rendered, the import runs, the chunk is fetched over the network, and React renders it once the promise resolves. Press the button and the component appears, and the first time you do it, there is a pause while the chunk downloads. Open the network panel and do it again, and you will see the request, which is the thing worth seeing, a separate file fetched on demand that was not part of the initial load. Press it a second time and there is no pause and no request because the module is now in memory. That is also a small warning about testing this. On a fast local connection, the delay is invisible, which is why the loading state you write is so easy to get wrong. Roots are the natural place to split because a root is already a boundary. The user is either on that page or they are not, and they cannot be on two at once. Lazy load each root component, and the initial bundle carries the shell and the landing page with everything else arriving as the user navigates. This one change is usually the largest single improvement available, and it needs no architectural work because the boundaries already exist. A lazy component cannot render until its chunk arrives, so something has to be shown in the meantime, and that is what suspense is for. Wrap the lazy component in a suspense boundary with a fallback, and React shows the fallback while it waits. Where you put the boundary matters more than what you put in it. A boundary at the top of the application replaces the whole page with a spinner every time anything loads. A boundary close to the lazy component swaps out just that region and leaves the rest of the interface usable. And a fallback with a different size to the real content will make the page jump when it arrives, so match the shape, which is what a skeleton is for. Several lazy components can share one suspense boundary or have their own, and the choice is a design decision rather than a technical one. One shared boundary means they appear together, which is right when they form a single unit, and wrong when one is fast and one is slow, because the fast one waits. Separate boundaries mean each region resolves on its own schedule. The demo here lets you trigger them independently, which is the easiest way to feel the difference. The list on screen is a good summary of where to split: roots, modals, and dialogues, anything heavy that most users never open, and large third-party libraries such as a chart or an editor. The corresponding rule for where not to split matters just as much. A chunk costs a network request, so splitting something small makes the page slower rather than faster, and splitting something that is always needed immediately just delays it. And measure the result, because bundle size is one of the few things in this course that is genuinely easy to measure. Your bundler will tell you exactly what is in each chunk and how big it is. The dynamic import is what creates the chunk, and your bundler does that at build time. React.lazy renders a component that has not arrived, and suspense shows something while it has not. Split at roots first, then at heavy or rarely used components. Put the boundary near the thing that is loading, not at the root. Match the fallback to the shape of the content. And check the numbers afterwards, because this is the one optimization where the before and after are unambiguous. The playground is one file with several lazy components and a suspense boundary, so read it as an experiment rather than an application. Look first at the shape of the lazy call and notice that the import is inside a function, which is what makes it dynamic and what lets the bundler defer it. Then look at where the suspense boundary sits relative to the components it covers and try moving it in your head. What would the user see if it wrapped the entire page instead of one section? The fallback is deliberately visible here. longer than it would be in production, because that is the only way to look at a loading state properly on a fast connection. The model to keep is that splitting happens in the bundler and waiting happens in React. A dynamic import draws a line in your build. React or lazy and suspense are how the interface behaves, while the code on the far side of that line is on its way. Start with roots, keep boundaries close to what they cover, and remember that every chunk is a request, so the goal is fewer bytes at the start rather than as many chunks as possible. The kata is the part that matters. Open the lesson, write the code yourself, then read back what you wrote and judge it. The link is in the description, and that practice is what keeps the skill yours. Kata is something you practice, not something you watch. Read the lesson, write the code yourself, then review what you wrote. This video is the reference you come back to afterwards. A model can produce this code in seconds, and the reason to write it by hand is to keep the judgment that tells you whether the code is any good. Context was the third re-render trigger in the reconciliation lesson, and it is the one with the sharpest edge. A component that reads a context re-renders when that context value changes, and it does so regardless of memo, regardless of where it sits in the tree, and regardless of whether it uses the part that changed. This lesson is about the 3 ways to stop that from costing you, and the first one is not an optimization, it is a modeling decision that happens to be fast. Here is the mechanism stated exactly. When a provider's value prop changes, React re-renders every component that reads that context, not the subtree, the consumers, wherever they are. And the comparison React uses is as identity. So a value built inline in the provider's markup is a new object on every render of the provider, which means every consumer re-renders every time the provider does, even when nothing inside the object changed. Note what this does to memo. A memoized component that reads a context is not protected because context is a separate trigger from props. Memo compares props and the context did not come in through props. The best fix is to stop putting unrelated things in one value. A typical context holds some state and the functions that change it, and those two have completely different lifetimes. The state changes constantly, the functions never change at all. Put them in 2 contexts. Now a component that only dispatches actions reads the stable one and stops re-rendering entirely, while components that display the state read the other. This is worth doing even when performance is not a concern, because it makes the dependency honest. A component that says it reads the updated context is telling you it does not care about the value. When the value has to be an object, wrap it in useMemo so it keeps its identity between renders where nothing relevant changed. This is the fix people reach for first, and it is the weaker of the two because it protects only against the provider re-rendering for unrelated reasons. It does nothing about the case where the state genuinely changed, and that is the common case. Note also that memoizing the value only works if the things going into it are themselves stable. So the functions won't use callback, and you are now maintaining 2 dependency arrays. That is exactly the cascade the memoization lesson warned about. And it is why splitting is the better answer where you can take it. The third fix is the one from the composition lesson applied here. If an expensive subtree sits inside a provider but does not read the context, pass it in as children rather than writing it inside the provider component. Its element is then created outside, so when the provider re-renders, that element is unchanged and reconciliation skips it. This is the same mechanism as before, and it is worth noticing that it is the only one of the 3 that costs nothing at runtime and cannot go stale. The list on screen is sound. Split state from updaters. Memoize the value when it must be an object. Keep providers close to the components that need them rather than wrapping the whole application by habit, because a provider at the root means every consumer anywhere is coupled to it. And one addition worth making explicit, If you find yourself building elaborate machinery to stop context re-renders, that is usually the signal that this data wants a state library with selector support rather than more context surgery. Context is a way to pass a value down without threading it through props. It was never designed as a store, and the lesson on context selectors later in the course is about exactly this boundary. Context re-renders every consumer when the value's identity changes, and memo does not protect against it because context is not props. Split state and updaters into separate contexts, so components subscribe only to what they use. Memoize the value when it is an object, and remember that it needs stable contents to work. Pass expensive non-consuming subtrees in a children, and when the surgery gets complicated, reach for a tool designed for the job. One context holding state and its updater together with several consumers and render counters on each. Press anything and watch all of them move, including the component whose only job is to call an updater and which does not display the state at all. That component has no reason to re-render, and it re-renders anyway because it reads a context whose value is a single object that changed. Look at how the value is constructed in the provider because that is where the whole problem lives. One object, rebuilt, carrying two things with different rates of change. The same application with two contexts and two providers. The updater context value never changes, so the component that only dispatches now re-renders 0 times no matter what you press, while the display components still update as they should. Read the two providers and notice how little code the change required, and read the consumers to see the real benefit. Each one now names which of the two it reads, which is a piece of documentation you get for free. Try adding a third piece of state and deciding which context it belongs in. That question having an answer is the sign the model is right. The model to keep is that context is a subscription and the unit of subscription is the whole value. Everything follows. Split the value so subscriptions are narrow, keep its identity stable so it does not change when nothing did, and keep subtrees that do not subscribe out of the re-render path by passing them in. When those three stop being enough, the data has outgrown context, and that is a design signal rather than a performance problem. The kata is the part that matters. Open the lesson, write the code yourself, then read back what you wrote and judge it. The link is in the description, and that practice is what keeps the skill yours. Kata is something you practice, not something you watch. Read the lesson, write the code yourself, then review what you wrote. This video is the reference you come back to afterwards. A model can produce this code in seconds, and the reason to write it by hand is to keep the judgment that tells you whether the code is any good. Every lesson in this section has ended with the same instruction, measure. This one is about how. It is also the lesson that decides whether the rest of the section is useful to you, because an optimization applied without a measurement is a guess that makes the code harder to read, and there is no way to tell the two apart afterwards. The tools here are not complicated. What takes practice is reading what they tell you and knowing which numbers actually matter. The profiler is a tab in the React Developer Tools extension. You press record, interact with the page, press stop, and you get a chart of every component that rendered in that period, how long each took, and why it rendered. That last column is the one people miss, and it is the most useful thing in the panel. For each component, it will tell you whether it rendered because its props changed, its state changed, its parent rendered, or a context changed. Those are lesson 14's 3 triggers reported back to you per component per commit. When you cannot work out why something is re-rendering, this answers it directly rather than by inference. The list on screen gives useful thresholds, and the 16 millisecond one deserves explanation. A screen refreshing 60 times a second has about 16 milliseconds per frame for everything. So a render that takes longer than that cannot keep up, and the interface visibly stutters. That is the number to compare against rather than any absolute idea of slow. Beyond that, look for a component rendering far more often than the interaction warrants, and for a white bar high in the tree because everything below it rendered too. Do not chase a component that renders often but takes almost no time. Frequent and cheap is fine, and the profiler makes that obvious in a way that counting console logs does not. A log at the top of a component tells you it rendered, and that is genuinely useful for a quick question. Two cautions. In development, strict mode renders twice, so every count doubles, and that is not a bug. And a log tells you a component ran, not that anything changed on screen, which is the distinction from the reconciliation lesson. Use logs for a fast yes or no, and the profiler for anything involving how long or how often. This is a nice small hook, and it answers the specific question the profiler cannot: which prop changed? It keeps the previous props in a ref, compares them key by key on each render, and logs the ones whose values differ. Two things worth noting. The comparison is the same shallow identity check that React.memo uses, so what this hook reports is exactly what Memo would have seen, which makes it the fastest way to find out why a memo is not working. And you would not ship it, so gate it behind a development check or strip it before it goes out. The order on screen is the whole discipline, and it is worth stating as a sequence you actually follow. Profile first. Find the component that is slow or the one that renders too often. Work out which of the three triggers is causing it. Apply the fix that matches that cause, which is usually structural rather than a memo. Then profile again and confirm the number moved. That last step is the one people skip, and skipping it is how a code base accumulates memoization that has never once prevented a render. The list on screen is the set you have now met individually, objects and arrays created in render which defeat every comparison downstream. Inline functions pass to memoize children, state placed higher than it needs to be, so unrelated things re-rendered together, large lists rendered in full. Each of those has a lesson behind it in this section, and what the list gives you is a place to start looking when the profiler points at something and you need a hypothesis. The profiler tells you what rendered, how long it took, and which of the three triggers caused it. 16 milliseconds is the frame budget, and that is the threshold worth measuring against. Frequent and cheap is not a problem. Why did you update hook answers which prop changed using the same comparison memo uses. Measure, fix the cause rather than the symptom, and measure again. And if the second measurement does not move, take the optimization back out. The playground is a single file built to be profiled rather than read. It has components that render more than they need to, why did you update hook wired up, and enough work in the wrong places to show up in a recording. The useful exercise is not to read the code and find the problems. It is to open the profiler on it and let the tool find them, then check the code and see whether the tool was right. Do that once on a file where you already know the answer and the panel stops being intimidating, which is most of what stands between people and using it on their own applications. The model to keep is that performance work is a loop with a measurement at both ends. The profiler will tell you which component and which trigger, and the section you have just finished tells you which fix matches which trigger, and the second measurement tells you whether you were right. Without the first measurement, you are guessing about the problem, and without the second, you are guessing about the solution. Neither guess leaves any trace in the code for the next person to check. The kata is the part that matters. Open the lesson, write the code yourself, then read back what you wrote and judge it. The link is in the description, and that practice is what keeps the skill yours. Kata is something you practice, not something you watch. Read the lesson, write the code yourself, then review what you wrote. This video is the reference you come back to afterwards. A model can produce this code in seconds, and the reason to write it by hand is to keep the judgment that tells you whether the code is any good. Two lessons in this section have already had to correct a claim about the compiler, so let me put the accurate version up front and then we can look at what it actually does. The React compiler is a separate opt-in build tool. It is not switched on by upgrading React and it is not installed in this project, which I checked before recording. What it does when you do enable it is genuinely significant, and it changes the default advice about memoization rather than the reasoning behind it. It is a compiler in the ordinary sense. It reads your components at build time and rewrites them. What it inserts is memoization, the caching of values and the skipping of re-renders that you would otherwise write by hand with useMemo, useCallback, and memo. The important word is build time. There is no runtime analysis, nothing watching your components as they run, and no cost paid while the page is open beyond the caching itself. Your source stays clean and the output is the optimized version. It analyzes each component to work out which values depend on which and inserts caching where a value can be reused. To do that safely, it has to assume your components follow the rules of React. Rendering is a pure calculation, props and state are not mutated, and hooks are called unconditionally at the top level. Where it can prove those things, it optimizes. Where it cannot, it leaves the component alone rather than risking a wrong result. That is a design decision worth understanding. The compiler is conservative, and code that breaks the rules does not get miscompiled, it simply gets skipped, which is also why the lint rules matter more once you adopt it. With the compiler enabled, most manual memoization becomes redundant. The use memo you would have written around a derived value, the use callback around a handler passed to a memoized child, and a good deal of the memo wrapping itself. The gain is not only speed, it is the removal of dependency arrays, which are the part that goes stale and produces bugs that are far harder to find than a slow render. Removing handwritten memoization is the compiler's most valuable effect, and it is the opposite of the direction people expect from a performance tool. The list on screen is the honest remainder. Work that is expensive in a way the compiler cannot see, such as a calculation whose cost depends on data rather than structure, values that must keep their identity for a reason outside React, like a dependency in an effect that talks to an external system, and components the compiler has skipped which you find by checking rather than assuming. This is a shorter list than the pre-compiler one, and the method from the profiling lesson is unchanged. Measure, find the cause, fix that. This section is the one to read carefully, and it is where the lesson gets it right. The compiler is opt-in and enabled in your build configuration. In practice, that means installing the Babel plugin and adding it to your bundler's React plugin options, plus the matching lint rule, so that code which would be skipped shows up as a warning rather than silently missing out. Check your own project before assuming any of this applies to it. The way to tell is to look for the plugin in your dependencies, which is exactly what I did for this one, and it is not there. The advice on screen is right, and it is worth noticing that it is the same advice as before, with more confidence behind it. Write the clear version. Do not memoize by reflex. Measure when something feels slow. What changes with the compiler is the default. Previously, the clean version was sometimes genuinely slower and you paid in readability to fix it, and now that trade is mostly gone. What does not change is that the compiler is not a substitute for a sound structure. It can cache a value, it cannot move your state to the component that should own it. The compiler is a build time opt-in tool, not a React 19 feature you get automatically. It inserts the memoization you would have written, and its biggest benefit is deleting dependency arrays rather than raw speed. It is conservative and skips code it cannot prove safe, which makes the rules of React and the lint rules more valuable rather than less. Manual optimization still applies to a short remainder, and structure is still yours to get right. The playground is one file showing components written the clean way without manual memoization, and the notes describe what the compiler would insert for each. Read it as a comparison between what you write and what runs. The useful exercise is to go through each component and predict which values the compiler could cache and which it could not, then check that against the nodes. The ones it cannot are almost always the same thing, something that reaches outside the component, or something whose dependencies cannot be determined by looking at the code. That is a good instinct to build, whether or not you ever turn the compiler on, because it is the same instinct that tells you which of your own memoization is doing anything. The model to keep is that the compiler moves memoization from your source to your build. It does the mechanical part, and it does it more consistently than a person will, which is exactly the kind of work a compiler should be doing. What it leaves you is the part that was always the interesting half, deciding where state lives, what each component owns, and whether the expensive thing needs to happen at all. Check whether your project has it enabled before you rely on any of it, because that answer is easy to assume and easy to check. The kata is the part that matters. Open the lesson, write the code yourself, then read back what you wrote and judge it. The link is in the description, and that practice is what keeps the skill yours. Kata is something you practice, not something you watch. Read the lesson, write the code yourself, then review what you wrote. This video is the reference you come back to afterwards. A model can produce this code in seconds, and the reason to write it by hand is to keep the judgment that tells you whether the code is any good. Everything else in this section has been about React doing less work. This one is about the browser doing less work, and it is the technique that survives when the others have run out. You can memoize a row component perfectly and still have a page that stalls, because the cost is not in your JavaScript at all. It is in the 10,000 DOM nodes you ask the browser to create, lay out, and keep in memory. Virtualization is how you stop asking. Browsers are fast, and they are not infinitely fast. Every element you render is memory held, style resolved, layout computed, and paint scheduled, and those costs are per node. So a list of 10,000 rows costs roughly 10,000 times a single row, and none of that is React's doing. This is worth being precise about because it changes which fix works. If the problem were React re-rendering rows, Memo would help. It is not. The rows are created once and then just sit there being expensive, and no amount of memoization removes a node that exists. Render only what fits on screen plus a small buffer and swap the contents as the user scrolls. About 20 nodes exist at any moment, whether the list has 100 items or 100,000, so the cost stops scaling with the data. Two mechanics make it look like an ordinary list. A spacer element with the full height keeps the scroll bar honest, so the thumb is the right size and the scroll distance is right. And the visible window is offset by however far down the list it belongs, so the rows land in the correct place rather than at the top. The user cannot tell from the outside, which is the whole trick. 5,000 rows all in the DOM, and the demo is honest about what that feels like. The initial paint stalls and scrolling is heavy. Look at the code and notice how reasonable it is. It maps over an array and renders a row for each with a key in a scrolling container. There is no mistake in it, and there is nothing to memoize. It is doing exactly what you asked, and what you asked for is expensive. Open the elements panel on this one and look at the node count, because that number is the thing this lesson is about. The same idea with 10,000 items and about 20 nodes, and the implementation is short enough to read completely. Follow the arithmetic. The scroll position goes into state on every scroll event. The start index is the scroll position divided by the item height, floored, which is only that simple because every row is the same known height. A buffer of 5 is subtracted and added at each end, so a fast scroll does not show blank space before the next batch arrives. Then the slice and an offset computed as the start index times the item height, applied as a transform on the group of visible rows. Around it sits a container whose height is the item count times the item height, which is the spacer that makes the scroll bar behave. That is the entire technique, and every virtualization library is a more careful version of these 6 lines of arithmetic. 3 costs worth stating out loud. It needs a known row height, and variable heights mean measuring rows and are considerably harder. Find-in page and screen readers only see what is rendered, so accessibility needs real thought. And scroll position in state means a render per scroll event, which is fine here and is the first thing to look at if a virtualized list ever feels sluggish. For production, use a maintained library rather than this. The reason to write it once is that a library's options stop being mysterious when you know which line each of them is adjusting. The model to keep is that the DOM is the budget. React can be perfectly efficient and the page still slow, because the cost was paid the moment those nodes existed. When a list is long enough for that to matter, the fix is not to render it faster, but to render less of it and to fake the rest with a spacer and an offset. Everything else in this section reduces work React does. This is the one that reduces work the browser does, which is why it is the one that still helps when the rest have stopped. The kata is the part that matters. Open the lesson, write the code yourself, then read back what you wrote and judge it. The link is in the description, and that practice is what keeps the skill yours. Kata is something you practice, not something you watch. Read the lesson, write the code yourself, then review what you wrote. This video is the reference you come back to afterwards. A model can produce this code in seconds, and the reason to write it by hand is to keep the judgment that tells you whether the code is any good. You have used compound components for years without the name. A select element and its options are one. The select owns which value is chosen, the options declare themselves, and you never pass an array of items into a select as a prop. That is the pattern. A parent that owns the state, a set of children that plug into it, and an API that is written as markup rather than configured as data. This lesson builds one and spends as much time on when not to as on how. The parts share state implicitly, and the mechanism is context. The parent creates a context holding whatever the group needs, which item is open, which tab is selected, and renders a provider around its children. Each child reads that context and behaves accordingly. Nothing is passed between them explicitly, which is exactly why the markup stays clean. Attaching the children to the parent as properties is a convention rather than a requirement. It groups them under one name and makes it obvious at the call site which parts belong together. 3 that matter. The API is expressive because the consumer arranges the parts in markup instead of describing an arrangement in props. The concerns separate because each part owns its own rendering and the parent owns only the shared state. And it is genuinely flexible. A consumer can put a wrapper around one part, reorder them, or render one conditionally without you having anticipated it. That last point is the real argument. A component configured by props can only do what its props allow. A component composed of parts can do things its author never thought of. The accordion on screen is the pattern working. The outer component holds which panel is open and provides it. Each item knows its own identifier, reads the context to decide whether it is the open one, and calls back into the context to change that. Look at what the consumer writes, markup that reads like a description of the accordion with no configuration object anywhere. Then look at what is not there. No array of panel definitions, no render prop for the header, no Boolean flags for behavior. This section is the honest one, and it is why this lesson is better than most treatment of the pattern. Every part you expose is API you now maintain and cannot change freely. The parts only work inside their parent, so you need a clear error when someone uses one outside it, or they get a confusing failure from a missing context. Types get harder. And the indirection is real. The state lives in a context. So following how a click becomes a change means jumping between 3 files instead of reading one component. For a widget with 2 configurations and no need for rearrangement, props are simpler, and simple is the point. Reach for this when consumers genuinely need to control the arrangement, and not because the markup looks more elegant in a blog post. The parts share state through context, which is what keeps the markup free of wiring. Attaching parts as properties of the parent is a naming convention, not a mechanism. The pattern buys arrangement flexibility which props cannot give you. It costs API surface indirection and type complexity. Guard against use outside the parent with a real error message. And check that the flexibility is wanted before paying for it. The version everyone writes first, and it is not a strawman. It is what happens when a component grows honestly. A list of items as a prop, then a flag for whether one can be open at a time, then something for the header, then a way to render a custom icon, then a callback for when it changes. Each of those was a reasonable response to a real request. Read the props together and notice what they have become: a small configuration language invented here that a consumer has to learn. Then ask what happens when someone wants a divider between 2 panels and see that the answer is another prop. The same accordion as parts. The parent holds the open state and provides it. The item, the header, and the panel read it. Compare the call sites rather than the implementations, because that is where the difference is. The compound version is markup a reader can follow without knowing anything about the component's props. And the divider question from a moment ago now has no answer required. You put a divider in because it is markup and you are arranging it yourself. Notice also that the implementation is not shorter. The complexity moved rather than vanished. Out of the consumer's configuration and into the component structure, which is a good trade when there are many consumers and a bad one when there is a single call site. The last variant splits the accordion into its own file, which is how you would actually ship it, and it is worth reading for the boundary rather than the behavior. The file exports the parent with the parts attached, and the context stays private inside it. Nothing outside can read that context or construct one of the parts in a way the parent did not intend. That encapsulation is the other half of the pattern. The parts appear to be independent components, and they are deliberately not, and the module boundary is what enforces it. Look for the check that fires when a part is rendered outside its parent, because that error message is the difference between a pattern that is pleasant to use and one that fails mysteriously. The model to keep is a parent that owns state and children that subscribe to it, presented as markup rather than configuration. It buys the consumer the ability to arrange the parts, which is the one thing props can never provide, and it costs you API surface, indirection, and a guard against misuse. Before reaching for it, ask whether anyone actually needs to rearrange anything. When the answer is yes, this is the right shape. When it is no, a component with 4 props is a better component. The kata is the part that matters. Open the lesson, write the code yourself, then read back what you wrote and judge it. The link is in the description, and that practice is what keeps the skill yours. Kata is something you practice, not something you watch. Read the lesson, write the code yourself, then review what you wrote. This video is the reference you come back to afterwards. A model can produce this code in seconds, and the reason to write it by hand is to keep the judgment that tells you whether the code is any good. Tabs are the canonical compound component, and the reason they are worth a whole lesson is that they contain a problem the accordion did not. The tab buttons and the tab panels are in different places on the screen, and they have to agree about which one is selected. That is the interesting constraint, and the solution to it is what people usually mean when they credit Ryan Florence with popularizing this pattern. On top of that sits the part most tutorials skip entirely: which is that a tab component with no keyboard support is not a tab component, and the specification for that is already written. The first version everyone writes takes an array of objects, each with a label and some content, and renders the buttons from one field and the panel from the other. It works immediately and it constrains you immediately. The label can only be a string until it needs an icon. The panel can only be what you put in the object. Putting a badge on one tab or a divider between two of them or having one tab disabled, each requires a new field in the object shape, and that shape is a small configuration language you are now inventing and documenting. Here is the move. Instead of one list producing both halves, you write two subtrees, a list of tabs and a set of panels. They sit in different parts of the markup and they stay in step because both read the same context. The root holds the active index and provides it, the tab list renders buttons that set it, and the panels render whichever one matches. Each half can now be arranged however the consumer wants, and neither knows anything about the other. Position is what pairs them, the third tab goes with the third panel, and that correspondence is established by order rather than by an identifier you have to invent. The build is 4 small pieces, and it is worth naming them because every compound component you write will have the same 4. A context holding the shared state. A root component that owns the state and renders the provider. The parts, each reading the context to decide how to render and what to do when clicked. And a hook that reads the context and throws a clear error if it comes back empty, which is what turns used outside the parent from a confusing crash into a sentence telling you what you did. This is the same duality as a native input, and it is worth copying deliberately. An uncontrolled component owns its own state and you give it an initial value. A controlled one has the state owned by you, passed in with the change handler. Supporting both is a small piece of code. The component keeps internal state and then uses the prop instead whenever the prop is not undefined. That single line is why a select element can be either, and building your components the same way means they compose with forms and with state you already hold, rather than fighting them. This is the section that separates a real tab component from a set of styled buttons, and the good news is that you do not have to design any of it because the specification exists. The roles come in a set, a container with role tab list, buttons with role tab, and panels with role tab panel. Each tab says whether it is selected and which panel it controls, and each panel says which tab labels it. Then the keyboard. Left and right arrows move between tabs, home and end jump to the first and last, and the implementation on screen wraps around at both ends. And the piece people miss entirely, only the active tab is reachable by tabbing, the others are removed from the tab order, so a keyboard user tabs once to reach the tab strip and then arrows within it. That is called a roving tab index, and without it, a 10-tab component costs 10 presses to tab past. The same honest section as the previous lesson, and it applies with more force here because this component is larger. You are exposing 4 or 5 parts, all of which are now public API. The state is in a context, so following a click to its effect means reading 3 definitions. And if the answer is genuinely a fixed set of 3 tabs that nobody will rearrange, the config-driven version at the top of this lesson is less code and easier to read. The pattern earns its cost when it is used in many places by people who need different arrangements, which is exactly why component libraries are built this way and why a single application screen usually should not be. Separated subtrees are the idea the tab list and the panels live in different places and agree through context paired by position. 4 pieces build it, context, root, parts, and a hook that errors clearly. Support controlled and uncontrolled the way native inputs do, with one line choosing between the prop and internal state. Implement the ARIA roles and the keyboard behavior because they are specified and a component without them is not accessible. And weigh the API surface against whether anyone needs the flexibility. The playground is 2 files and read them in the order they are given. The first is the consumer's view. Markup that arranges a tab list and some panels, which is what you are trying to make possible. The second is the component, and it is long, which is the honest picture of what a real compound component costs. Work through it looking for the 4 pieces named earlier, and then look specifically at the keyboard handler and the tab index, because that is the part you would have had to look up, and it is right there. The exercise worth doing afterwards is to add a 5th tab with an icon and a badge to the consumer file, and notice that you do not have to touch the component at all. That is the entire return on the pattern demonstrated in one edit. The model to keep is 2 subtrees kept in step by a shared context paired by position, with the state owned either by the component or by you. Everything else in this lesson is care rather than cleverness. A hook that fails with a useful message, a line that supports both control modes, and an accessibility specification that has already been written and only needs implementing. When you next reach for a tab component, that last part is the one to check first, because it is the part that will not be there. The kata is the part that matters. Open the lesson, write the code yourself, then read back what you wrote and judge it. The link is in the description, and that practice is what keeps the skill yours. Kata is something you practice, not something you watch. Read the lesson, write the code yourself, then review what you wrote. This video is the reference you come back to afterwards. A model can produce this code in seconds, and the reason to write it by hand is to keep the judgment that tells you whether the code is any good. Render props is the pattern hooks we're supposed to replace, and it is usually taught as history for that reason. That is a mistake, and this lesson is unusually good about why. There are 4 situations where a render prop is still the better answer, all of them cases where the component needs to own something the consumer cannot, and knowing them is what stops you reaching for a hook in the one place it does not fit. A render prop is a function passed to a component which the component calls to produce its output. The component owns some state or behavior, and instead of deciding what to display with it, it hands the value back to you and lets you decide. Nothing about it is a React feature. It is a function passed as a prop called during render, and everything else follows from that. The demo tracks the mouse and hands the coordinates to a function you supply. Notice the division. The component owns the listener, the state, and the cleanup, and knows nothing about what appears on screen. You own the markup and know nothing about how the position was obtained. That separation is the whole point, and it is the same separation a custom hook gives you, which is exactly why the comparison later in this lesson is worth taking seriously. A common variation passes the function as children rather than as a prop called render. It reads better at the call site because the function sits between the tags where markup normally goes, and it is the same mechanism. Children is just a prop, and a prop can hold a function. Worth knowing both forms exist since libraries differ, and the choice is entirely about how the call site reads. The toggle here hands back both a value and the function that changes it, which is the shape most render props end up with. Compare it mentally with use state, the same pair delivered differently. The component keeps the state, you receive it as arguments rather than as a return value. When the only difference between 2 patterns is where the parentheses go, that is the moment to ask what else differs, which is the next section. Here is the honest comparison. A custom hook returns values into your component, so you call it at the top and then write ordinary markup. A render prop wraps your markup in a function which nests, and 3 of them nested is genuinely unpleasant to read. That nesting is the thing hooks removed and the reason they won. For sharing logic, a hook is better on almost every axis. No wrapper component, no extra element in the tree, no indentation, and easier types. The card on screen puts it as UI composition, which is the right frame. A render prop is good when the shared thing is bound up with rendering, when the component decides what to render and how often, and only the appearance is yours. And this one has logic reuse, which is equally right. When the shared thing is a value or a behavior that your component then uses however it likes, a hook is simpler in every respect. Most of what people share between components is this kind, which is why hooks became the default. 4 cases follow, and they are the reason this lesson is worth watching rather than skimming. Each one has the same underlying shape. The component owns something the consumer cannot own, and a hook has no way to give it away. When the component attaches an observer to a real DOM node it owns that node's lifetime. A hook could return a ref for you to attach, which pushes the responsibility onto every consumer and gives every one of them a chance to forget. The render prop version keeps the node and the observer inside and hands out only what was measured. This is the strongest of the 4. A hook runs once per component, so a list of 1,000 rows each needing their own piece of state cannot be served by one hook call. You would need a component per row just to have somewhere to call it. A component that iterates and invokes your render prop once per item with that item's state does this naturally. Virtualized lists work exactly this way, and that is not a coincidence. A component can hold a socket, a subscription, or a connection and never hand it out, exposing only the derived values through the render prop. A hook returns its values into your scope, where you can keep them, pass them on, or misuse them when the encapsulation matters. When there is exactly one right way to use the resource, keeping it inside is a feature. When the parent has measured something and the children need that measurement to decide what to render, the parent has to be the one calling. A hook cannot do this because by the time your component runs, the measurement has not happened yet. This is why virtually every responsive layout and measurement library exposes a render prop or a children function. For pure logic, a debounce, a fetch, a piece of local storage, a media query, hooks win on every axis and it is not close. No wrapper, no nesting, no extra element, better types, and they compose by being called one after another rather than by wrapping each other. If what you are sharing is a value and not a rendering responsibility, write a hook. A render prop is a function passed to a component and called during render in either the render prop or children as function form. Hooks replaced it as the default for sharing logic. For good reasons, nesting is the cost that never goes away. It still wins in 4 cases, all of them where the component must own something, the DOM node's lifetime, iteration over many instances, an encapsulated resource, or a measurement the children depend on. Ask who has to own the thing, and the answer tells you which pattern to use. 2 components that both track the mouse, each with its own state, its own listener, and its own cleanup. The logic is identical in both and neither knows about the other. This is the same starting point as the custom hooks lesson, deliberately, because the interesting question is not how to remove the duplication. It is which of the 2 available answers to use, and at this size either would work. The tracking moves into one component that owns the listener and calls a function you pass with the current position. Both consumers become markup. Read it and notice the shape at the call site. Your markup now lives inside a function inside a component, indented one level further than before. With one of these, it is fine. Picture 3, one inside another, and you can see the whole argument for hooks in the indentation alone. The last variant is labeled data-driven, and what it actually shows is one tracker component serving 2 completely different interfaces. Same component, same state, 2 call sites, and the 2 render functions produce things that have nothing in common. One a panel of coordinates, the other a dot that follows the pointer. That is the separation stated as plainly as it can be. The component knows how to track a mouse and nothing about what a mouse position should look like, and each consumer decides that independently without the component changing. Try the exercise of adding a third usage that draws something else entirely and notice that the tracker is untouched. The model to keep is a question about ownership. If the consumer can own the thing, the state, the ref, the life cycle, then a hook hands it over and gets out of the way, and that is the better tool. If the component must own it because it manages a node, iterates over many instances, encapsulates a resource, or measures something the children depend on, then it has to be the one calling your code, and that is a render prop. Hooks are the default and render props are not obsolete. They are what you reach for when the calling has to happen from the inside. The kata is the part that matters. Open the lesson, write the code yourself, then read back what you wrote and judge it. The link is in the description, and that practice is what keeps the skill yours. Kata is something you practice, not something you watch. Read the lesson, write the code yourself, then review what you wrote. This video is the reference you come back to afterwards. A model can produce this code in seconds, and the reason to write it by hand is to keep the judgment that tells you whether the code is any good. A higher order component is a function that takes a component and gives you back a new one with something added. It is the oldest of the three sharing patterns in this section and the least used today, and I want to be straightforward about that rather than pretend otherwise. For most of what people used hooks for, a hook is now better. What is still worth an 8-minute lesson is that the pattern has not disappeared, it has narrowed, and the places it survives are informative about what wrapping can do that calling cannot. Take a component, return a new component that renders the original with extra props or extra behavior around it. The name comes straight from higher order functions, and the analogy is exact. A function that takes a function and returns a function applied to components. Notice what that gives you, which a hook does not. The HOC decides whether to render the wrapped component at all, and it can render something else instead because it sits between the parent and the component rather than inside it. The list on screen is the historical one: authentication, loading states, error boundaries, logging, injecting data. Read it and notice what most of those have in common. They are decisions about whether to render the component, made before it renders. That is the shape hooks are actually good at, and it is why authentication is the example everybody reaches for. A hook inside the component cannot decline to render the component it is inside. For sharing logic, hooks win for the same reasons they beat render props. No wrapper component, no extra layer in the tree, no name collisions between props and types that are far simpler. Hooks have specific costs worth naming. Props pass through invisibly, so reading a component tells you nothing about what its wrapper is injecting. Two HOCs can inject the same prop name, and the outer one silently wins. The display name in the developer tools becomes a nest of wrappers unless you set it deliberately. And refs do not pass through by default, so a wrapped component is not forwardable unless the HOC handles it. None of that applies to a hook, which is why hooks took over. If you are writing one, the list on screen is correct and worth following literally. Do not mutate the component you are given, return a new one. Pass unrelated props straight through with a spread, so the wrapper is transparent to everything it does not care about. Set the display name, because the alternative is a developer tools tree full of anonymous wrappers. Do not create the wrapped component inside render, because a new component type on every render unmounts and remounts the whole subtree. That is the reconciliation rule from lesson 14, and it is the most damaging mistake on this list. And compose them outside the component once rather than on each render. And hook is a function from component to component. It can decide not to render what it wraps, which is the one thing a hook genuinely cannot do, and that is why authentication and loading gates are where the pattern survives. Its costs are invisible props, name collisions, display names, and refs. For everything that is logic rather than gatekeeping, write a hook. And never build the wrapper during a render. Two components, each checking whether the user is signed in and each returning a sign-in prompt when they are not. The check is 4 lines and it is repeated verbatim. What makes this a good example is the failure mode it invites. The third component that needs protecting will be written by someone who forgets, and nothing about the code makes that omission visible. A missing loading spinner looks wrong immediately. A missing hours check looks completely normal. The check moves into a function that takes a component and returns a guarded one. Read what the wrapper does before it renders anything, it decides. If there is no user, it returns the prompt and the wrapped component never runs at all, not rendered and discarded, never called. That is the property this pattern has and hooks do not, and it is why this particular use case survived the transition. Applying it is one line at the export, and a component that is not wrapped is now visibly not wrapped, which is exactly the reviewability the previous variant lacked. The last variant wraps components to log and count their renders, and it is worth reading for the mechanics rather than the feature. Look at the generic signature that takes a component type and returns one with the same props, which is how you keep an RC type safe. Look at the spread that passes every prop straight through untouched. And look at where the wrapper's own state lives. The render count is in a ref inside the wrapper, entirely invisible to the component being wrapped, which neither knows nor can find out that it is being logged. That transparency is the pattern's real characteristic, and it cuts both ways. It is what makes an HOC composable, and it is what makes a stack of them hard to debug. The model to keep is a wrapper that gets to decide. A hook runs inside your component and hands you values, and HOC sits outside it and controls whether it runs at all. Almost everything people once used HOCs for was logic, and that work has properly moved to hooks. What is left is gatekeeping, yes, authentication, permissions, loading, and error boundaries, where deciding not to render is the entire job. When you meet one in an existing code base, read the wrapper first because the props it injects will not be visible anywhere else. The kata is the part that matters. Open the lesson, write the code yourself, then read back what you wrote and judge it. The link is in the description, and that practice is what keeps the skill yours. Kata is something you practice, not something you watch. Read the lesson, write the code yourself, then review what you wrote. This video is the reference you come back to afterwards. A model can produce this code in seconds, and the reason to write it by hand is to keep the judgment that tells you whether the code is any good. Every input on a page has state, and the only question is who owns it, React or the DOM. That single decision is what controlled and uncontrolled means, and it is worth learning properly for two reasons. It produces the most common warning in React, which people fix by copying a line from a search result without understanding it. And it is the pattern you have to implement yourself the moment you write a component other people will use, which the tabs lesson touched on, and this one covers properly. A controlled input takes its value from React state and reports changes back through a handler. Here is the part that makes it click. The input is not being told to update. It is being told what to display on every render, and it displays exactly that. Type a character and the DOM would normally show it. React then re-renders with the value from state, and what you see is whatever state now says. If your handler ignores the change, the character disappears because the input has no state of its own to fall back on. That is not a bug, it is the whole design, one source of truth, and the field is the display of it. An uncontrolled input keeps its own value in the DOM the way a plain HTML form always has. You give it a starting value with the default value attribute and then leave it alone, reading it when you need it, usually with a ref or from the form on submit. React does not re-render as the user types because React does not know they are typing. Worth being precise about the two attributes because this is where the warning comes from. Value makes it controlled, default value makes it uncontrolled, and they are not interchangeable spellings of the same idea. The card lists the advantages and they all come from the same property. React knows the value on every keystroke. Instant validation, formatting as you type, disabling the submit button while the field is empty, driving another part of the interface from what is typed. Anything that has to react to the value as it changes needs the value as it changes, and only this mode provides that. And these come from the opposite property: React is not involved. Less code, no state, no handler, no re-render per keystroke. For a large form where nothing needs to happen until submit, this is genuinely simpler and genuinely faster, and it is closer to how the platform already works. The performance point is real but modest, so let it be a tiebreaker rather than the reason. The rule I would give is a question about timing. Does anything need to happen while the user is typing? If yes, controlled, because that is the only mode where anything can. If no, if the value only matters at submit, uncontrolled is less code and fewer moving parts. Most application forms end up controlled because validation and disabled buttons are common requirements, and that is fine. What is not fine is reaching for control by reflex on a 12-field form where nothing reads the values until the end. This section is the one worth staying for because it is what you need when writing a component for other people. A library component cannot choose. Some consumers will want to own the value and some will not. So it supports both and the implementation is small. Keep internal state as a fallback and use the incoming prop instead whenever the prop is not undefined. Then whichever exists is what gets displayed, and the change handler both updates the internal state and calls the consumer's callback. That is how a native select does it, how every date picker and combo box you have used does it, and it is about 6 lines. The rules on screen are short and they are load-bearing. Lock the mode at the first render and never switch. A component that starts uncontrolled and later receives a value prop produces React's warning about switching modes, and the reason it warns is that the ownership of the value has changed underneath it, and neither party can now say what the correct value is. In practice, this happens when a value arrives from a fetch, and the fix is either to render nothing until the data is there, or to start controlled with an empty string rather than undefined. That is the distinction to remember. Undefined means uncontrolled and empty string means controlled and empty. They look similar in code and mean opposite things. Controlled means React owns the value and the input displays it. Uncontrolled means the DOM owns it and you read it when needed. Choose by asking whether anything must happen while typing. The value attribute and the default value attribute select the mode, and undefined against empty string is the trap. A reusable component supports both by preferring the prop when it exists and falling back to internal state. And the mode is fixed at the first render, so decide before you have data rather than after. This is the mistake that produces the warning, and it is worth seeing rather than reading about. The input is given a value from state and no change handler. React renders it with that value and now type into it. Nothing happens. The character appears for an instant and is replaced by the value from state, which never changed because nothing was there to change it. The field is not broken and it is not read only in the HTML sense. It is doing exactly what a controlled input does, which is display the state, and the state has no way to move. The console explains this, and the two ways out are to add the handler or to use the default value attribute instead. The handler is added and the loop closes. Type a character, the handler puts it into state, React re-renders, and the input displays what state now holds. Read the flow in that order rather than assuming the input updates itself, because that order is what explains everything else. Why you can transform the value on the way through and have the field show the transformed version, why an ignored change makes the character vanish, and why validating on every keystroke costs you nothing extra here. The same field with the DOM owning the value. There is no state, no handler, and no re-render. As you type, the input keeps its own value and a ref reads it at the point it is actually needed. Compare the amount of code with the previous variant and then ask what you gave up. Nothing can respond to the value while it is being typed because nothing knows. That is the trade in its entirety, and having seen both written out, the choice for your own forms should stop feeling like a matter of taste. The model to keep is a question of ownership asked once per input. React owns it and the field displays state, or the DOM owns it and you read it when you need it. Everything else follows. The warning is about ownership changing halfway, the undefined trap is about accidentally declaring no owner, and the hybrid pattern is a component politely letting the consumer decide. Ask who owns this value, decide before the first render, and stick to it. The kata is the part that matters. Open the lesson, write the code yourself, then read back what you wrote and judge it. The link is in the description, and that practice is what keeps the skill yours. Kata is something you practice, not something you watch. Read the lesson, write the code yourself, then review what you wrote. This video is the reference you come back to afterwards. A model can produce this code in seconds, and the reason to write it by hand is to keep the judgment that tells you whether the code is any good. Everything React does is arranged as a tree, and until now the React tree and the DOM tree have matched. A child component's elements appear inside its parent's elements. A portal breaks exactly one half of that. The element goes somewhere else in the document while the component stays exactly where it was in the React tree, and the reason to care is a problem that has nothing to do with React at all. Some CSS on an ancestor can make a model impossible to display correctly, and no amount of z-index will fix it. Create a portal with create portal, giving it what to render and which DOM node to render it into. The children appear inside that node, typically the body, rather than inside the parent's markup. What does not change is anything else. The component is still a child in the React tree, still receives its props, still reads the same context, and its state still lives with the component that owns it. Only the physical placement moves. Holding those two trees apart in your head is the whole lesson. The model on screen is rendered through a portal into the document body, and it covers the page properly because nothing above it in the document can clip it. Look at where the model is written in the code though, inside the component that owns the open state, exactly where you would expect it. That is the value. You write the model where it belongs, logically next to the state that controls it, and it renders where it needs to be physically. This is the part that surprises people, and it is worth being precise. Events from inside a portal bubble up through the React tree, not the DOM tree. So a click inside a model rendered into the body will still reach a click handler on the React component that contains the portal, even though there is no DOM path between them. That is not an accident. It is React's synthetic event system doing what the delegation lesson described. React catches events at the root and then walks its own tree, and its own tree still has the portal's contents as a child. The practical consequences run both ways. A form inside a portal still submits to the handler on the component that owns it, which is what you want. And an outside click handler that closes a dropdown can be triggered by a click inside its own portal content, which is not. The list on screen is the whole set, and they share one property, something that must escape its container. Modals covering the page, tooltips that would otherwise be cut off by a scrolling panel, drop-downs near the edge of a card, and notification toasts belonging to the whole application rather than to whichever component raised them. If a thing you are rendering is not visually contained by its parent, that is the signal. A tooltip is the smaller case and the more common one. A tooltip inside a container that has overflow hidden gets clipped at the boundary, and moving it to the body avoids that entirely. The cost you take on is position. Outside the container, it is no longer positioned relative to its trigger, so you have to measure the trigger and place the tooltip yourself. Portals solve the clipping and hand you the arithmetic, which is exactly the trade every positioning library exists to manage on your behalf. Create portal renders children into another DOM node while the component stays put in the React tree. Context, props, and state are unaffected. Events bubble through the React tree, which is usually what you want and occasionally the source of a confusing outside click bug. Reach for it when something has to escape a container that would clip it or stack it wrongly. And remember, it does not solve positioning, only containment. This is the problem. And the demo names the cause in its own heading. The card has overflow hidden and the modal is inside it. Overflow hidden tells the browser to cut off anything that extends past the elements box. and the child cannot opt out of that. So the dialog is drawn correctly and then trimmed to the shape of the card. Try raising the z-index in your head and notice it changes nothing because z-index controls what is drawn in front of what. And this is not a question of order. The pixels outside the box are not being covered up, they are not being painted. There is a second version of this trap worth knowing about, where an ancestor creates a new stacking context with a transform or a filter, and a fixed overlay can then no longer sit above the rest of the page. Different mechanism, same conclusion. The ancestor decides and no CSS on the modal overrules it. The same modal, one call different. It now renders into the document body, so the card that was clipping it is no longer an ancestor at all, and the overlay covers the page as intended. Read the component and notice how little moved. The state, the handlers, and the markup are all where they were, and the change is a wrapper around what gets returned. That is the practical shape of the fix, and it is why portals feel like a small tool for a problem that felt large. The last variant is the fuller version with a modal and a tooltip together, and it is worth reading for the details a real implementation needs. Look for where the portal target is obtained and what happens if it does not exist yet. Look for the escape key handler and the cleanup that removes it. And look at what is not handled because that is instructive too. Focus is not trapped inside the modal, and the page behind it still scrolls. A production dialog needs both, which is the strongest argument for using the platform's own dialog element or a maintained library rather than shipping this. The portal is the easy part, a correct modal is not. The model to keep is two trees that usually agree and no longer have to. The React tree decides what your component is a child of, and therefore its props, its context, and where its events go. The DOM tree decides what it is visually contained by, and therefore what can clip it or stack above it. A portal separates those two answers, which is why the fix for a trapped modal is not CSS at all. When something needs to escape its box, move it in the document and leave it where it is in your code. The kata is the part that matters. Open the lesson, write the code yourself, then read back what you wrote and judge it. The link is in the description, and that practice is what keeps the skill yours. Kata is something you practice, not something you watch. Read the lesson, write the code yourself, then review what you wrote. This video is the reference you come back to afterwards. A model can produce this code in seconds, and the reason to write it by hand is to keep the judgment that tells you whether the code is any good. Here is a problem you have definitely hit. You have a button component with your styles and behavior on it, and now you need one that navigates, so it has to be a link, not a button. Wrapping the link in the button gives you two elements where you wanted one, and nesting an anchor inside a button is invalid HTML besides. This lesson is about the two ways out, and the second one is the technique behind almost every modern headless component library. Your component renders a specific element, and sometimes the consumer needs a different one. A button that is really a link, a menu item that is really a rotor link, a trigger that is really a custom component someone else wrote. You cannot solve this by adding props because the thing that has to change is the element itself. And wrapping is not a solution. It adds a node to the DOM, splits styling and behavior across two elements, and produces invalid markup in exactly the cases you most want it. The traditional answer is an as prop, where you pass the element type you want and the component renders that instead of its default. It is simple and it works. Two costs. The types are genuinely difficult. A properly typed polymorphic component has to infer the props of whatever you passed, and that is some of the least pleasant TypeScript you will write. And it only reaches one level. The component renders your element, so anything more complicated than a tag name gets awkward. The alternative inverts it. Instead of telling the component what to render, you give it the finished element as its child and tell it to merge into that rather than render its own. So you write your anchor or your rotor link or your custom component, and the button merges its props onto it. The consumer supplies the element and the component supplies the behavior, which is the reverse of the as prop and is why the types get so much simpler. There is nothing to infer because you wrote the element yourself. The demo toggles the same button between rendering a native button and merging into an anchor. Watch what stays identical, the styles, the behavior, and everything the button contributes. And watch what changes the element in the DOM. One component, two element types, no wrapper in either case. The mechanism is small enough to read in one screen. A slot component takes its own props plus a single child element, checks the child really is an element, and calls clone element to produce a copy with the props merged in. That is it. Clone element is a React function that takes an existing element and returns a new one with additional or overridden props, and this is one of its few genuinely good uses. Two details in the merge are worth pausing on. The child's own props are spread last, so where both sides set the same prop, the child wins. The consumer's explicit choice beats the component's default. And style is merged as an object rather than overwritten, so the component's styling survives and the child's additions layer on top. Look closely at that ordering when you read it, because merge order is the entire behavior of this pattern and it is one line. Use asChild when you are building something for other people, a design system, a component library, anything where consumers will need element types you have not thought of. Use the as prop when the set of elements is small and known and you would rather have the simpler call site. And for an application component used in 3 places, use neither. Render the element you need. This is machinery for the library author case, and the cost of it in a single application is real and the benefit is mostly theoretical. asChild delegates rendering to the child and merges the component's props onto it using clone element. It avoids the wrapper element and the invalid markup that comes with nesting interactive elements. It is simpler to type than a polymorphic as prop because the consumer writes the element. Merge order decides who wins, and in this implementation the child does. And it is a library author's tool. Reach for it when you do not know what your consumers will need. The wrapping approach and the demo is honest about what it produces. There is an anchor inside a button which is invalid HTML. Browsers will accept it and screen readers and keyboard behavior will not thank you. The styles sit on the outer element and the navigation on the inner. So hover, focus, and click are now split across 2 nodes that have to be kept in agreement. Every one of those problems comes from the same source. 2 elements exist where the design called for 1. The same button delegating. When asChild is set, it renders a slot instead of a button, and the slot clones the child with the button's props merged in. 1 element in the DOM, an anchor, carrying the button styling and the anchor's behavior. Read the slot itself, it is about 8 lines, and then read the order of the spreads because that ordering is the whole contract. Slot props first, child props second, so the child overrides. Style merged deliberately rather than replaced, so both contribute. The last variant is the fuller implementation, and it is worth reading for what a production version adds. Look for the handling of a child that is not an element or text or several children, because clone element requires exactly 1 element, and a real implementation has to decide what to do otherwise. Look at how refs are dealt with, since both the component and the consumer may want 1 and only 1 can win unless they are composed. And notice what this implementation does not do that a library like Radix does: compose event handlers, so both the components and the childs run. Here, the child's handler replaces the components, which follows directly from the merge order you just read. That is a reasonable choice, and it is a choice, and knowing which one your slot makes is the difference between the pattern working and a click handler silently disappearing. The model to keep is a reversal of who supplies the element. Normally, your component decides what to render and the consumer configures it. With asChild, the consumer supplies the finished element and the component merges itself into it, which removes the wrapper, keeps the markup valid, and sidesteps the typing problem entirely. The whole mechanism is clone element plus a merge, and the merge order is the part to get right because it silently decides whose props win. The kata is the part that matters. Open the lesson, write the code yourself, then read back what you wrote and judge it. The link is in the description, and that practice is what keeps the skill yours. Kata is something you practice, not something you watch. Read the lesson, write the code yourself, then review what you wrote. This video is the reference you come back to afterwards. A model can produce this code in seconds, and the reason to write it by hand is to keep the judgment that tells you whether the code is any good. Every pattern in this section so far has treated children as something to render. This one treats them as something to read. The parent looks through its children, inspects their props, and uses what it finds to build part of its own output. It is a real technique with real uses, and it is also the one lesson in this section where the honest recommendation is mostly do not. So we will cover how it works and then be straightforward about why React's own documentation lists the API it depends on as legacy. Children arrive as a prop, and that prop is just a value. Instead of dropping it into your output, you can walk it, look at each child's type and props, and treat those as a description of what to build. A tabs component can read the label of each panel and generate the tab strip from it, so the consumer writes their panels once and never repeats the labels. That is the appeal. The markup becomes a single source for both halves. Compare this with the tabs lesson earlier in this section. There, the tab list and the panels were separate subtrees that agreed through context, and the consumer wrote both. Here, the consumer writes only the panels, each carrying a label prop, and the parent derives the tab strip by reading those labels. Less to write and less to keep in sync. The cost, which the next sections make concrete, is that the parent now knows what its children are, which is exactly what composition normally avoids. The tabs on screen were built this way. Every tab button you can see was generated from a label prop on a panel that the consumer wrote. Nothing declares the buttons. Try to imagine adding a fifth tab and notice that it is one element with one prop and the strip updates itself. That is the pattern delivering exactly what it promises. The mechanism is two functions. Children.for each walks the children prop safely, which matters because that prop is not reliably an array. It can be one element, several, a fragment, a string, or nothing at all, and iterating it directly breaks on most of those. Then is valid element checks. Each entry really is an element before touching its props. And here is the line that carries the whole cost of the pattern. The parent compares each child's type against the panel component to decide whether it counts. That comparison is the parent knowing exactly which components it is willing to accept, and everything that goes wrong with this pattern goes wrong there. The section on screen calls the children API legacy, and that is React's own wording. So let me explain what actually breaks. The type comparison only matches the exact component. Wrap a panel in anything, a conditional wrapper, a component that adds a permission check, a fragment from a map, and the parent no longer recognizes it, and the tab silently disappears with no error. The consumer cannot compose around your children, which is the opposite of what every other pattern in this section is for. And it fails invisibly, which is the worst property a pattern can have. The alternatives are the ones you have already built. Pass the data as an actual array prop, which is honest about being data. Or use context, the compound component approach from lesson 22, where each child registers itself with the parent instead of the parent inspecting each child. The second is what modern libraries do, and it survives wrapping because a wrapped child still renders and still registers. Children as data means the parent reads its children's props rather than only rendering them. Children dot for each and as valid element are what make walking that prop safe. The pattern removes duplication between a list and its contents, and the price is a parent that recognizes only exact component types. It breaks silently when a child is wrapped. Prefer an array prop when the thing genuinely is data, or context registration when you want composition, and reach for this mainly when reading existing code that uses it. The playground is one file holding the full tabs implementation, and it is worth reading with one question in mind. What happens if a consumer wraps a panel? Find the type comparison, so it is a single condition, and follow what that condition does when the child is a wrapper component that renders a panel inside itself. The answer is that it does not match. The panel contributes no tab, and its content never appears with nothing logged and nothing thrown. Then look at the tabs lesson from earlier in this section in your head, where each panel registered itself through context, and notice that the same wrapping is harmless there. That comparison is the entire argument for preferring registration over inspection, and it is much more convincing once you have found the exact line that fails. The model to keep is inspection against registration. Inspection means the parent looks at what it was given and decides what counts, which couples it to specific component types and breaks the moment anything is wrapped. Registration means each child announces itself through a context the parent provides, which survives wrapping because rendering is what triggers it. The first is less code, and it is what this lesson demonstrates. The second is what to reach for, and knowing why is the useful part of having seen both. The kata is the part that matters. Open the lesson, write the code yourself, then read back what you wrote and judge it. The link is in the description, and that practice is what keeps the skill yours. Kata is something you practice, not something you watch. Read the lesson, write the code yourself, then review what you wrote. This video is the reference you come back to afterwards. A model can produce this code in seconds, and the reason to write it by hand is to keep the judgment that tells you whether the code is any good. This lesson closes the pattern section, and it is the simplest thing in it, which is the point. Slots are named props that hold content. That is the entire pattern. After compound components, render props, HO keys, and children inspection, it is worth ending on the one that requires no machinery at all, because for a very large share of real components, it is the right answer and people talk themselves out of it. A slot is a prop that takes an element instead of a string or a number. A card takes a header, a footer, and a body. A dialog takes a title, content, and actions. Each name prop is a place where content goes, and the component decides where each one is rendered. Nothing new is happening here. Props have always been able to hold elements, and this is only a name for using that deliberately with names that describe regions of a layout. Children is one unstructured slot. When a component has one place to put content, that is exactly right, and when it has three, it is not. Handing a component a single blob and expecting it to work out which part is the header means it cannot. It would have to inspect the children and match on types, which is lesson 29 and comes with all the problems we just covered. Named props skip that entirely because the consumer has already labeled each piece by choosing which prop to put it in. The card on screen shows the failure. Everything arrives as one lump, and the component can only render it in one place. Any structure the consumer intended on this bit is a heading, this bit is actions, exist in their head and in the order of the markup, and nowhere the component can read. Styling one region differently from another is impossible without guessing. The same card with each piece arriving through its own prop. The component now controls the layout completely. It can put a border under the header, push the footer to the bottom, and add padding to the body because it knows which is which. And it can respond to absence. No footer prop means no footer area at all, rather than an empty box where one would have been. The demo toggles the header and footer on and off. Watch the layout when a slot is missing, because that is where slots earn their keep over children. The component renders the region only when the prop is there, so the card closes up rather than leaving a gap. That conditional is one line per slot, and it is the difference between a component that looks right in every configuration and one that looks right in the configuration you designed it for. There is almost nothing to implement. Accept the props, render each one where it belongs, and guard each region on the prop being present. Two small things worth doing well. Type the slots as React node rather than as a specific element type, because a consumer may reasonably pass a fragment, a string, or several elements. And name the slots after regions of the layout rather than after what you expect to be in them. Header rather than title, because the first survives the consumer putting something you did not anticipate in it. Here is the decision, and it is worth stating as a progression. Children when there is one content area, which is most components. Named slots when there are several fixed areas and you control the layout between them. Compound components when the consumer needs to control the arrangement itself or when the parts need to share state. That order is also increasing cost. The children is free, slots are one prop per region. Compound components bring context, a public API of parts, and the indirection that goes with them. The card on screen puts compound components as the most flexible and the most complex, which matches lesson 22 exactly. The distinction that decides between them is whether the arrangement is yours or the consumer's. With slots, you decide where the header goes and they decide what is in it. With compound components, they decide both. Most application components want the first and most library components want the second, which is roughly why one pattern dominates each world. Dialog is the clearest case. Title, body, and actions are three regions with genuinely different treatment. The title is styled, the body scrolls, the actions are pinned to the bottom and right aligned. Three name props express that directly, and the component can guarantee the structure, which matters more here than elsewhere because a dialog has accessibility requirements that depend on knowing which part is the title. Slots are named props holding elements, one per region of a layout. They exist because children is a single unstructured area and most components have more than one. The component owns the arrangement and the consumer owns the content. Guard each region, so a missing slot removes it rather than leaving a gap. Type them as React node and name them after regions. And choose by counting one area children, several fixed areas, slots, consumer controlled arrangement, compound components. The card taking everything as children. Read it and notice that there is genuinely no way for this component to do better with what it has been given. It cannot style the heading differently because it does not know which part is the heading. It cannot separate the actions because they are just more children. The consumer's intended structure is invisible to it, and the only ways out are named props or inspecting the children, which we have just seen the cost of. 3 props instead of 1, and the component gains complete control of the layout. Look at how each region is rendered conditionally. So a card without a footer has no footer area rather than an empty one. Then look at the call site and notice it is arguably clearer than the children version because each piece of content is labeled by the prop it is passed to. That is unusual for a pattern as the implementation gets more capable and the call site gets more readable at the same time. The last variant is a fuller component with more slots and real styling, and it is worth reading for how quickly the pattern reaches its limit. Count the slots. At 3 or 4, this is clean. At 8, it is a component with 8 element props and a layout nobody can picture from the signature. That is the point where the consumer wanting to rearrange things stops being hypothetical, and it is the signal to move to compound components. Knowing where the boundary sits is more useful than either pattern on its own, and this variant is close enough to it to feel where it is. The model to keep is that children is one slot, and the moment you need 2, you need names. Everything else in this lesson follows. The component owns the arrangement because it knows which region is which, Absent slots remove their regions and the pattern runs out when the number of regions gets large enough that the consumer wants to arrange them. Of everything in this section, this is the one to reach for first. The elaborate patterns are for when you have established that you need them. The kata is the part that matters. Open the lesson, write the code yourself, then read back what you wrote and judge it. The link is in the description, and that practice is what keeps the skill yours. Kata is something you practice, not something you watch. Read the lesson, write the code yourself, then review what you wrote. This video is the reference you come back to afterwards. A model can produce this code in seconds, and the reason to write it by hand is to keep the judgment that tells you whether the code is any good. This opens the state management section, and context is where it has to start, because context is the thing people reach for and then discover is not quite a state manager. It solves one problem completely, getting a value from where it lives to where it is needed without threading it through every component in between. It does not solve the problem people expect it to, which is managing shared state efficiently, and knowing exactly where that line falls is what this lesson is for. 3 pieces. Create context makes the object. A provider wraps a subtree and supplies a value. Use context reads the nearest provider above the component that calls it. That word nearest is worth pausing on. Providers can nest, and a component gets the closest one above it in the tree, which is what makes it possible to override a theme for one section of a page. If there is no provider at all, the component gets the default value passed to create context, which is a genuinely useful place to put a sensible fallback and a common place for a confusing bug when the provider was meant to be there and is not. Nothing stops you having several, and you should. A theme context, an authentication context, a local context separate things with different lifetimes and different consumers. The alternative people drift into is one application context holding everything, which couples every consumer to every change, and the provider lesson in the performance section covered exactly what that costs. Multiple contexts also read better. A component that reads the RWth context is telling you what it depends on. This is the combination that gets called poor man's redux, and the description is fair. A reducer owns the state transitions, context distributes the state and the dispatch function, and you have something with the shape of a store and none of the dependencies. 2 things make it work in practice. Put the state and the dispatch in separate contexts, because dispatch never changes, and components that only dispatch should never re-render. That is the split from lesson 18, and this is where it pays most. And keep the reducer pure so it stays testable without any of this machinery around it. The list on screen is the same advice as the provider lesson, and it is worth restating in one sentence because it is the thing people get wrong. Context re-renders every consumer when the value's identity changes, and memo does not protect against it. So split the value into separate contexts, keep each one's identity stable, and pass expensive non-consuming subtrees in as children so they are not rebuilt by the provider's render. Those 3 cover almost everything. When they stop being enough, when you genuinely need components to subscribe to part of a value and not the rest, that is not a context problem anymore. And the next lesson is about exactly that boundary. Context passes a value down without prop drilling, and a component reads the nearest provider above it. Use several small contexts rather than one large one. Combine it with a reducer when you want transitions in one place, keeping state and dispatch in separate contexts. Remember that every consumer re-renders when the value changes, and that memo cannot stop it. And treat elaborate work to avoid that as a signal that the data wants a different tool. The playground is one file with a theme context, an authentication context, and a reducer-backed one, so you can see the 3 shapes side by side. Read them for the differences rather than the similarities. The theme context is a value and a setter, which is the simple case. The auth context carries a small object, which is where the identity question starts to matter. And the reducer backed one splits state from dispatch, which is the pattern worth copying. Try the exercise of adding a fourth piece of shared state to this file and deciding which of the three shapes it belongs in. The answer is usually obvious once you ask how often it changes and who needs it. And that is the whole design method for context. The model to keep is that context is a delivery mechanism, not a store. It answers where does this value come from, and the answer is the nearest provider above me. It does not answer how do I subscribe to only the part I care about, and everything that feels awkward about context at scale comes from asking it that second question. Use it for what it does: configuration, themes, the current user, a dispatch function, and when you find yourself splitting a context for the third time to avoid re-renders, take that as information rather than as a puzzle to solve. The kata is the part that matters. Open the lesson, write the code yourself, then read back what you wrote and judge it. The link is in the description, and that practice is what keeps the skill yours. Kata is something you practice, not something you watch. Read the lesson, write the code yourself, then review what you wrote. This video is the reference you come back to afterwards. A model can produce this code in seconds, and the reason to write it by hand is to keep the judgment that tells you whether the code is any good. The previous lesson ended by saying context answers where does this value come from, and not how do I subscribe to only the part I care about. This lesson is that second question answered properly. It is the most technically dense lesson in the course so far, and it is worth the effort because what you build here is the mechanism inside every state library you have used. And once you have written it, their documentation reads completely differently. State the problem exactly. A context notifies every consumer whenever its value changes, and it compares by identity. So an object holding 5 fields re-renders all 5 sets of consumers when any one field changes. A component that reads only the user's name re-renders when an unrelated counter increments. Splitting into more contexts helps and does not scale. 5 fields become 5 providers, and the moment 2 of them are needed together, you are back to nesting and to values that change for reasons a consumer does not care about. Here is the move, and it is a genuine change of model rather than an optimization. Take the state out of React entirely and put it in a plain object that holds a value and a list of listeners. Components then subscribe to that store with a selector, a small function saying which part they want, and re-render only when that selected part changes. React has a hook built for exactly this. Use sync external store, which takes a subscribe function and a function returning the current snapshot. What context distributes now is just the store itself, which never changes identity, so the provider causes no re-renders at all. The subscriptions do all the work. This is the part that catches everyone, and the implementation on screen handles it explicitly. Your selector's result is compared against the previous result to decide whether to re-render, and the default comparison is identity. So a selector that returns a new object, picking 2 fields into a fresh object literal for instance, produces a different object every single time it runs, never compares equal, and re-renders on every store change. You have written a subscription that behaves exactly like the thing you were trying to replace. 2 ways out. Select primitives, 1 per hook call, which is the simplest and is what most code bases end up doing. Or pass a shallow equality function that compares the fields rather than the reference, which is what the shallow comparison in this file is for. If you have ever wondered why Zooston's documentation is so insistent about this, that is why. Real applications need computed values, a filtered list, a total, a count of something. A selector can compute, and the same trap applies with more force because filtering an array returns a new array every time. The answer is the same. Either return a primitive such as the length, or use an equality function that looks inside and memoize the expensive part if it is genuinely expensive. Worth noticing that a selector runs on every store change for every subscribed component. So an expensive selector multiplied by 50 components is real work. A single global store is fine until you need two of the same thing, get an eye, two independent lists on one page, or a store per open document. Putting the store in a context solves that. And this is context doing what it is genuinely good at. Not distributing changing state, but distributing a stable reference to which store this part of the tree should use. That is dependency injection, and it composes properly because the value never changes and no consumer re-renders when it does not. The comparison card puts splitting as the simpler approach then, and it is right for a wide range of applications. Several small contexts, each with a stable value, gets you most of the benefit with none of this machinery, and it is the answer for the majority of real code bases. Reach past it when the number of contexts starts tracking the number of fields, or when consumers need different combinations of the same data. And this is the other side. One store, fine-grained subscriptions, scales to many consumers and frequent updates. The cost is the machinery you can see on screen, plus the equality trap waiting for anyone who writes a selector carelessly, which is why the honest recommendation is to use a library. Not because you cannot write it, you just watched it be written, but because the library has already handled the snapshot caching, the server rendering path, and the equality helpers. And those are exactly the parts where a subtle mistake produces a bug you will not find by looking. Context notifies every consumer because it compares one value by identity. Selectors fix that by moving state to an external store and subscribing per component through useSync external store. The selector's result is compared to decide on re-rendering, so returning a fresh object defeats the whole mechanism. Select primitives or supply a shallow equality function. Context still has a role, holding a stable reference to the store for scoping. And this is the inside of the libraries you already use, which is the real reason to have built it once. The problem measured. Several consumers, each reading one field from a single context value with render counters. Change one field and watch every counter move, including the components that read nothing related to it. Nothing here is written badly. This is what context does faithfully. The counters are the useful part. This lesson is one of the few in the course where the improvement is a number you can watch change rather than an argument you have to accept. The same application on a store with selectors. Change one field now and only the counters for components selecting that field move. The rest stay exactly where they were. Read the hook implementation while you are here because it is 5 lines and it is the whole idea. Get the store from context, subscribe to it, and hand use sync external store, a function that runs the selector against the current state. React does the comparing. And notice what every one of these components selects, a single field, a string, or a number, because that is the only reason this version can get away with being this short. The snapshot function builds a fresh result on every call, and for a primitive that is harmless since two equal strings compare equal. Select an object here and this exact code would re-render forever. The last variant is the full version and it is 220 lines, which is itself the argument. Read it for the parts the simple version leaves out. A shallow equality helper, so a selector may return an object, memoize derived selectors, and caching around the snapshot so it returns the same reference until the state actually changes. That last one is not decoration. useSync external store calls the snapshot function repeatedly and compares what it gets back. So a function that builds something new every time never settles. Each of those exists because of a specific failure, and you can work out which from the code. This is also the point where the recommendation becomes concrete. When your handwritten version has grown to look like this one, you have rebuilt a library, and the remaining differences between yours and theirs are the bugs they have already fixed. The model to keep is a change of ownership. Context asks React to distribute a value, so every consumer hears about every change. An external store keeps the value outside React and lets each component subscribe to exactly the slice it uses, with the comparison deciding whether that slice actually changed. That comparison is the whole design, and the fresh object trap is the one thing to remember. If your selector builds something new each time, nothing can ever compare equal, and you have written an expensive way to re-render everything. The kata is the part that matters. Open the lesson, write the code yourself, then read back what you wrote and judge it. The link is in the description, and that practice is what keeps the skill yours. Kata is something you practice, not something you watch. Read the lesson, write the code yourself, then review what you wrote. This video is the reference you come back to afterwards. A model can produce this code in seconds, and the reason to write it by hand is to keep the judgment that tells you whether the code is any good. Count the Boolean flags in the last component you wrote that fetch it something. Loading, error, success may be submitted. 4 booleans give 16 combinations and you meant 4 of them. The other 12 are states your component can technically be in, and that nobody designed loading and error at the same time, success and loading together. This lesson is about not having those 12, and the technique is older and simpler than most of what this course has covered. A state machine says there is a fixed set of states, the thing is in exactly one of them, and there is a defined set of transitions between them. Idle goes to loading when you submit. Loading goes to success or to error and to nothing else. What makes it different from a pile of booleans is not the vocabulary, it is the exclusivity. One variable holding one of 4 values cannot represent 2 states at once. So the invalid combinations do not exist rather than being avoided by discipline. The first item on screen is the whole argument, and it is worth reading slowly. Impossible states are impossible. Not discouraged, not caught in review, unrepresentable. Everything else follows. Transitions are explicit. So the answer to can this go from error straight to success is in the code rather than in someone's memory. The set of states is a list you can read, which makes the thing testable and, unusually for code, diagrammable. And a state that carries its own data, error holding the message, success holding the result, makes it impossible to have an error message with no error, which is the flag-based version of the same bug. XState is the well-known library here, and it is worth being clear about what it adds, because you do not need it to get the benefit. A reducer with a switch on the current state gives you the exclusivity and the explicit transitions, and that is most of the value. XState adds hierarchy and parallel states for machines complex enough to need them, visualization, and a formal state chart model with a specification behind it. Reach for it when the machine is genuinely complicated. For a 4-state fetch, the reducer you already know how to write is the right size. The list on screen is a good one. Multi-step forms, authentication flows, anything with a wizard, media players, any request with a life cycle. The property they share is that the transitions are the interesting part. When what matters about your state is the values, use ordinary state. When what matters is which stage you are in and what may follow it, a machine expresses that directly, which is the same test the useReducer lesson gave, taken one step further because a machine also restricts which transitions are allowed rather than only naming them. A state machine is a finite set of states, one at a time, with defined transitions. Its value is that invalid combinations become unrepresentable rather than avoided. Attach data to the state that owns it, so you cannot have a message without an error. A reducer with a switch is a state machine and is enough for most cases. Reach for XState when you need hierarchy, parallelism, or the diagram, and choose it when the transitions matter more than the values. 4 booleans and the combinations they allow. Read the handlers and count how many places have to set more than one flag to keep the picture consistent. Setting loading true and error false and success false each time in the right order by hand. Every one of those is an opportunity to forget one. And the failure is not an exception. It is a spinner that stays on screen next to an error message, which is a bug report you have almost certainly received. The code is not badly written. The shape simply allows more states than the design has. One variable holding one of four values and a transition function that decides what may follow what. Look at what disappeared. Every place that set two flags together is now a single assignment because the states are exclusive by construction. Then look at the transition function itself, because that is the design made explicit. You can read off which moves are legal, and a move that is not there simply cannot happen. Notice the data traveling with the state as well, the error carrying its message and the success carrying its result, so the component can only read a message when there is one to read. The last variant is a fuller machine with more states and a real flow, and it is worth reading with one exercise in mind. Pick two states that should never follow each other, then try to find a way to get from one to the other. If the machine is written properly, there is no path, and confirming that takes seconds because the transitions are a list rather than a property of scattered code. That is the practical benefit that survives after the novelty wears off. Questions about what your component can do have answers you can look up instead of reason about. The model to keep is that a type can rule out a bug. 4 booleans describe 16 situations and you wanted 4. One value from a set of 4 describes exactly the 4. Everything else, explicit transitions, data attached to its state, the diagram, follows from making the shape of the state match the shape of the design. You do not need a library to do it. You need to stop reaching for another boolean when the thing you are describing is a stage. The kata is the part that matters. Open the lesson, write the code yourself, then read back what you wrote and judge it. The link is in the description, and that practice is what keeps the skill yours. Kata is something you practice, not something you watch. Read the lesson, write the code yourself, then review what you wrote. This video is the reference you come back to afterwards. A model can produce this code in seconds, and the reason to write it by hand is to keep the judgment that tells you whether the code is any good. This closes the state management section by comparing the options, and I want to set the comparison up honestly because library roundups are usually a list of adjectives. The useful comparison is not which is nicer, it is what shape of state each one assumes. And there is a prerequisite question that comes first and gets skipped. Does this state need to be global at all? Most state that ends up in a global store started as component state that someone lifted one level too far. The list on screen is a good one, and what its entries share is that they are read in many places and owned by nobody in particular. The signed in user, the theme, a notification queue. Compare that with the form's contents or whether a drop-down is open, which belong to one component and its children. The test from the composition lesson still applies and is still the first thing to ask: how far up does this genuinely need to go? Global is the answer when the answer is everywhere, and it is over-applied because it is easier than working out where the value actually belongs. Context is built in and needs no dependency, and lesson 31 covered what it is: a delivery mechanism. It suits values that change rarely, a theme, a locale, the current user, where re-rendering every consumer on a change is genuinely fine because changes are rare. It stops suiting the job when updates are frequent and consumers are many, which is the point lesson 32 picked up. ZooStend is a single store outside React with selector-based subscriptions, and you have already built it. That is not a figure of speech. Lesson 32's external store with useSync external store and per component selectors is the same design, and the equality trap you learned there is the same trap its documentation warns about. What the library adds is the careful parts: snapshot stability, shallow comparison helpers, middleware, dev tools, which is exactly the list of things that were fiddly when we wrote them by hand. Jotai takes the opposite shape. Instead of one store you slice with selectors, it has many small atoms, and a component subscribes to the atoms it uses. Derived atoms compute from other atoms and update when their inputs do. It is bottom-up, where Zustand is top-down. You compose state out of small pieces rather than carving it out of a large one. Which fits better depends on whether your state naturally decomposes. A graph of independent values suits atoms, and one large interrelated document usually does not. Redux is the reducer pattern from lesson 11 applied to the whole application, with the strictness kept and most of the ceremony removed. What it still buys, and what nothing else on this list matches, is the tooling. Every change is an action with a name, so DevTools can show you an ordered log of everything that happened and let you step backwards through it. On a large team, on a long-lived application, that traceability is the argument, not performance and not conciseness. The recommendations on screen are by application size, and I would replace that axis with two better questions. How is the state read? There are a few large slices or many independent values. That separates a store with selectors from atoms. And how much do you need to explain what happened after the fact? That is what pulls you towards Redux and its log. Size correlates with both, which is why the usual advice is roughly right, but the underlying questions are the ones that give you an answer for your case rather than for a typical case. Ask whether the state needs to be global before choosing how to make it global. Context is delivery and suits rarely changing values. Zustand is one store with selectors, which is the mechanism you built in lesson 32. Jotai is many atoms composed bottom-up. Redux toolkit is reducers plus a traceable log of every change. Choose on the shape of your state and on how much you need to explain it later, not on the size of the application. The playground implements the store pattern directly in about 80 lines, and it is worth recognizing what it is. A create store function holding state and a set of listeners, a hook wrapping use sync external store, two components sharing that store with no provider and no context anywhere. This is Zustand's core in miniature, the same design, minus the selector layer that lesson 32 added and minus everything the library handles around the edges. Read it, then read Zustand's introduction and notice how little of that documentation is new information now. That is the point of having written it. The libraries stop being magic and become a list of decisions you can evaluate. The model to keep is that these tools differ in the shape they assume, not in quality. One store you slice, many atoms you compose, or a delivery mechanism for values that rarely change, plus a strict reducer with a log when you need to answer questions about the past. You have now built two of those from scratch, which means picking between them is a judgment about your state rather than a guess about libraries. And the first question stays the same. Does this need to be global, or did it just get lifted too far? The kata is the part that matters. Open the lesson, write the code yourself, then read back what you wrote and judge it. The link is in the description, and that practice is what keeps the skill yours. Kata is something you practice, not something you watch. Read the lesson, write the code yourself, then review what you wrote. This video is the reference you come back to afterwards. A model can produce this code in seconds, and the reason to write it by hand is to keep the judgment that tells you whether the code is any good. ARIA has a reputation for being a long list of attributes to memorize, and that is the wrong way in. The specification's own first rule is not to use it. If a native HTML element already carries the meaning you need, use that element and add nothing. Almost all accessibility work in a React code base is applying that one rule, and the attributes are for the cases the platform genuinely does not cover. This lesson is those two halves in order. ARIA is a set of attributes that describe an element to assistive technology, what it is, what state it is in, and what it is called. Two things it does not do, and both surprise people. It changes nothing visually and it changes no behavior at all. Putting a button roll on a div does not make it focusable, does not make the keyboard activate it, and does not make it do anything a div did not already do. It only changes what a screen reader announces. That gap between what an element is announced as and what it actually does is where most broken accessibility comes from, and it is why the specification tells you to reach for the real element first. The list on screen starts with semantic HTML first, and that ordering is the whole discipline. A button element gives you the role, focusability, keyboard activation with both enter and space, disable semantics and form submission, and it gives them consistently across browsers and assistive technologies. Every one of those is something you would otherwise write and maintain. After that, label things that have no visible text, never put a role on an element that already has the right one, and use ARIA hidden only for genuinely decorative content, an icon next to a word that already says the same thing. And the rule that catches people, ARIA hidden on a focusable element produces something a keyboard can reach and a screen reader cannot describe, which is worse than either alone. ARIA describes, it never behaves. The first rule is to use the native element instead because it brings behavior that ARIA cannot add. Reach for attributes when there is no native equivalent, and then supply the state as well as the role because a role without its state is only half the information. Label anything whose purpose is not in its visible text. And test with the keyboard first, since almost every accessibility bug worth finding shows up as something you cannot reach or cannot activate. A div dressed as a button. It looks right, it has a click handler, and a mouse user would never know. Now go through what a keyboard user gets. You cannot tab to it because a div is not focusable. If you force focus onto it, enter does nothing and space scrolls the page. A screen reader announces it as a group of text rather than a control, so nothing tells the user it can be activated, and it has no disabled state to speak of. That is 4 separate failures from one substitution, and none of them is visible on the screen. The same thing as a button element, and count what came back for free. It is in the tab order without a tab index. Enter and space both activated, including the detail that space must not scroll the page while doing so. It announces as a button with its label. It supports disabled properly, which removes it from the tab order as well as graying it out. The visual difference is nothing. Once you have styled it, the difference in what it can do is everything. This is the first rule of ARIA in one div, and it is why the rule is first. The label on this variant says div, and it is worth looking at what the code actually does, because it is better than the label suggests. It is a real button element given a switch role, an ARIA checked attribute carrying the on or off state, and an ARIA label describing what it controls. That is the correct pattern, and it is more instructive than a div would have been. HTML has no switch element, so the role is genuinely needed, and the button underneath still supplies the focus, the keyboard handling, and the activation. Notice that the role and the state travel together. A switch that never reports whether it is checked is announced as a switch in no particular state, which is not much better than a plain button. The lesson to take is the layering. Native element for behavior, ARIA only for the meaning the platform does not have. The model to keep is that ARIA is a description layer and nothing more. It tells assistive technology what something is, it never makes it so. So the order is always the same. Reach for the element that already behaves correctly and add attributes only where the platform has no equivalent, supplying the state alongside the role. And check it with the keyboard, because the keyboard is where the difference between an element that behaves and one that merely claims to becomes obvious in about 2 seconds. The kata is the part that matters. Open the lesson, write the code yourself, then read back what you wrote and judge it. The link is in the description, and that practice is what keeps the skill yours. Kata is something you practice, not something you watch.
Read the lesson, write the code yourself, then review what you wrote.
This video is the reference you come back to afterwards. A model can produce this code in seconds, and the reason to write it by hand is to keep the judgment that tells you whether the code is any good. The previous lesson said to test with the keyboard, so this one is about what you are testing for. There is a quick version you can run on any page you have built. Put your mouse down, press tab repeatedly, and watch where the focus ring goes. If it disappears, if it jumps somewhere unexpected, or if it wanders behind a modal that is supposed to be blocking, you have found something real. Almost every problem in this lesson shows up in that 30-second exercise. The list on screen names who benefits, and the point I would add is that it is not a small group, and it is not only people with permanent disabilities. Someone with a broken wrist, someone using a screen reader, someone on a laptop with a failing trackpad, and every power user who lives on the keyboard. It also happens to be the accessibility work with the clearest test. Unlike color contrast or sensible labeling, you can verify keyboard access completely by using it without any specialist tooling. 3 values, and one of them is a trap. 0 puts an element in the natural tab order, in document order, which is what you want for anything custom that should be reachable. -1 removes it from tab order while leaving it focusable in code, which is exactly what you need for a modal container you intend to focus programmatically, and for the inactive tabs in a roving tab index. And any positive number jumps the element ahead of everything with 0 across the whole page, which sounds useful and reliably produces an order nobody can predict once a second developer adds another. Treat positive tab index as something you do not use. Focus is a single thing that moves, and dynamic interfaces have to move it deliberately. Open a modal, focus should go inside it, usually to the first control or the dialog itself. Close it, focus should return to whatever opened it, or the user is dumped at the top of the document with no idea where they were. Delete a row, focus has to go somewhere because the element holding it has just been removed and the browser's fallback is the body. This is where React makes things easy and easy to forget. You render the modal conditionally, the DOM changes, and nothing moves focus unless you write it. The list on screen is the set of conventions users already have. Tab and Shift tab move between components. Arrow keys move within one, inside a tab strip, a menu, a list box, which is the roving tab index from lesson 23. Enter and space activate escape cancels or closes. Home and end jump to the ends. What matters is that these are expectations rather than suggestions. A menu that requires tab to move between items is not a broken menu technically, and it is wrong because every other menu the user has ever used works the other way. This ties the section back to lesson 23, and it is worth noticing that the accessible tabs component and the compound component are the same object. The pattern gave us a parent owning the selected index and parts reading it. The accessibility requirements gave us roles, arrow key handling, and a roving tab index. Neither is an addition to the other. A component built one way and not the other is either inaccessible or unstructured, and building it once with both is barely more work than either alone. Try the demo with the keyboard rather than the mouse. Tab once and you are on the tab strip. Arrows move between tabs. Tab again and you are past the strip and into the panel. Count the presses to get past 3 tabs. It should be 1, not 3. That is the roving tab index working, and it is the clearest demonstration of why it exists. Everything interactive must be reachable and operable by keyboard. Use tab index 0 to add, -1 to make focusable but skipped, and never a positive value. Move focus deliberately when the interface changes into a dialog on open, back to the trigger on close, somewhere sensible after a deletion. Follow the conventions for arrows, enter, space, and escape because users already have them. And test by pressing tab, which finds most of this in half a minute. A modal that renders on top of the page and does nothing about focus. Open it and press tab. The focus ring walks through the dialog and then straight out into the page behind, which is still there, still focusable, and visually covered. A sighted keyboard user watches the ring vanish under an overlay. A screen reader user is simply reading the page behind the dialog with no indication that anything is in front of it. Nothing here throws and nothing looks wrong on screen, which is why this shifts so often. The same modal with the two things it was missing. Focus moves into the dialog when it opens, so the user starts where the content is, and tab is contained. At the last focusable element, it wraps to the first instead of escaping. Read how the trap is implemented because the mechanics are worth knowing. So it collects the focusable elements inside the container, watches for tab, and redirects at the boundaries. Note also the cleanup restoring focus to whatever was focused before, which is the half people forget. Trapping focus and then dropping it on close is only half a fix. The last variant is a fuller example with several patterns in one place. Read it with the keyboard rather than the eyes. Open the page, put your hands on tab, arrows, and escape, and work through it. Anything that surprises you is a bug, and the useful thing about this variant is that it is written correctly, so the surprises should be zero. Getting a feel for what correct feels like is most of what makes the wrong version noticeable in your own work later. The model to keep is that focus is a single thing, it is always somewhere, and when the interface changes, it is your job to decide where. Everything else follows. A modal takes focus and gives it back. A deleted row hands focus to a neighbor. A tab strip is one stop with arrows inside it, and nothing anywhere uses a positive tab index. And the test is not a tool or an audit, it is pressing tab and watching. Do that on the last thing you built and you will almost certainly find one of these. The kata is the part that matters. Open the lesson, write the code yourself, then read back what you wrote and judge it. The link is in the description, and that practice is what keeps the skill yours. Kata is something you practice, not something you watch. Read the lesson, write the code yourself, then review what you wrote. This video is the reference you come back to afterwards. A model can produce this code in seconds, and the reason to write it by hand is to keep the judgment that tells you whether the code is any good. Forms are where accessibility problems cost the most, because a form is the point at which someone is trying to actually do something rather than read. And the most common mistake in modern interfaces is one that looks like good design, using placeholder text instead of a label. It looks clean, it saves vertical space, and it fails for more people than almost anything else on this list. That is where this lesson starts. Every input needs a label element associated with it, and association means one of two things: the labels for attribute matching the input's ID or the input nested inside the label. Both work. What does not work is a paragraph that sits above the input looking like a label because nothing connects them, so a screen reader reaching the input announces an edit field with no name. The association also gives you something sighted mouse users benefit from, and nobody mentions. Clicking the label focuses the input, which makes small checkboxes and radios far easier to hit. Mark required fields in two channels because they serve different people. The required attribute tells the browser an assistive technology, which is what makes the field announce as required and lets validation work. And something visible tells sighted users. An asterisk alone is not enough on its own. It needs the attribute behind it and a legend somewhere saying what the asterisk means, since the convention is learned rather than obvious. This is the part that is nearly always missing. An error message rendered next to a field is invisible to a screen reader user unless it is connected, and the connection is ARIA described by on the input pointing at the message's ID. Then the error is read out as part of the field. Add ARIA invalid, so the field itself announces as invalid rather than only having a red border, since color alone carries no information to anyone who cannot see it. And put the message in a live region if it appears after the user has moved on, so it is announced when it arrives rather than only when focus returns. A set of radio buttons is one question, not four unrelated controls, and field set with the legend is how you say that. The legend is announced along with each option, so the user hears the question and then the choice rather than 4 labels with no context. Same for a group of related checkboxes and for an address block. It is one of the oldest features in HTML and one of the least used. The list on screen holds together, and the theme running through it is that every piece of information must exist in more than one channel. Errors carry color and text and an attribute. Required state carries a visual marker and an attribute. Labels are visible text and a programmatic association. Anywhere a single channel carries something on its own, either color for error, position for meaning, placeholder for label, someone loses the information entirely. That is the test to apply when reviewing your own forms, and it is faster than working through a checklist. Every input needs a real label associated by for an ID or by nesting. Placeholders are not labels, they vanish on typing and are often too low contrast to read. Mark required both visually and with the attribute. Connect errors with ARIA described by and mark the field ARIA invalid. Group related controls in a field set with a legend and check that no single piece of information depends on one channel alone. The version that looks clean in a design review. Every field has placeholder text and no label. Work through what breaks. The placeholder disappears the moment someone types, so anyone who is interrupted has no way to know what the half-filled field was for. Placeholder text is styled light gray by default and usually fails contrast requirements. Screen readers vary in whether they read it at all, and where they do, it is announced as a hint rather than a name. And nobody can click a label to focus the field because there is not one. That is 4 groups of people affected by one decision that was made to save a line of vertical space. The same form corrected. Each input has a label tied to it by ID. The error message has its own ID. The input points at it with ARIA described by, and ARIA invalid marks the field. Read the IDs carefully because that is where this goes wrong in practice. The association is a string match, so a typo produces markup that looks correct, passes review, and connects nothing. Notice as well that the error text is a sentence explaining what to do rather than the word invalid, because a screen reader user hears the message with no red border and no visual context to interpret it. The last variant is a complete form with grouping, validation, and live feedback. Read it for the field set and legend around the related controls and for where the live region sits. Then do the exercise that makes this stick. Work through the form using only the keyboard and imagine the announcements at each step, the field name, whether it is required, the error when it appears. Anywhere you cannot say what would be announced, that is a gap, and it is usually an association that was never made. The model to keep is that every piece of information in a form has to exist in at least 2 channels. A label is visible text and a programmatic association. An error is color, words, and an attribute. Required is a marker and a property. When information exists in only one channel, some group of users gets nothing, and the placeholder as label pattern is the clearest example. It puts the field's name in a channel that disappears exactly when the user needs it. Labels above inputs, errors connected by ID, and related fields group. That is most of it. The kata is the part that matters. Open the lesson, write the code yourself, then read back what you wrote and judge it. The link is in the description, and that practice is what keeps the skill yours. Kata is something you practice, not something you watch. Read the lesson, write the code yourself, then review what you wrote. This video is the reference you come back to afterwards. A model can produce this code in seconds, and the reason to write it by hand is to keep the judgment that tells you whether the code is any good. 3 lessons of rules, and this is how you find out whether you followed them. The important thing to establish first is what automated testing can and cannot do, because the tools are good and the claims made for them are not. An automated checker verifies mechanical facts. This input has no label. This contrast ratio is below the threshold. This element has an invalid role. It cannot tell you whether the label is meaningful, whether the reading order makes sense, or whether your custom widget behaves the way users expect. So the honest structure is 3 layers, and this lesson goes through them in increasing order of what they catch and effort they cost. The list on screen names the standard set. Axe core is the engine most of them are built on. JSX puts it in your unit test, so a violation fails the build. And the ESLint JSX A11i plugin catches a useful subset while you are still typing, which is the cheapest place to catch anything. Turn that lint rule on first if you do nothing else in this lesson. It costs 1 line of configuration, and it finds the missing alt attributes and the invalid role names before they exist anywhere but your editor. The pattern is 3 lines. Render the component, run Axe against the container, and assert there are no violations. 2 things about that are worth stating. It runs against whatever you rendered, so a component with a modal will only have the modal checked if the test opens it. The coverage is exactly your rendering coverage and no more. And a violation report names the rule and the element, so the failure tells you what to fix rather than only that something is wrong. Put this in the tests you already write rather than in a separate accessibility suite, because a separate suite is one nobody runs. This is the part I would emphasize most because it is a genuine 2-for-1. Testing library pushes you towards querying by role and accessible name, get by role button with the name submit rather than by test ID or class. That makes tests less brittle, which is why the library recommends it. It also means that if you cannot write the query, the element does not have a role or a name, and a screen reader user cannot find it either. Your test suite becomes an accessibility check as a side effect of being written well, and a failure to query is a real signal rather than a testing inconvenience. The list on screen is short, and the first item does most of the work. Tab through the whole thing. Then check that focus is visible at every stop, that a modal traps and returns focus, that everything reachable can be operated, and that nothing depends on color alone. All of this is 15 minutes on a page, you already know, and it catches the entire category the automated tools cannot order: meaning and behavior. The list of readers on screen matters because they behave differently, and testing on one is not testing on all. VoiceOver is built into macOS and iOS, NVDA is free on Windows, and between them you cover a good deal of real usage. What is worth saying to anyone who has not tried it, the first 10 minutes are disorienting, and that is normal. You are hearing an interface you have only ever seen. Start with something you built, turn the screen off, and try to complete one task. You will find things no tool reports, and the experience changes how you write markup permanently. Putting the automated layer in continuous integration is what stops regressions, and the useful framing is that it holds a line rather than raises a standard. It cannot make an application accessible. It can stop the accessible parts becoming inaccessible while nobody is looking. Fail the build on violations, and keep the manual pass for review rather than trying to automate a judgment. Automated tools verify mechanical facts and cannot judge meaning, order, or behavior. Enable the ESLint plugin first, then add Axe to the tests you already have. Query by role and accessible name, which improves the tests and checks the accessibility at the same time. Tab through everything by hand. Use a screen reader on your own work at least once. And put the automated layer in CI to hold the line rather than to claim a standard. The playground here is a checklist rendered as a component, and it is worth using rather than reading. Work through the items against something you have actually built, not against this page. The value is in the answers, and they will not all be yes. Notice how the items divide. Some are things a tool could check for you, and the rest are questions only a person can answer, which is the same division this lesson opened with. If you keep one artifact from this section, make it this list, and run it before you call a feature done rather than after somebody reports a problem. The model to keep is 3 layers, each catching what the one before it cannot. Lint while you type acts in the tests you already run and your own hands on the keyboard for everything that is about meaning and order rather than markup. The tools are genuinely useful and they check a minority of what matters, so treat a clean automated report as the start of the review rather than the end of it. And the single highest value habit in the whole section is still the cheapest one: press tab and watch. The kata is the part that matters. Open the lesson, write the code yourself, then read back what you wrote and judge it. The link is in the description, and that practice is what keeps the skill yours. Kata is something you practice, not something you watch. Read the lesson, write the code yourself, then review what you wrote. This video is the reference you come back to afterwards. A model can produce this code in seconds, and the reason to write it by hand is to keep the judgment that tells you whether the code is any good. This opens the machine coding section where the lessons are problems rather than concepts. A file explorer is one of the most common interview questions there is, and what it is really testing is not whether you know recursion. It is whether you can decide where state belongs when the tree is arbitrary depth, and that decision is the whole difference between a version that works and one that mostly works. A component that renders itself. That is the mechanism, and it is worth being clear about why it terminates. The recursion stops because eventually a node has no children to map over, so no further instances are created. There is no base case written anywhere, the data provides it. That is the shape of nearly every recursive component you will write. And it is why the data structure matters more than the rendering. A cycle in the data would give you infinite recursion with no obvious place to look for the bug. Read this one properly because there are 4 decisions in it worth more than the recursion itself. The first is where the open state lives. Each tree item holds its own isOpen flag in its own use state. That is a state collocation from lesson 15 applied to something arbitrarily deep. There is no map of open folders anywhere, no set of expanded IDs because each node keeps its own. Opening a folder re-renders that subtree and nothing above it. The second is the contrast with selection. The selected ID is not local. It lives in the parent and comes down as a prop with a callback going back up. And the reason is the rule from the state lesson applied honestly. Only one file can be selected at a time. So the selection is a fact about the whole tree rather than about any node. 2 pieces of state in one component, one deliberately local and one deliberately lifted, and the code tells you which is which by where it is declared. Third, look at the click handler and find the stop propagation call. Every level of this tree is a nested div with its own handler, so without it, clicking a file would fire the handler on that file and then on every folder containing it, collapsing the tree on the way up. That is lesson 5's bubbling met in the first place where it genuinely bites. Fourth, the depth prop. It is passed down and used for indentation, and it is worth noticing that the component does not know where it is otherwise. A recursive component has no idea how deep it is unless something tells it, which is a small thing and a good habit. Anything the recursion needs to know about its position has to be an argument. Then read the 2 things that are not handled, because in an interview, those are exactly what gets asked next. There is no keyboard support, so this tree is unusable without a mouse. Arrows to move right and left to expand and collapse, which is the tree pattern from the accessibility section. And the shape is fixed at build time, so nothing here adds, renames, or deletes a node. Try adding one of those and the state question gets harder immediately because now the tree is data that changes rather than a constant. The model to keep is that recursion in React is just a component that renders itself, and the interesting part is never the recursion. It is which state belongs to each node and which belongs to the tree. Openness is per node, so it lives in the node. Selection is one fact about the whole thing, so it lives above. Get that division right and the component is 30 lines. Get it wrong, so one open map in the parent or a selected ID per node, and you will spend the rest of the exercise keeping things in sync. The kata is the part that matters. Open the lesson, write the code yourself, then read back what you wrote and judge it. The link is in the description, and that practice is what keeps the skill yours. Kata is something you practice, not something you watch. Read the lesson, write the code yourself, then review what you wrote. This video is the reference you come back to afterwards. A model can produce this code in seconds, and the reason to write it by hand is to keep the judgment that tells you whether the code is any good. A search box that suggests as you type is the machine coding question that separates people, and not because it is hard to build. The naive version takes 5 minutes and works on your machine. What it does not handle is 4 separate problems that only appear under conditions you will not hit while testing: too many requests, repeated requests, responses arriving out of order, and a keyboard. This lesson is those 4, and the third one is the interesting one. Here is the problem stated exactly. You type 3 letters, so 3 requests go out. Responses do not come back in the order they were sent. The network does not promise that, and a slower query genuinely can resolve after a faster one sent later. So the results for your first 2 letters can arrive after the results for all 3, override them, and leave the user looking at suggestions for a query they finished typing a moment ago. Nothing errors. The code is correct in every individual step, and the outcome is wrong. The fix in this implementation is 4 lines and worth memorizing. The effect declares a local flag saying this request is the current one. The response handler checks that flag before touching state, and the cleanup sets it to false, which runs before the next effect. So the moment a newer query starts, the older one is marked stale and its response is discarded when it lands. That ordering is the cleanup guarantee from lesson 8 used for the thing it is best at. Read the whole component because there are 4 mechanisms in it and each one is small. Debouncing is first, and it is the custom hook from lesson 10. The query goes in, a delayed copy comes out, and the effect depends on the delayed copy rather than the raw one. 400 milliseconds, so a normal typist produces 1 request rather than 1 per keystroke. The cache is a ref holding a plain object keyed by query string. A ref rather than state, deliberately, it is lesson 9's rule applied cleanly. The cache changing does not change what is on screen, so React does not need to know about it, and putting it in state would re-render on every write for nothing. Then the raise guard we just covered. Notice where the cache write happens, inside the freshness check, so a stale response does not populate the cache either. That detail is easy to miss, and it matters because a cache poisoned by a stale response returns the wrong answer instantly, forever. And the keyboard handler. Arrow down and arrow up, move a selected index, enter accepts the highlighted suggestion, escape closes the list. Look at the prevent default calls on the arrow keys. And without those, the cursor jumps to the start and end of the input while you're trying to move through the list, which is the small detail that separates a real typeahead from a demo. 2 things to notice that are missing, because an interviewer will ask, there is no ARIA markup at all. A real combo box needs role combo box, ARIA expanded, ARIA active descendant, and the list box roles, which is lesson 35's territory and is genuinely fiddly. And there is no abort of the in-flight request. The stale response is ignored, but it still arrives, so the bandwidth is spent. An abort controller fixes that. And the reason to know the difference is that ignoring is about correctness and aborting is about cost. The model to keep is that the naive version of this component is correct in every step and wrong overall. Debounce reduces how many requests you make, the cache removes the repeats, the freshness flag makes sure the answer you display belongs to the question you last asked, and the keyboard handler is what makes it usable at all. Every one of those exists because of something that does not happen on a fast connection with a slow typist, which is exactly why this question gets asked. The kata is the part that matters. Open the lesson, write the code yourself, then read back what you wrote and judge it. The link is in the description, and that practice is what keeps the skill yours. Kata is something you practice, not something you watch.
Read the lesson, write the code yourself, then review what you wrote.
This video is the reference you come back to afterwards. A model can produce this code in seconds, and the reason to write it by hand is to keep the judgment that tells you whether the code is any good. A toast system is the machine coding problem that is really an API design problem. The rendering is a list of colored boxes in a corner. Anybody can do that. What is being tested is whether you can make it callable from anywhere without every component along the way knowing about it. And this implementation answers that in a way that uses 3 separate things this course has already built. The container renders through a portal, which is lesson 27 exactly. The toasts stay children of the provider in the React tree, so they keep its context and its event handling, while their DOM nodes go somewhere they cannot be clipped or stacked under anything. That matters more here than for a modal, because a toast can be triggered from inside any component, including one buried in a card with overflow hidden, and it has to appear in the corner of the screen regardless of where the call came from. Same mechanism as the modal lesson applied to a case where the trigger's position is genuinely arbitrary. 2 files and read the provider first because it holds the design. The state is an array of toasts in the provider, and the 2 functions that change it are add and remove. Look at what goes into the context value. Only those 2 functions, not the array. That is the split from lesson 18, and it is doing real work. A component that only wants to fire a toast subscribes to a value that never changes, so it never re-renders when a toast appears or disappears. The toasts themselves go straight to the container as a prop rather than through the context at all. Both functions are wrapped in useCallback, and here that is not decoration. The context value is an object built during render, so without stable functions, it would be a new object every time the provider re-renders, which is every time a toast is added, and every consumer would re-render for nothing. This is the case from lesson 12, where memoization genuinely earns its place, and it earns it because something downstream is comparing. Then they auto-dismiss. Add schedules a timeout that removes the toast by ID after the duration. Notice it removes by identity rather than by position, which is what makes it correct when several toasts are on screen and one is closed by hand in the middle. A version that remove by index would take the wrong one. And the hook at the bottom throws if there is no provider above it. That is the guard from the compound components lesson, and it turns the most likely mistake, calling useToast outside the provider, from an obscure failure into a sentence telling you what you did. One thing to look at critically, the timeout is not cleaned up if the component unmounts first, and it is not cancelled when a toast is dismissed by hand. The callback still fires and tries to remove an ID that is already gone. That is harmless here, because removing a missing ID is a no-op, and it is exactly the kind of thing worth saying out loud in an interview rather than hoping nobody notices. The model to keep is that this is an API design question wearing a UI costume. The interface you want is one function call from anywhere, so everything else follows. Context to reach anywhere without prop drilling. A portal, so the output is not trapped where the call happened. Functions in the context rather than data, so callers do not re-render. And stable identities, so the split actually pays. Every one of those is a lesson from earlier in this course, and the toast is just the place they all turn out to be needed at once. The kata is the part that matters. Open the lesson, write the code yourself, then read back what you wrote and judge it. The link is in the description, and that practice is what keeps the skill yours. Kata is something you practice, not something you watch.
Read the lesson, write the code yourself, then review what you wrote.
This video is the reference you come back to afterwards. A model can produce this code in seconds, and the reason to write it by hand is to keep the judgment that tells you whether the code is any good. A Kanban board is the drag and drop question, and the thing worth knowing before you start is that the browser has an API for this and it behaves oddly. There is one line in particular that makes the difference between a working board and a board where nothing ever drops, and it looks like it should not be necessary. This lesson is that API, and then the part that is actually React. 3 events carry the whole interaction. A drag start fires on the thing being dragged, and it is where you record what is moving. Drop fires on the target, and it is where you apply the change. And in between, drag over fires continuously on whatever the pointer is above. And here is the line that catches everyone. You must call prevent default in drag over, or the drop event never fires at all. That reads like a bug, and it is not. The browser's default for drag over is to refuse the drop because most elements on a page are not drop targets. Preventing the default is how an element declares that it will accept this. So the mental model is inverted from everything else. You are not adding a behavior, you are canceling a refusal. Everyone writes this component once without that line, watches cards refuse to drop, and checks their state logic for 20 minutes. The React side is smaller than the API side, and there are 3 things worth reading. First, the state is a flat array of tasks, each carrying a status, and the columns are derived by filtering that array. There is no array per column and no nested structure. That means a drop is a single update, set this task status to the target column, rather than removing from one list and inserting into another, which is 2 operations that can disagree. Flat state with a discriminator is almost always the better shape for this problem, and it is the decision an interviewer is watching for. Second, look at what drag start does. It sets React state with the dragged ID, and it also puts the ID into the browser's data transfer object. Both. The state is what this component uses, and the data transfer is the API's own mechanism, which is what makes a drag work across windows or into another application. Knowing which is which matters. If you only set React state, dragging outside the page carries nothing. Third, the update itself is a map that returns a new array with one task changed, immutable and one statement. Compare that to the to-list version where you have to remove and insert and keep both consistent, and where an interruption between them leaves the card in neither column. Then the honest limits, because this is where the follow-up questions go. There is no reordering within a column. A drop sets the status, and where the card lands inside the list is wherever the filter puts it. There is no drop indicator showing where the card will go. And the whole thing is mouse only. The native API has no keyboard equivalent, which is why every serious drag and drop library implements its own keyboard interaction rather than using this API at all. That is the honest reason libraries exist here, and it is a better answer than it is complicated. The model to keep has 2 halves. The API half is that drag over must prevent the default because you are cancelling the browser's refusal rather than adding an acceptance. The React half is that a flat list with a status field turns a move into 1 update instead of 2, and 1 update cannot leave the board in a state you did not design. And the limitation worth remembering is that this API is mouse only. The moment accessibility matters, this is a case for a library rather than a case for more code. The kata is the part that matters. Open the lesson, write the code yourself, then read back what you wrote and judge it. The link is in the description, and that practice is what keeps the skill yours. Kata is something you practice, not something you watch. Read the lesson, write the code yourself, then review what you wrote. This video is the reference you come back to afterwards. A model can produce this code in seconds, and the reason to write it by hand is to keep the judgment that tells you whether the code is any good. This closes the machine coding section, and it is the one where the old answer and the current answer are genuinely different. The way this used to be built was a scroll listener doing arithmetic. In the scroll top plus client height against scroll height, firing dozens of times a second and needing throttling to be usable. The browser now has a purpose-built API for exactly this question, and it is both simpler and cheaper. If you learned this the old way, this is the lesson where you replace it. The idea is to stop asking and start being told. You put a small element at the bottom of the list, a sentinel, and hand it to an intersection observer, which calls you when that element enters or leaves the viewport. No scroll handler, no measuring, no throttling. The browser already knows what is on screen because it has to for painting, so it can answer this question for free where your code would be recomputing it constantly. The threshold of 1 in this implementation means the callback fires only when the sentinel is fully visible, rather than as soon as a single pixel of it appears. That is a design choice about how eagerly you load. Threshold 0 fetches the moment the sentinel peeks into view, which feels smoother and fetches more. Threshold 1 waits until the user has genuinely reached the end. 4 pieces of state and 2 effects. And the interesting part is how they are separated. The first effect owns the observer, create it, observe the sentinel, and disconnect in the cleanup. That cleanup matters more than usual here. An observer holds a reference to a DOM node, and one created on every render without disconnecting leaks both the observer and the element it watches. This is lesson 8, and it is the case where forgetting is genuinely expensive. The second effect owns the fetching, and it depends on the page number. So the observer does not fetch. It increments a page and something else notices the page changed and goes to get it. That separation is worth copying. The thing detecting the need and the thing satisfying it are not the same code, which is what lets you trigger a load from a button as well without duplicating anything. Now look at the guard inside the observer callback. It checks has more and not loading before incrementing. Without that, a sentinel sitting in view during a slow request fires again on every intersection change and you request 3 pages at once. And has more is what stops it looping forever at the end of the data. An empty response sets it false, the guard stops firing, and the sentinel can sit there harmlessly. 2 limits worth naming. There is no error state. A failed request leaves loading true and the list stuck with no way to retry, which is the first thing to add. And nothing here removes items from the top, so scrolling far enough builds a very long list and every node stays in the DOM. That is lesson 21's problem arriving from a different direction, and combining infinite scroll with virtualization is the real answer for a genuinely long feed. The model to keep is that you stopped asking and started being told. A scroll handler measures constantly to answer a question the browser already knows. An observer lets the browser tell you when the answer changes. Everything else here is bookkeeping around that. A sentinel to watch, a guard, so one intersection does not become 3 requests, a flag for the end of the data, and a cleanup because an observer holds on to a DOM node. And when the list gets long enough to matter, this technique and virtualization are not alternatives, so you need both. The kata is the part that matters. Open the lesson, write the code yourself, then read back what you wrote and judge it. The link is in the description, and that practice is what keeps the skill yours. Kata is something you practice, not something you watch. Read the lesson, write the code yourself, then review what you wrote. This video is the reference you come back to afterwards. A model can produce this code in seconds, and the reason to write it by hand is to keep the judgment that tells you whether the code is any good. This opens the last section of the course, and there is no code in it. The prompt is a senior interview question, a 10-year-old application, class components, Redux everywhere, a 5 MB bundle, custom build tooling, and how would you modernize it? Everything up to now has been about what to write. This is about sequencing work across quarters while a team keeps shipping, and the honest thing to say is that the technical part is the easy half. The interviewer is checking whether you can plan organizational change, not whether you know that classes became functions. The wrong answer is a rewrite, and it is wrong for a reason worth being precise about. A rewrite delivers nothing until it delivers everything, which means it can be cancelled at any point up to that moment with nothing to show. The answer they are looking for ships value at every stage, keeps the test green throughout, and gives the organization an off-ramp if priorities change, because over 18 months, priorities will change. Before touching anything, find out what you actually have. How many class components and which of them are load-bearing? What the bundle is made of? Which dependencies are unmaintained? Because those set your real upper bound rather than your React version. And crucially, which parts have tests, because that determines the order of everything that follows. Skipping this is how you spend a quarter on the wrong battle and meet the real risk surface in production. The name comes from the tree that grows around its host until the host is gone. Practically keep the legacy code at the leaves and put thin adapters at the boundaries so new work can use modern patterns immediately, even though the screens around it are old. The reason this matters more than it sounds is political rather than technical. It means the team is not blocked waiting for a migration, and every new feature is written the new way rather than adding to the pile you are trying to shrink. Class to function, life cycle to effect, and reach for code mods rather than doing it by hand. These changes are mechanical, reviewable, and individually boring, which is exactly what you want. Each one is small enough to verify, and the behavior is meant to be unchanged. Doing this stage well is what makes the next stage survivable. Now the hard part, and the page is right to say the regressions live here. Reshaping state from spread merges into reducers, replacing context used as a global store with selectors. Those are the things this course spent its middle sections on, and each one changes how the application behaves under conditions nobody wrote a test for. Go slowly, ship behind flags, and do it after stage 3 rather than before, which is the single most important ordering rule in this lesson. TypeScript in strict mode, a modern test runner, current routing, and the compiler if it fits. 2 notes. This stage is enormously easier once the code is functions rather than classes, which is another reason for the ordering. And the React compiler is opt-in and separate, exactly as lesson 20 said. So it belongs in the tooling stage as a deliberate decision, not as something the version upgrade brings with it. Dead branches, polyfills for browsers nobody uses, higher order components that hooks replaced. The page calls the deletion the biggest win, and I would agree, for a reason worth stating. Every line you delete is a line that cannot break, cannot need updating, and does not have to be understood by the next person. It is also the stage most likely to be skipped because it looks like it produces nothing. 5, and the last one is the one people miss. Doing stage 4 before stage 3, refactoring behavior in untested code. Big bang rewrites where 6 months with nothing shipped means the project gets cancelled. Skipping the audit. Forgetting the bundle because modern React does not fix a 5 megabyte monolith on its own, and root level splitting often delivers more of what users notice than the framework upgrade does. And framing the whole thing as the React 19 project, call it modernization that happens to land on React 19, because that framing survives a change of leadership and the version named one does not. The list on screen is what a good interviewer asks next, and they are all about judgment rather than React. What stays a class component forever? How you report progress to people who do not read code. What the rollback plan is for the risky stage. How you work with the team that built and still owns the legacy version, which is the one people answer worst because the answer is about people. And which features get blocked and which keep shipping, because none is not a credible answer, and saying so shows you have done this. The sequence is audit, strangle, mechanical, behavioral, tooling, delete, in that order, and the order is the content. Ship something at every stage. Keep the test green. Put the risky behavioral work after the mechanical work, never before. Do not name the project after a version number. And be ready to say what you will not do, because a plan with no boundaries is not a plan. The model to keep is that a migration is the sequence of shippable stages, not a project with an end date. Every stage leaves the application working and delivers something someone can point at, which is what makes it survivable across the reorganizations and priority changes that will happen while it runs. The technical decisions in this lesson are ones this course already covered. What is new is the ordering, and the ordering exists because of how organizations behave rather than how React does. The kata is the part that matters. Open the lesson, write the code yourself, then read back what you wrote and judge it. The link is in the description, and that practice is what keeps the skill yours. Kata is something you practice, not something you watch. Read the lesson, write the code yourself, then review what you wrote. This video is the reference you come back to afterwards. A model can produce this code in seconds, and the reason to write it by hand is to keep the judgment that tells you whether the code is any good. The prompt here is 50 product teams, a fragmented design system, and 3 different buttons already in existence. And the question is how you stop it fragmenting again next year. The framing that makes this lesson worth watching is in its first line. Anyone can build a button, and almost nobody can keep 50 teams converging on the same button 2 years later. Everything the earlier sections taught about component design is assumed. What is being tested is whether you understand why good components get abandoned. It is a stakeholder question wearing a technical costume. The interviewer is not going to be impressed by a props API, because the reason there are 3 buttons is never that somebody could not design one. It is that a team needed something on a deadline, the design system did not have it, asking would have taken 3 weeks, and building it locally took an afternoon. Every part of this lesson is really about that afternoon and how to make the other path faster than it. Design system engineers, product engineers, designers, accessibility, brand, product managers, executives. Each want something different, and several of them can veto. Writing the map down matters because a design system fails at the seams between these groups rather than inside any one of them. And the most common seam is the one between brand and engineering, where visual drift starts and where nobody is watching until a customer mentions it. Strict semantic versioning and deprecation windows long enough that a team can plan around them. The thing to be honest about is that a deprecation without a migration path is just a message that annoys people. Ship the code mode with the deprecation, or accept that version 1 lives forever alongside version 2, multiplying maintenance and confusing everyone who joins after. A public proposal template and a review committee with rotating product engineers on it, so it is not the design system team deciding alone. And the number that decides whether this works is the turnaround time. 6 weeks and engineers stop contributing and build locally, which is the failure mode listed later in this lesson. The process is only as good as it is fast. This is the section I would put first if it were my lesson, because it is what actually works. Strong defaults, so the easy path is the correct one. Lint rules that catch a raw color import and point at the token. Design tokens synced between design tooling and code, so the two cannot drift apart by hand. Office hours, and embedding a design system engineer inside a product team for a quarter, which the page calls the highest bandwidth feedback channel you have. And I would agree, but it is the only one where you find out what is painful rather than what people bothered to report. Know which components are used, which props are used, and who is still on the old version. This is not analytics for its own sake. Without it, you cannot deprecate anything because you cannot tell who would break. A system with no usage data only ever grows. Everything stays because removing it might hurt someone and nobody can say who. This one is counterintuitive, and it is right. Give teams a controlled way to deviate, style overrides, and asChild prop, a documented escape, because if you do not, they will fork. And the difference matters enormously. A control deviation is visible and reversible, and you can go and look at how many teams needed it, which tells you what the system is missing. A fork is invisible until somebody finds it 18 months later during a brand audit. 5, and they are all versions of the same thing. The official path became slower than the local one. The team has a black box. 6-week RFCs. No deprecation discipline. No telemetry, so nothing can ever be removed. Brand and design system not talking, so drift appears and customers notice first. And the last one is the sharpest, treating governance as paperwork. Process without adoption levers is theater, and every engineer can tell the difference within a week. The list on screen is what separates a real answer from a rehearsed one. How do you handle a team that wants a one-off for an experiment? How does the design system team justify headcount when it ships no product features, which is the question that decides whether the team exists in 2 years? What the on-call story is for a bug that breaks 50 teams at once. When you fork for a different platform, and how you migrate the 3 existing buttons without freezing feature work, which is lesson 44's problem in a different costume. Governance is a stakeholder management rather than API design. Adoption levels beat process documents because lints and code mods and good defaults change what happens by default and templates do not. Telemetry is not optional because you cannot deprecate what you cannot measure. And escape hatches make deviation visible, where their absence makes it into a fork you find out about much later. The model to keep is that a design system is not a library, it is an agreement between teams, and agreements decay unless something maintains them. Every technique in this lesson is a way of making the correct path the fastest path, good defaults, lint rules that tell you the answer, code mods that do the migration, and escape hatch so a deadline does not force a fork. Build the button well by all means. Then spend your time on the reasons somebody would build their own anyway. The kata is the part that matters. Open the lesson, write the code yourself, then read back what you wrote and judge it. The link is in the description, and that practice is what keeps the skill yours. Kata is something you practice, not something you watch. Read the lesson, write the code yourself, then review what you wrote. This video is the reference you come back to afterwards. A model can produce this code in seconds, and the reason to write it by hand is to keep the judgment that tells you whether the code is any good. This is the last lesson in the course, and it closes a loop that opened in the performance section. Back there, the instruction was always measure. This asks the harder version, how do you keep something fast for 3 years through team rotation and feature pressure when the person who cared about it has moved on? 5 million users, one application, and a budget that has to survive people who were not there when it was set. The framing on screen is exact and worth repeating. Anyone can shave 200 milliseconds off a page this quarter, and the hard part is keeping it shaved when 6 new engineers join the roadmap doubles and the original champion leaves. That is a process question, not a technical one. Every optimization in the performance section of this course is a one-time win unless something defends it, and nothing about React tells you what that something is. A budget is not one number, and the reason is that each layer catches what the others cannot. 3 of them, and they are described next. A zipped JavaScript limit per root failing the build when it regresses. This is the easiest to enforce and the easiest to reason about because the number is deterministic and the feedback arrives in the pull request that caused it. It is also the layer that catches the most common regression. There is somebody imported a library to use one function from it. The 75th percentile of the core web vitals, gathered from real users rather than a laboratory. This is the layer that tells you the truth because it is measured on the devices and networks your users actually have rather than on a developer machine. It is also the slowest to react since you need enough traffic to see a change, which is exactly why it cannot be your only layer. Automated audits on representative pages at pull request time. These catch things the other two miss, and the lesson gives a specific example later that is worth waiting for. A team can improve a field metric by making the page genuinely worse and only a synthetic check notices. Every route has one named owner, and performance is a property of the team that ships features there rather than of a central performance team. This is the structural decision the whole lesson rests on. A central team that owns the numbers gets treated as the department that says no, and everyone else stops thinking about it. A central team that builds tooling and consults, while root teams own their own numbers, produces the opposite behavior. A regression beyond a threshold pages the owner. A sustained breach requires a written postmortem. And the line worth taking away is the one about those postmortems being public. It makes repeated regressions socially expensive, which the page calls the most underrated lever in performance governance. And I would agree. It works because it is not a punishment. It is a document written by the team that everyone can read, and nobody wants to write the third one. Scheduled revisits of the budget itself. Without them, budgets calcify, and a calcified budget is worse than none because it looks like governance while measuring against expectations that have moved. New routes start strict, and a team has to justify a relaxation rather than justify tightening. Same for launches, a temporary exemption with the sunset date written into the specification, not one quietly lifted and never restored. This is the same principle as the design system lesson. Make the correct thing the default, because defaults are what happen when nobody is paying attention, and over 3 years most of the time nobody is. 5 and 2 deserve highlighting. Good hearting is the sharpest. A team improves the largest contentful paint number by lazy loading the element that was the largest contentful paint, so the metric improves and the page gets worse. Field metrics will not catch that, and a synthetic check will, which is the concrete argument for having all 3 layers rather than the cheapest one. And set ones never revisited because networks get faster and devices change. A budget from 4 years ago defended today is a ceiling rather than a floor. Genuine questions with no clean answers, which is what makes them good ones. What happens when a launch really does need more budget, how you keep third-party scripts inside a budget you do not control, and how you keep any of this alive through a reorganization. Having a considered answer to the third matters more than the first two because it is the one that decides whether the other answers ever get used. Layer the budget, bundle in continuous integration, field metrics from real users, synthetic checks at pull request time, own it by root rather than centrally. Let postmortems do the enforcing. Keep defaults strict and exemptions explicit and time-boxed. And schedule the review, because the thing that kills a budget is not a bad quarter, it is nobody looking at it for a year. That is the end of the course. The last 3 lessons had no code in them, and that is deliberate. At a certain point, the limit on how good a code base is stops being what the team knows and starts being what the organization defends. The 43 lessons before this one were about knowing. These 3 are about defending. And the through line from the very first lesson still holds. Use the abstraction, understand the layer below it, and keep the judgment that tells you whether what you have built is any good. That judgment is the thing worth practicing, and it is the only part a model cannot hold for you. The kata is the part that matters. Open the lesson, write the code yourself, then read back what you wrote and judge it. The link is in the description, and that practice is what keeps the skill yours.